Hey there, welcome to the Deep Learning Full Course by Simplilearn. Do you know AI and deep learning is everywhere? From self-driving cars and voice assistant to recommendation engines and medical imaging, at the heart of these breakthroughs is deep learning, the technology that teaches machines to think, learn, and make decisions like humans. In this course, we will take you from the fundamentals of neural networks and backpropagation to advanced concepts like CNN, RNN, and GANs. You get hands-on experience building models, training networks, and solving real-world problems that power cutting-edge AI applications. And here's the exciting part. Deep learning expertise is in massive demand. Tech companies, healthcare innovators, research labs, and startups are all looking for professionals who can build intelligent systems that transform industries. And by the end of this course, you won't just understand deep learning. You'll be able to create AI solutions that make a real impact. So if you're ready to geek out on neural networks, dive into data, and become a deep learning pro, hit that like, subscribe, and let's unlock the future of AI together. Also, if you're interested below.
Introduction of Artificial Intelligence and Machine Learning. By the end of this lesson, you will be able to define artificial intelligence, describe the relationship between artificial intelligence and data science, define machine learning, describe the relationship between machine learning, artificial intelligence, and data science, describe different machine learning approaches, identify the applications of machine learning. Let's understand how the field of artificial intelligence emerged. Let's first understand the reason behind the emergence of AI. Data economy is one of the factors behind the emergence of AI. It refers to how much data has grown over the past few years and how much more it can grow in the coming years. When you look at this graph, you can clearly understand how the volume of data has grown. You can see that since 2009, the data volume has increased by 44 times with the help of social websites. The explosion of data has given rise to a new economy, and there is a constant battle for ownership of data between companies to derive benefits from it. Now that you know that data has grown at a rapid pace in the past few years and is going to continue to grow, let's understand the need for AI. As you know, the increase in data volume has given rise to big data, which helps manage huge amounts of data. Data science helps analyze that data. So the science associated with data is going toward a new paradigm where one can teach machines to learn from data and drive a variety of useful insights, giving rise to artificial intelligence. Now, you may ask, what is artificial intelligence? Artificial intelligence refers to the intelligence displayed by machines that simulates human and animal intelligence. It involves intelligence agents, the autonomous entities that perceive their environment and take actions that maximize their chances of success at a given goal. Artificial intelligence is a technique that enables computers to mimic human intelligence using logic. It is a program that can sense, reason, and act. Let's look at some of the areas where artificial intelligence is used. Artificial intelligence is redefining industries by providing greater personalization to users and automating processes. One example of artificial intelligence in practice is self-driving cars. Self-driving cars are computer-controlled cars that drive themselves. In these cars, human drivers are never required to take control to safely operate the vehicle. These cars are also known as autonomous or driverless cars. Let's see how Apple uses AI. iPhone users can experience the power of Siri, the voice. It simplifies navigating through your iPhone as it listens to your voice commands to perform tasks. For instance, you can ask Siri to call your friend or to play music. Siri is fun and is extremely convenient to use. Another example is Google's AlphaGo, which is a computer program that plays the board game Go. It is the first computer program to defeat a world champion at the ancient Chinese game of Go. Amazon Echo is another product. It's a home-controlled chatbot device that responds to humans according to what they are saying. It responds by playing music, movies, and more. If you've got compatible smart home devices, you can tell Echo to dim the lights or turn appliances on or off. You can use AI in chess, and here is an example of a concierge robot from IBM called IBM Watson. The IBM Watson AI has typically been in the headlines for composing music, playing chess, and even cooking food. Let's move ahead and look at some sci-fi movies with the concept of artificial intelligence. The films featuring AI reflect the ever-changing spectrum of our emotions regarding the machines we have created. Humans are fascinated by the concept of artificial intelligence, and this is reflected in the wide range of movies on AI. Recommendations systems are used by a lot of e-commerce companies. Let's see how they work. Amazon collects data from users and recommends the best product according to the user's buying or shopping pattern. For example, when you search for a specific product in the Amazon store and add it to your cart, Amazon recommends some relevant products based on your past shopping and searching pattern. So before you buy the selected product, you get recommendations based on your interest, and there is a possibility that you may also buy the relevant product with the selected product. If not, you have the chance to compare the selected product with the recommended products. Now let's move ahead and understand the relationship between artificial intelligence, machine learning, and data science. Even though the terms artificial intelligence, AI, machine learning, and data science fall in the same domain and are connected to each other, they have their specific applications and meaning. Let's try to understand a little about each of these terms. Artificial intelligence systems mimic or replicate human intelligence. Machine learning provides systems the ability to automatically learn and improve from the experiences without being explicitly programmed. Data science is an umbrella term that encompasses data analytics, data mining, machine learning, artificial intelligence, and several other related disciplines. Let's look at the flow diagram and try to understand the relationship between AI, machine learning, and data science. Interestingly, ML is also an element of artificial intelligence. So the first step is data gathering and data transformation. This step basically comes under data science. Data transformation is the process of converting data from one format or structure into another format or structure. Data transformation is important to activities such as data management and data integration. After gathering data, we would want to use the data to make predictions and derive insights. In order to get predictions out of the data set, we use machine learning techniques such as supervised learning or unsupervised learning. On an overview level, supervised and unsupervised learning are the machine learning techniques used to extract predictions from a given data set.
Now you must be thinking where deep learning comes into the picture. Deep learning is a subfield of machine learning involved with algorithms. It uses artificial neural networks, which are modeled on the structure and performance of neurons in the human brain. Deep learning is most effective when there isn't a clear structure to the data that you can just exploit and build features around.
Now, the next step in the flow diagram is to get insights from predictions being made. In order to do so, you need to use data analysis, which actually is the process under data science. Now, when you are done with all of these, you must want your data to perform some actions. This is where AI comes into the picture. Artificial intelligence combines predictions and insights to perform actions based on the human decision and automated decision. Now, let's move ahead and understand the relationship between artificial intelligence, machine learning, and data science. Let's look at the relationship between artificial intelligence and machine learning. Artificial intelligence is the engineering of making intelligent machines and programs. Machine learning provides systems the ability to learn from past experiences without being explicitly programmed. Machine learning allows machines to gain intelligence, thereby enabling artificial intelligence. Let's now understand the relationship between machine learning and data science. Data science and machine learning go hand in hand. Data science helps evaluate data for machine learning algorithms. Data science covers the whole spectrum of data processing, while machine learning has the algorithmic or statistical aspects. Data science is the use of statistical methods to find patterns in the data. Statistical machine learning uses the same techniques as data science. Data science includes various techniques like statistical modeling, visualization, and pattern recognition. Machine learning focuses on developing algorithms from the data provided by making predictions. So, what is machine learning? Machine learning is the capability of an artificial intelligence system to learn by extracting patterns from data. It usually delivers quicker, more accurate results to help you spot profitable opportunities or dangerous risks. Now, you must be curious to understand the features of machine learning. Machine learning uses the data to detect patterns in a data set and adjust program actions accordingly. Pattern detection can be defined as the classification of data based on knowledge already gained or on statistical information extracted from the patterns. It focuses on the development of computer programs that can teach themselves to grow and change when exposed to new data by using a method called reinforcement learning. It uses external feedback to teach the system to change its internal workings in order to guess better next time. It enables computers to find hidden insights using iterative algorithms without being explicitly programmed. Machine learning uses algorithms that learn from previous data to help produce reliable and repeatable decisions. It automates analytical model building using the statistical and machine learning algorithms that tease patterns and relationships from data and express them as mathematical equations. Let's understand the different machine learning approaches. So, what is the actual difference between traditional programming and machine learning? In traditional programming, data and program is provided to the computer. It processes them and gives the output. However, the machine learning approach is very different. In machine learning, algorithms are applied on the given data and output. The result of the applied algorithm and calculations is a learning model that helps machine to learn from the data. In traditional programming, you code the behavior of the program, but in machine learning, you leave a lot of that to the machine to learn from data. Now, let's first understand the traditional programming approach. Traditionally, you would hard code the decision rules for a problem at hand, evaluate the results of the program, and if the results were satisfactory, the program would be deployed in production. If the results were not as expected, one would review the errors, change the program, and evaluate it again. This iterative process continues till one gets the expected result. What is the machine learning approach? In the new machine learning approach, the decision rules are not hard-coded. The problem is solved by training a model with the training data in order to derive or learn an algorithm that best represents the relationship between the input and the output. This trained model is then evaluated against test data. If the results were satisfactory, the model would be deployed in production, and if the results are not satisfactory, the training is repeated with some changes. Machine learning techniques. Machine learning uses a number of theories and techniques from data science. Here are some machine learning techniques: classification, categorization clustering, trend analysis, anomaly detection, visualization, and decision making. Let's look at these techniques. Classification is a technique in which the computer program learns from the data input given to it and then uses this learning to classify new observations. Classification is used for predicting discrete responses. Classification is used when we are training a model to predict qualitative targets. Categorization is a technique of organizing data into categories for its most effective and efficient use. It makes free text searches faster and provides a better user experience. Clustering is a technique of grouping a set of objects in such a way that objects in the same group are most similar to each other than to those in other groups. It is basically a collection of objects on the basis of similarity and dissimilarity between them. Trend analysis is a technique aimed at projecting both current and future movement of events through the use of time series data analysis. It represents variations of low frequency in a time series, the high and medium frequency fluctuations being out. Anomaly detection is a technique to identify cases that are unusual within data that is seemingly homogeneous. Anomaly detection can be a key for solving intrusions by indicating a presence of intended or unintended induced attacks, defects, faults, and so on. Visualization is a technique to present data in a pictorial or graphical format. It enables decision makers to see analytics presented visually. When data is shown in the form of pictures, it becomes easy for users to understand it. Decision-making is a technique or skill that provides you with the ability to influence managerial decisions with data as evidence for those possibilities. Now, I am sure you have a better understanding of the overview of machine learning, so let's look at some real-time applications of machine learning. Artificial intelligence and machine learning are being increasingly used in various functions, such as image processing, robotics, data mining, video games, text analysis, and healthcare. Let's look at each of them in more details. So what is image processing? It is a technique to convert an image into a digital format and perform some operations on it so as to induce an enhanced image or to extract some helpful information from it. Let's look at some of the examples of image processing. Facebook does automatic face tagging by recognizing a face from a previous user's tagged photos. Another example is optional character recognition, which scans printed docs to digitize the text. Self-driving cars are another big example of image processing. Autopilot is an optional drive system for Tesla cars. When autopilot is engaged, cars can self-steer, adjust speed, detect nearby obstacles, apply the brakes, and park. Now let's see how robotics uses machine learning. Robots are machines that can be used to do certain jobs. Some of the examples of robotics are where a humanoid robot can read the emotions of human beings, or an industrial robot is used for assembling and manufacturing products. So let's look at some real-time applications of machine learning. Let's see what data mining is. It is the method of analyzing hidden patterns in data. Let's look at some of the applications of data mining. It is used for anomaly detection to detect credit card fraud and to determine which transactions vary from usual purchasing patterns. It is also used in market basket analysis, which is used to detect which items are often bought together. It can be used for grouping, where it classifies users based on their profiles. Machine learning is also applied in many video games in order to give predictions based on data. In a Pokemon Go battle, there is a lot of data to take into account to correctly predict the winner of a battle. And this is where machine learning becomes useful. A machine learning classifier will predict the result of the match based on this data. Let's move on to one of the most popular applications of machine learning, which is text analysis. It is the automated process of obtaining information from text. One example of text analysis is spam filtering, which is used to detect spam in emails. Another example is sentimental analysis, which is used for classifying an opinion as positive, negative, or neutral. It detects public sentiment in Twitter feed or filters customer complaints. It is also used for information extraction. such as extracting specific data address, keyword, or entities. There are many applications of machine learning in the healthcare industry, identifying disease and diagnosis, drug discovery and manufacturing, medical imaging diagnosis, and so on. Some of the companies that use machine learning have revolutionized the healthcare industry are Google DeepMind Health, BioBeats, Health Fidelity, and Ginger.io.
So what is deep learning? Deep learning is a subset of machine learning which itself is a branch of artificial intelligence. Unlike traditional machine learning models which require manual feature extraction, deep learning models automatically discovers representation from raw data. So this is made possible through neural networks, particularly deep neural networks which consist of multiple layers of interconnected nodes. So these neural networks are inspired by the structure and the function of human brain. Each layer in the network transforms the input data into more abstract and composite representation. For instance, in image recognition, the initial layer might detect simple features like edges and textures, while the deeper layer recognizes more complex structure like shapes and objects. So one of the key advantages of deep learning is its ability to handle large amount of unstructured data, such as images, audios, and text, making it extremely powerful for various applications. So stay tuned as we delve deeper into how these neural networks are trained, the types of deep learning models, and some exciting applications that are shaping our future. Types of deep learning. Deep learning AI can be applied supervised, unsupervised, and reinforcement machine learning using various methods for each. The first one, supervised machine learning. In supervised learning, the neural network learns to make prediction or classify that data using labeled datasets. Both input features and target variables are provided, and the network learns by minimizing the error between its prediction and the actual targets. A process called backpropagation. CNN and RNN are the common deep learning algorithms used for tasks like image classification, sentiment analysis, and language translation. The second one, unsupervised machine learning. In unsupervised machine learning, the neural network discovers patterns or clusters in unlabeled datasets without target variables. It identifies hidden pattern or relationship within the data. Algorithms like autoencoders and generative models are used for tasks such as clustering, dimensionality reduction, and anomaly detection. The third one, reinforcement machine learning. In this, an agent learns to make decisions in an environment to maximize a reward signal. The agent takes action, observes the records, and learns policies to maximize cumulative rewards over time. Deep reinforcement learning algorithms like deep Q networks and deep deterministic polygradient are used for tasks such as robotics and gameplay. Moving forward, let's see what are the artificial neural networks. Artificial neural networks, RNNs, inspired by the structure and the function of human neurons, consist of interconnected layers of artificial neurals or units. The input layer receives data from the external resources and it passes to one or more hidden layers. Each neuron in these layers computes a weighted sum of inputs and transfers the result to the next layer. During training, the weight of these connections are adjusted to optimize the network's performance. A fully connected artificial neural network includes an input layer or more hidden layers and an output layer. Each neuron in a hidden layer receives input from the previous layer and sends its output to the next layer. So this process continues until the final output layer produces the network response. So moving forward, let's see types of neural networks. So deep learning models can automatically learn features from data, making them ideal to tasks like image recognition, speech recognition, and natural language processing. So the most common architecture in deep learnings are the first one, feed-forward neural network, FNNs. So these are the simplest type of neural network where information flows linearly from the input to the output. They are widely used for tasks such as image classification, speech recognition, and natural language processing, NLP. The second one, convolutional neural network, designed specifically for image and video recognition, speech recognition, NLP, and language translation. So now let's move forward and see some deep learning application. The first one is autonomous vehicle. Deep learning is changing the development of self-driving car. Algorithms like CNNs process data from sensors and cameras to detect objects, recognize traffic signs, and make driving decisions in real time, enhancing safety and efficiency on the road. The second one is healthcare diagnostic. Deep learning models are being used to analyze medical images such as X-rays, MRIs, and CT scans with high accuracy. They help in early detection and diagnosis of diseases like cancer, improving treatment outcomes and saving lives. The third one is NLP. Recent advancement in NLP powered by deep learning models like Transformer, ChatGPT have led to more sophisticated and human-like text generation, translation, and sentiment analysis. So applications include virtual assistant, chatbots, and automated customer service. The fourth one, deepfake technology. So deep learning techniques are used to create highly realistic synthetic media known as deepfakes. While this technology has entertainment and creative application, it also raises ethical concern regarding misinformation and digital manipulation. The fifth one, predictive maintenance. In industries like manufacturing and aviation, deep learning models predict equipment failures before they occur by analyzing sensor data. Their proactive approach reduces downtime, lowers maintenance costs, and improves operational efficiency. So now let's move forward and see some advantages and disadvantages of deep learning. So first one is high computational requirements. So deep learning requires significant data and computational resources for training. Whereas advantage is high accuracy, achieves state-of-the-art performance in tasks like image recognition and natural language processing. Whereas deep learning needs large labeled datasets, often require extensive labeled dataset for training, which can be costly and time-consuming together. So second advantage of deep learning is automated feature engineering. Automatically discovers and learns relevant features from data without manual intervention. The third disadvantage is overfitting. So deep learning can overfit to training data, leading to poor performance on new unseen data. Whereas the third deep learning advantage is scalability. So deep learning can handle large complex dataset and learn from massive amount of data. So in conclusion, deep learning is a transformative leap in AI, mimicking human neural networks. It has changed healthcare, finance, autonomous vehicles, and NLP.
Deep Learning Tutorial. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you? We're going to go over applications of deep learning. What is deep learning? Why is deep learning important? What are neural networks? The activation function in our neural network, the cost function that comes in for processing our neural networks, how do neural networks work, deep learning platforms, and then we'll do introduction to TensorFlow and a use case implementation using TensorFlow so you can see how it works and get some hands-on. So start off with the applications of deep learning. Deep learning helps us make predictions about the rain, earthquakes, tsunamis, etc., allowing us to take the required precautions. With deep learning, machines can comprehend speech and provide the required output. Deep learning enables a machine to recognize people and objects in the images fed to it. And with deep learning, advertisers can leverage data to perform real-time bidding and targeted display advertising. And these are just a small sample of the myriad of different uses for deep learning today. So what is deep learning? Deep learning is a subfield of machine learning that deals with algorithms inspired by the structure and function of the brain. When we look at this, we have the larger category, which is artificial intelligence, very generic, comprehensive ideal. And in there we have machine learning, and then a subcategory of machine learning is deep learning. So when we talk about artificial intelligence, this is the ability of a machine to imitate intelligent human behavior. So when we look at something, can it solve a problem the way humans do? Can we take it to that next level? So it's just not repeating some kind of simple output that we programmed it to do. Can it actually start imitating human intelligence? And we look at machine learning, we have the application of AI that allows a system to automatically learn and improve from experience. So machine learning, the most basic machine learning, is your linear regression model. You put a bunch of dots on the graph and you draw a line through them, and you have a guess of what X and Y are based on what X is, you can guess what Y is. And finally, we have our deep learning, application of machine learning that uses complex algorithms and deep neural nets to train a model. Why is deep learning important? It works with unstructured data. Machine learning works only with large sets of structured and semi-structured data, while deep learning can work with both structured and unstructured data. Handles complex operations. Deep learning algorithms can perform complex operations easily, while machine learning algorithms cannot. Feature extraction. Machine learning algorithms use labeled sample data to extract patterns, while deep learning accepts large volumes of data as input. Analyze the input to extract features out of an object. Achieve best performance. Performance of machine learning algorithms decreases as the amount of data increases. So to maintain the performance of the model, we need deep learning. And this is always a challenge of when do you go from machine learning, doing linear regression or other regression models, to deep learning neural networks. It really centers around both the complexity as it becomes more and more complex, or the problem becomes harder to solve, along with the amount of data. So both of those play a huge part in deciding which would best serve your purposes to predict what your data is going to do and try to predict the outcome. So what are neural networks? With deep learning, a machine can be trained to identify various shapes. So here we have a square coming in. You can see we've broken it up into the pixels, and we want the label to come out square. And if we turn the square slightly sideways, it's still a square, and we want it to still say it's a square. With deep learning, a machine can be trained to identify various shapes, or the different patterns of those shapes as they are in this case being rotated. But how is the machine able to do this? So we'll look at a nice grid, 28 by 28, 784 pixels. And when we look at that grid, we can look at each one of those pixels as inputs. So a neural network is a system modeled on the human brain. And so we have all our inputs, kind of like your eyeball coming in there. It has the sensors in the back, your different input sensors, which are your cones and rods. So each one of those is an input coming in with information. And it goes into a neuron, and then it sends out a pulse. So the data is fed as an input to the neuron. The neuron processes the information provided as an input. The information is transferred over weighted channels. And this is very central to our neural network. Each one of those pulses coming in gets a different weight. And the output is the final value predicted by the artificial neuron. In this image, we're only looking at one neuron. So remember, we're talking about a lot of neurons working together. And we'll look at how those fit together in just a moment. When we look at one neuron, so let's just take a look at that one neuron. Let's dig a little deeper so we can get some concepts in here so we can understand the neural network. So what exactly happens within a neuron? We have an activation function. So within each neuron, the following operations are performed. The product of each input and the weight of the channel it's passed over is found. Sum of the weighted products is computed. This is called the weighted sum. And a bias unique to the neuron is added to the weighted sum. And you can always look at that as if you have an XY graph, where's your y-intercept? You know, the old Euclidean geometry, x or y equals 3x plus 5. That's your plus 5 is that bias, is where does that come in. And this is a little bit more complicated because it's not like 3x, it's more like 3x1, 5x2, 6x7, and usually you're dealing with float numbers. So it doesn't even look like that. It looks like 0.001 times x1, 0.13 times x2, and so on. So the numbers get a little confusing, but the concept is very straightforward. We're going to multiply the weight times the value coming in, and we're going to add that all together plus the bias. And the final sum is then subjected to the particular function known as the activation function. And the most simplest one is if it's greater than 0, it's 1. If it's less than 0, it's 0. They usually use there's a lot of other functions that are more reliable than that one. But that one gives you the most basic understanding of what you're looking at. 0 or 1 coming out. In most cases, you actually have a value coming out. And in some cases, we use like a tangent wave so that there can be a value between 0 and 1, but it might be, it tends to shoot right up to 1 rather quickly. But you know, those are things you can fine tune in your neural network as you start getting to the solution. Let's keep into the generals here and let's see what's the next step. We're going to look at the cost function. And this is so important in understanding how the current neural networks that we're working with are able to learn things. So we end up with a cost value. The cost value is the difference between the neural net's predicted output and the actual output from a set of labeled training data. The least cost value is obtained by making adjustments to the weights and biases iteratively throughout the training process. And when you think about this, we're not just sending one set of numbers through, we're sending all kinds of data in here. So you might have 100 samples or 1,000 samples, and each one of those samples comes in, and then we look at the cost for that. And we want to get that cost, the average minimal among all the different samples. So we want a general answer on there. You can see here we denote the predicted output with a little half triangle over it, and then the actual output is just a straight Y on this. Let's learn how neural networks work. Let's dig in a little deeper in how we program them. How do neural networks work exactly? In this, we're jumping from a single node into a larger picture. So our neural network will be trained to identify shapes. And we'll start with the square again, 28 by 28 or 784 pixels. And this is kind of one of the standard images we work with a lot of times. Our shapes are images of 28 by 28 pixels. Each pixel is fed as an input to the neurons in the first layer. So here we have our input layer. Each one of those, we might flatten that out. That's the most easiest way to process that, but not the only way to process. So we flatten it out so it's just one long array. And then we have hidden layers that improve the accuracy of the output. And you can see here we're not looking at just one neuron. We actually have a row, 2 hidden layers, and each layer is a row of neurons. And data is passed on from layer to layer over weighted channels. Each one of those inputs is then weighted to each of the next neurons in the next layer, in the hidden layer. Each neuron in the first hidden layer takes a subset of the inputs and processes it. Let's look into what happens within the neurons. So here we have step 1, and we can see in here where we have x1 times weight 1, x2 times weight 2 plus b1. That's that top neuron up there. And then we have the next neuron down, which is step 2. And then in step 2, they denote with the Greek symbol phi, and phi is the activation function based on step 1. So it might be if it's close to 0, it's 0. If it's close to 1, it's 1, and it might be a value in between. It's very common, depending on what activation function you use. The results of the activation function determine which neurons will be activated in the following layer. So you can see here we have B1, that's what we looked at with x1 and weighted 1, x2 and weighted 2, and then you would compute B2 the same way, and B3 the same way, and B4 and B5 and so on. So each neuron has an input from all the input layers go into each of the hidden layer neuron, the first hidden layer. The result of the activation function determines which neurons will be activated in the following layer, and then that activation number goes off to the next layer. So we see here B11, B12, B13, and B14, and the weights coming in from B1. So let's say B1 fires and it goes into B11. Usually you would see the weights going all the way down. So B2 would have their weights going into B1, and B2 would then go into B11. B1, B2, B3, and B4 and B5 would then go into B11, and they would have their weights depending on what came out. It might just be 0, so there's nothing coming through, or it might be a value between 0 and 1, and so forth for B12, B13, B14, and B15. And then we take those, and they'll have the weights attached to each one of those coming out, and they go into the final layer. In this case, we have a neuron that represents a square, a neuron that represents a circle, and a neuron that represents a triangle. And just as before, the information reaching this layer is processed, after which a single neuron in the output layer gets activated. But our input was a square. What went wrong here? Remember, we started with a square. What do we have coming out? It said a circle. Well, that's going to be a problem because we don't want it to tell us that squares are circles. Well, our network needs to be trained first. How do we train a network? The predicted output is compared against the actual output by calculating the cost function. Remember our cost function at the end? We take whatever we said it was going to be and what it actually is, and we just subtract those two. And the most common way used to generate the cost function is as follows, is we're going to take the actual value minus the predicted value, where you have y, and then you have y with the half triangle over it is the predicted, and then y is the actual value. We subtract them, we square that value, and then we divide divided by 2. So it's usually how they generate the cost function. The cost function determines the error in prediction and reports it back to the neural network. So we're going to do some backpropagation. That's what this is called, backpropagation. We're going back through the network the other way, and we're sending that error back the other way. The weights are adjusted in order to reduce error. The network is trained with the new weights, and you can see here we have c equals 1/2 y minus y predicted, or y actual minus y predicted squared. Once again, the cost is determined and backpropagation is continued until the cost cannot be reduced any further. Now, keep in mind, if we have one picture of a square and it goes through, we actually do just a little training. We don't change it all to match that first one. Otherwise, you'll have what they call a bias. So each of those data goes back with our backpropagation, and we'll send hundreds of samples on there until we can get that cost as a whole down as low as we can get, so that our average cost is very low, without it being biased towards one specific figure. And you can see here we have our input layer, hidden layer, and our setup on here. Similarly, once we've trained it for our square, the network must also be trained to identify circles and triangles too. So we need sets of all of these. We need lots of squares, lots of circles, and lots of triangles. The weights are this further adjusted in order to predict the 3 shapes with the highest accuracy. We can now rely on our neural network to predict the input shapes. And you can see we have a triangle coming in here, and it goes through. Here's our circle going through, and it's going to light up the circle, and so on for the square. So before we dive into some hands-on, let's take a look at some deep learning platforms. The primary programming language, we're going to look at 4 of these platforms, and we're going to start with Torch. The primary programming language is Lua with an implementation in C2. Torch's Python implementation is called PyTorch. And this is interesting because Python has become one of the leads in data analysis. So you'll almost always see a PyTorch, or any one of these will have a Python equivalent, and it's slowly spreading throughout the languages. So I'm sure there's within Torch, it's also probably got a Java set up, and definitely has a C because its primary implementation is in C. And so we have Keras. Keras is a Python framework for deep learning, and USP is reusability of code for the CPU and GPU processing. We have TensorFlow. TensorFlow is deep learning platform by Google. It was developed in C++ and has its implementation in Python. And just a quick highlight, Keras and TensorFlow have slowly been working together. So there's a lot of things that you can actually put Keras on top of TensorFlow and access TensorFlow. Although there are still some tools in TensorFlow that Keras doesn't fully access. But it is a great interface for doing that. And then there's it has really, once they open sourced it, it was just amazing how much it's spread in use and how many tools are linked into TensorFlow. Tensors are vectors or matrices of n dimensions. And you can see here we have dimension 5, we have a dimension 4 by 5, or 5 by 4 as the case is, 5 rows by 4 columns. Here's one where it's 3 by 3 by 3. And so this is kind of nice because when you're processing pictures, there's certain things you want to do where you want the pixels to be next to each other. That's very important. Same thing if you're processing, say, a movie. You might want a 3 by 3 grid coming in where you have the layers of the frames coming in to be processed. So you can see how having different dimensions is really helpful in analyzing certain data structures. And this is what's so great about tensors is you can, of course, flatten them out like we did earlier, or you can process them based on their location. In TensorFlow, all computations performed involve tensors. So everything going through is always looked at as tensors, as a matrix, or matrices of n dimension. TensorFlow architecture is as follows. Pre-processing data, build a model, train and estimate the model. And what we'll do is we'll go ahead and dig into use case implementation with TensorFlow. To do that, I'm actually going to go into, in this case, I'll be using the Anaconda Navigator. And you can use either Jupyter Lab or Jupyter Notebook. Most people are very familiar with Jupyter Notebook. It's very commonly web-based. The Jupyter Lab is the next version of Jupyter Notebook, and it just lets you have multiple tabs open when you're working on it. And if you're using Anaconda, you'll go under Environments, and you'll want to make sure that you have your TensorFlow installed. And you can simply, we'll do this, I have it installed, but you could do all, we'll do all. You can do a search under all for Tensor, and you can see all the different tensors. It's actually installed in here, version 1.13.1. If it wasn't you could check the box and then run the install on there and it'd bring it right in. But we'll go ahead and start up our Jupyter Lab, which is going to open up, in this case I use Google Chrome. And in our Jupyter Lab or Jupyter Notebook, if you're in the notebook you only have one tab and you won't have the added options, like there's a folder and different things you can do in the lab that you can't do in the notebook. But everything we're going to do you can easily do in the notebook. And you'll start up a new project. Deep learning is what I'm going to call this. And if you're not familiar, you can definitely, we have some tutorials out on the use of Jupyter Notebook and how to run it and set it up and things like that. The most basic is we put our code in here. It has a nice display, a nice interface, especially for data science. I can display all kinds of things on this page, and then you can just run this page right here. There's no code in it, so it's not going to show any thing until I put some code in there. And of course you can cut your cells and things like that. So the first thing we want to do is we want to import our tools. Now if you haven't, remember you got to install TensorFlow, and we'll also use Pandas. Pandas is a nice database setup. And that again is underneath your environment, and you can see here your whatever you're working on, my Simplilearn setup, where I've installed TensorFlow and Pandas in here. And I'll simply go up here and run this. I'm not going to see anything, so we've just imported those into our notebook that we're working on. So those are now available to us. And it helps to have some data to work with. And we have here, I'm going to create a path and a test path. And we'll go ahead and let's just highlight this whole path. And you can always post a note either down below in the YouTube video, or you can post a note on Simplilearn.com and ask for this path if you're not quite picking it up. But it is over here at the UCI EDU on their setup, and it's in their archive. So it's archive.ics.uci.edu/ML for machine learning /machine-learning-databases/adult. That's quite a mouthful. And in this case, we have adult data and adult test. But let's go ahead and just take a look at that. Let me just paste that right in there to our browser window. And here's our adult data. And if I click on there, it's going to come down as a download. I'm going to go ahead and open it as a text in my notepad. And the guys in the back were kind enough to look up to find out what the actual columns were in this coming across. So let me go and take that to pull that information. And it doesn't matter whether I put it before or below because these are just variables. But we can see here that we have age, work class, final WGT. I'm guessing that's final. We'll look that up in just a second to see what that matches. In fact, let's pull that up and just put them next to each other so we can kind of see what we got here. So we have age, we have our working class, state gov, maybe final wage, 77,516, education of bachelor's, education number 13, marital, never married, admin, clerical, relationship not in family, so on and so on. So it goes all the way across here. And so we've pulled out this information, native country, label, etc. We'll go ahead and run this. And so now we've loaded all our different paths. And this path, by the way, this is the same columns on here, so I don't need to create a separate columns on the adult test. And once we've run this, we've set those variables, let's go ahead and pull that data in. And to do that, we'll use Pandas. And we'll create a df train, a df test. Each one's going to have our PD for pandas.readcsv. It'll have our path we put in there, our path test. The first one went ahead and skip initial space, true, names columns. There's our columns in there. Index column equals false, there's no index column. On the second one, if we went back into here and we open up adult test, let me just go ahead and open that up, pad. You'll see there's an actual row up here we want to skip. 1x3 cross validator with all the same data in it. So we're looking at the same data in there, and here we're going to go ahead and bring in our data. And then once you bring it in, it's always nice to see what kind of shape your data is in. And of course, when we talk about shape, we're talking about how many rows and columns, not whether it's been lifting weights. We can see here we have, each one has 15 columns, and that goes with our columns right here. If we counted them, there's going to be 15. And the first data set has 32,561 rows, where the second one has 16,281 rows. And it's also good to see just how the data came in, so we'll use the pandas D types. We'll run that. And you can see here where age came in as an integer 64, working class as an object, which makes sense. And then we have our FNL WGT, the education as objects, or, well, this is an integer object, so on, all the way down. And if we flash back to the data, we look at the last column, it's less than or equal to 50K. And if we scroll down enough, we'll see it's also greater than or equal to 50K. So we'd like to kind of give that its own special setup on that label. So on that feature, we're going to set the label equal to, if it's less than or equal to 50K, it's going to be 0. And if it's greater than or equal to 50K, it's going to be 1. So it's one or the other. That's always an easy thing to read. And then we can take this and we can go dftrain.label equals label item for item in dftrain label. And this just loops through all the labels. There's a lot of ways we can do this. Pandas, this might be actually kind of a slower way. There's a way to do just that setup and do the logic within the setup instead of doing a loop. But for this thing, it'll work fine. We're not dealing with a lot of data. It's a large data set, but it's not that big of a data set as data goes. And we also want to do it for our test data. I didn't really mention that we created we're looking at two different data sets. One, we're going to train the data, and then we're going to take it and run the test data to see if it works. So we have our two different data sets, and we didn't catch it off the bat. If you were pulling up this, you're going to pull up one, this is the training set. And if we go back in here and open up the test set, let me just go back and do that, adult test. One of the things that we didn't notice that you'll want to pull up is at the end there's a period. So we're pre-processing our data. We want to make sure that we include that period in every line on the second setup. So when I go back to my Jupyter Notebook, I've got to have a label T, which is less than or equal to 50K period, or greater than or equal to 50K period for 1. Otherwise, it's doing the exact same thing. We're going to change the df train label and the df test label to 0 or 1. We'll just run that. We'll go ahead and print the df train label value counts and the df test label value counts. And this is always a good idea because we want to know, is there any weird stuff going on there? If there's null values, stuff like that, this will turn up on that setup. And we can see here we have zeros, how many ones, and so on there. Just a quick view of the data that we're going through. And if we go back up here, go ahead and print the train D types again. And we run that. You could actually run it up there and it'd give you the new answer because it's loaded this information. We now see it's an integer. And if you go back up here, it was an object. So that makes life a little easier as far as what we're doing with this. Now at this point, we're going to look at the data and we can see we have a lot of numbers and we have a lot of categories in here. So categories would be United States, male, never married versus 7. And we can also see that when we looked at this, we have our integers, we have our objects, working class. So the next thing we want to do on there is we want to go ahead and take that where we have integers and the objects, and we want to bring that down here. We want to create those categories in a way that the computer can see them. And we'll start with our continuous features like age. We can see age integer, FNLWGT is an integer, capital gain is an integer, educational number, there's our educational number is an integer, and so on. So if we're going to have these as continuous features where they're an integer, we also need to make a list of the categorical features we want to work with, such as working class, education, marital, occupation, relationship, race, sex, and native country. And again, these are all objects, so that makes sense. And when we flip back over to the data, we can see here we're actually looking at United States. If we continue down, see if I can find another one. A lot of United States on this particular one. I was getting worried there for a second that we only had United States and it was a very biased census, which it probably is for wherever it came from. And of course, bachelor's, associate, vocational, some college. So you can see this is more categorical versus an actual number. So now we have our categorical and we have our continuous features. And this is just the list of these. So let's go ahead and run that and load that list in there so we can now start manipulating our data with it. Now we get our first line of TensorFlow code, which is exciting. And we're going to create a variable continuous features. And what we're doing in here is we're going to go into TF feature columns. So we have the feature columns. We're going to set those up. Numeric columns K for K in continual features. So this is going to go in here and says each one of these is a continual feature, and we're going to feed that into the feature column. Not very exciting on the output because we're just creating this variable here, letting it know what columns are what. And then we're going to create a relationship setup. So we have continuous features and then we have a relationship. And again, we're doing TF, but in this case we use feature column. So just like this one, we're telling it feature column, and now we do categorical column with vocabulary list. So that's one of the things we can do with TensorFlow. And we're going to feed it one. We have relationship, and so we're just drilling down to the relationship column. And these are the options they had. So this is going to be the vocabulary attached to this column. And we'll go ahead and run that. So we load up our relationship. And then we're going to do one more way of loading. In this one, we're going to do categorical features. And so in categorical features, we're going to do TF feature column. There's our command we've already seen before. And it's going to be categorical column with hash bucket. We're going to create buckets. In this case, for K in categorical features, so it's going to create a bucket for each one of these categorical features. And the bucket size is 1,000. So we're looking at, and we've actually kind of repeated something because relationship is also in the bucket setup on there. But we wanted to show you three major ways of loading in your different features. One is our features that we know where it's going to be a number. So our continuous features. Then we can set it as a relationship. In this case, we actually created a vocabulary, husband, not in family, very clear vocabulary on there. And then we also are loading just general categories into buckets. You can set different bucket settings in here. We went ahead and just went with 1,000, so pretty much everything, since there's not a huge number of categories, each one gets their own kind of bucket setup in there. And as far as the initial setup, we need to go ahead and create a model. And so this is where it starts to come together. We've, as far as the pre-setup, we have our TF, we have an estimator. We're going to do linear classifier on the estimator. In classes equals 2, so we know there's only 2 classes we're looking at. We have ongoing train feature columns. And then we have our different, we have categorical features plus continuous features. So this basically creates our model, what data is going in. And we'll go ahead and run this. And you can see here that it gives us a little information that we had our TensorFlow using default config. You can change a lot of defaults you can change as far as a model directory, random seed, saving summary, checkpoints. There's all kinds of things you can go in here and set up. Rewrite options, keep checkpoint mix, etc. At this point, the model hasn't done anything. All we've done is create the model. So let's just do a real quick rehash of what we've done so far. What we started off with is we grabbed some data. In this case, adult and adult tests. We have a training data set and a test data set. We set the columns up. We took a very short, brief exploration of the data and its shape as far as what we're working with. We changed our label around a little bit so that the label makes a little bit more sense of 0, 1. Instead of, for the machine, it's easier to spit out a 0 or a 1. We can look up here, we double check to make sure how many zeros and ones we have. Double check our data, make sure it's integer 64, nothing weird's going on. And then we looked at 3 different ways that we can kind of label the data as far as the way we're going to read it. We have our continuous features and a categorical features. Here's our relationship, which is one of them. When we went ahead and created our model, we did not put the relationship in here. Which you can do. You can actually maybe take it out of categorical and then have its own on here instead of having categorical features and continuous features and so on. So we've created our setup for our model. The next thing we need to do is we need to go ahead and create a function letting it know how to read the data into our model. How are we going to train it? And let's go ahead and create 2 variables. The first one is going to be features. This is just all the features that are in there. And then the second one is going to be our label. And this is basically, we're looking at all the different information we can put into it. And then is that person, based on that information, going to make less than or greater than 50K? That's what that comes down to. Now, the next part, the definition we're going to create has a lot in it. And we're going to feed this definition into our model training. So there's a lot of stuff that goes on here. First, we'll call it get input in function. Def get input function. We have our data set, number of epochs equals none, in batch equals 128, shuffle equals true. So we're running this, and it's going to return a TF estimator inputs pandas input function. And in this case, it's going to be x equals our PD data frame K dataset K values for K in features. Y is PD series dataset label values. Batch size equals in batch. Number of epochs equals number of epochs. Shuffle equals shuffle. So in here, we're passing in the number of epochs. We're not too worried about, we're going to just go once through the data because there's a lot of data in there. We don't need to rerun it. Epochs is how many times do you cover all the data? And then how many groups of data do you pull in and batch at a time? So we're only going to look at 128, do the reverse propagation like we talked about, and then it'll go to the next batch, and the next batch, and the next batch, and it shuffles them. So shuffle means that we're randomly picking where they're coming from. And we're not too worried about the number of epochs for this particular model. Depending on how much data you have and depending on what you're running, depends on how many epochs you need to run. And there's a lot of rules on how many epochs you need to run. One of them is if your training data and your testing data, because you'll check your testing data against your training data. If your testing data starts having a better results than your training data, that means you're no longer fitting towards the data, but you're fitting to the answer. So it's kind of these little weird things you start to on here. And TensorFlow is really cool because it actually checks a lot of that for you. But we're just going to set number of epochs equal to 0, and then we have our data set going in. So we're creating our get function. How do we get the data into training our model? And we'll go ahead and run that. So now we have our data function, and now it knows where the data is coming from. So we need to go ahead and train it. And that's simply we take our model we created way up here. That's where we take the model there. We've told it what columns it's going to pull in, so it knows what columns it's looking at, know what the definition where it's going to get the information from. So now we want to go ahead and train it. And here's our input function equals, in this case, get input function. And here we tell it that our data set is a df train, number of epochs equals none, which is already automatically set up there. In batch equals 128, which is what we have up here. Shuffle equals false, and we're going to do 1,000 steps. So we're actually going to go through 128 batches, but we're going to do that 1,000 times. And we'll go ahead and run this. And I just ran an update, so it's going to give me some warnings because of that update. And then we're back here and it's still going. To construct pipelines, use TF data module. Not a big problem. We let it go ahead and run all the way through on here. And it takes it just a moment. There we go. There's our 1,000 coming out. As you can see here, here's checkpoints for 1,000, ongoing training, 1,001, global steps. And this is just all the reverse propagation going on. That's what we're doing here. One of the things we didn't cover is we do it in small increments. So it's not all done like one error goes all the way back. You'd only do a part of that error, and each one sends back a little piece, and so you slowly adjust your different weights going all the way back. And then if you're going to train your model, we want to know how it did. So we're going to do model evaluate. And our input function equals, remember our input function up here that we created? Way up here. We're going to take this input function, and instead of the data set that's coming in, we put in the data set here for training. Where's our training? Input train. There we go. df underscore train. Now we're going to go ahead and evaluate, and here it is, get input function test. So we're going to test the data out. Number of epochs 1, we don't need to rerun it more than once. Per batch 128, so on, shuffle, and steps 1,000. So we're going to go ahead and evaluate this. Let's just see how good our test data did, how good our model was programmed on our training data, and how it evaluates on the test. And we can see it going on down here where it's got the evaluating. Graph was finalized. Let me just highlight that. Ongoing model checkpoint, TensorFlow running local init, evaluate 100 out of 1,000, and so on. And once it gets to the end, we get a nice output here. We have an accuracy, in this case, of 0.79 with a baseline of 0.76. So now we've created a model. Let's go ahead and tweak it a little bit. So we have our accuracy up here. What we're going to do is we're going to look at age. And let's just go ahead and create a new square value for age. And the reason we want to look into the square value of age is we know that if you really look through the data, you'll find that as a young person, the age keeps increasing. And as you get close to retirement, it begins to decrease. So we square the value of age. And that's very data specific when we're looking at data. You'll find that any kind of data that has that kind of like uptick and downtick, by squaring it or square rooting it, you can get some very different results. And so we're going to go ahead and square our age. And this is kind of, it's interesting because at this point, even at the beginning of this, we're focused on deep learning and on TensorFlow. But before I would begin even looking at any of this, I would have probably run some kind of heat map or some kind of evaluation in R or sklearn in Python to find out the correlation between different features, to see just how well they correlate to each other. And there certainly are some wonderful tools for that, because sometimes you can just mark off some features and other features you bring in. But for the deep learning, we can see how we can just dump it all in there and let it sort it out itself. And we're going to just write a quick little function here to take the square variable. In this case, we have dft, dfte. And this is our training and your test variable, and the variable age coming in. And we just want to go ahead and create a new under dft, and the new is going to be the variable name, whatever we put in there, which will be age. So let's load this. Here's our functions now loaded. And certainly we could have just done that as a line of code, but you start to get the feeling that when you build these functions, you might use it. You can now use this function if you had a number of different features that had this kind of quality to them. And we have our df train new, so we're going to create a new training and a new test, and it's going to equal the square variable df train or df test, and the variable name is age. Let's just go ahead and run run that. And so now we have our df train new and df test new. And just like we did before, let's just double check the shape of our data and make sure it all matches. And when we look at the output here, really what's important is that each one of these has 16 features in it. We want to make sure we're not getting something weird on there. And our training set has 32,561 rows in it, and this one has just over 16,000 in there. And everything's pretty much the same, except that in our continuous features new, we now have the new column we put in there. So we need to change that. And we have our continuous features new down here, which we're going to load up with our TF feature column numerical. This should all look familiar because we just did this. And so we're going to load that up with the new being the new value in there. And let's go ahead and run that. And we'll create a model, but we'll call it Model 1. And this is the same that we did before, except now we have our continuous features new in here. So here's our new model. In this case, Model 1 instead of model. And we're going to build that model right there. Now we haven't trained it. All we've done is told it where to get the data and how to get the data and what features are coming in. We haven't actually told it everything on the features coming in because we still need to also build our get input function. So where's the input coming from? So we built the model with the features in it, and now we need to go ahead and create our get input function. This is the same as before, but you'll see we now have it with the data set coming in is going to be the same data set up here. And so if we scroll a little bit to the right, we should see the new. And there it is. Sure enough, there's our new on the right. And so let's go ahead and run that. Now we've defined our model. We've defined where the information is coming from. And again, you can go back and review the first part because this is identical that we did before, except now we have new as the column for the age. And we'll go ahead and do our Model 1, and let's go ahead and train it. There's our input function, get input function that we defined up here. df train is going to be the same, and everything else is going to be the same. Let's go ahead and run that. And it should go through here and run the tensor info coming in. And it's going to go through, in this case, what we have, steps 1000, shuffling, so it's going to go randomly, 128 per batch, and then the epochs is automatic. We're not worried about that today. So now we have a trained TensorFlow model. And with our new model, just like we did before, we want to go ahead and evaluate it. So it's the same setup we had before with our same get input function, with our df test new in here coming in. So there's our new data coming in. And this is really common when you're doing these models. You make little tiny tweaks to see if you can improve it. One of the best articles I read recently was you build your model to fail. You want a running model so that you actually have something to compare against. And then you continually tweak it till you get a better accuracy. Now, I don't expect the accuracy necessarily to get better on this because of the way we partition the data. But we can see here we now have an accuracy of 0.76, which is a little bit over the baseline. And it's about what I would have expected it to be kind of the same. The reason is because we split the data at the people making over 50K and those making less. And so the age factor shouldn't be a huge factor. It would be if we were looking at more discrete buckets, like 40 to 50, 50 to 60, 60 to 70 when we create buckets. But in this, I didn't really expect it to go up that much. In fact, we could probably run it a dozen times, which would be very bad data science. And we see we actually had a slightly better one up here, but our baseline accuracy was 0.76. And we come down here, we still see, here's our accuracy baseline, 0.763. That didn't really change. And the accuracy didn't really go up that much. I could hit the run button a few times, and I would probably upbeat the one above. So not a big change, but that's all right. This is how we learn. This is how we go through and figure out what's going to work with our data and what's not. What's going to improve the quality of our data so we have a better prediction and what's not. And we can now go ahead and utilize this model. This is where it gets exciting when you're actually working with somebody or with your clients and you come in and you say, okay, here's my predictions. We're going to create a list and we're going to use Model 1 and we're going to predict. And our input function is get input function, df test new. Again, this probably doesn't make too big of a difference, but we'll go ahead and stick with the new data we created. Number of epochs 1, batch 128. So all this should look pretty familiar, but we're running the prediction. So we're going to load all our predictions into the predictions. And let's go ahead and run that. And you'll see it go through the TensorFlow setup. And so it's running, done running local ops. And then let's just go ahead and print the df test new, iLocation 0, so row 0. And we're going to look at the predictions also for the same location 0. And let's go ahead and run that. And we can see here that we have age 25, work class private. It has all the information coming in for that individual. And then it comes down here and we go ahead and get our prediction. And in this particular instance, there's our label 0. And then we come down here and we see, it takes a little bit for the setup to look up, but there's our array, which also returns a 0. And it has information for us on there, probabilities, logistics on here. So you can see there's all kinds of additional information you can pull from this. And likewise, we could do it for position 3. Let me go ahead and run that. And what's kind of nice about this is you can now see here's label 1, and here's our logistics output. And again, I have to kind of hunt for it a little bit in this particular setup, but here's the output array, and there's our 1. And they match, label 1, 1. So we predicted for the very first one, location 0, that it's going to be a 0 on the label. It's going to make under 50,000. And the individual in 2, working class, private, whatever setup on here, capital gain, capital loss, etc., came up as 1, meaning they're going to make over 50,000. So we covered a lot. I mean, this is the basics, and you can see as you dig deeper, when you look at some of this code, let me just go back up here. We're way back up here at the very top, a little too far overshot. As we start working in here, we have 1, defining your features. And at this point, we didn't show this, but I would probably use either Python or R to show a relationship correlation, because they have some really easy packages in there to pull that up. So you can see what features are really connected and how they're connected. And then we showed you different features. Like we have ones that are integers, and then we have ones like sex that are objects. You're 0 or 1, you're male or female. You're same thing with race. Probably have just maybe 16 different races listed there. Ethnicities, things like that. Native country, again, that's, you don't have like infinite number of native countries. You just have a handful. So we look at this. We have our features. We looked at that. We have our continuous features like age, which is a number, or in this case, an integer, and education number, how many years, and so on, along with your race, your sex, your relationship, which are just very abbreviated categorical data. So we looked at that. We went in there and we showed you how to, where was it? Here we go. We go back up here. So we create our model. The model knows what categories are coming in. That's really important. And this is probably one of the more complicated parts of this is our input function. And this input function is so important. So I want to just rehash the input function for that reason. This lets us know how we're pulling the data. It lets us know if we're going to go through all the data 20 times, or we're just going to let TensorFlow itself keep going until the training model reaches a point. That point is based on what they call bias. You can become biased on your training data. And so when it hits a certain point where it becomes overly biased to just that data, then it doesn't really work really good in the outside world. You start losing. You want to keep it generic, but as close as possible to the right answer. So generic answers for a huge amount of data. And then we have our batch size. Are we going to shuffle it, which we did. And then also our estimator inputs. So you have your estimator function here. And then of course where the actual data is coming from. So you can see all this is in that get input function. That's where a lot of the work comes in putting this together. And then we train our model. That's pretty straightforward. Once you have your input function and all your setup, training the model is quick. And then we go ahead and evaluate, and then we can go ahead and create a predict, and then look at our predictions and how they work on individuals. So it gives you a whole roundabout setup on here and how this is set up and how it's working. Certainly there are a lot more things you can do with TensorFlow. This is the basic TensorFlow, and it's always developing, so it's exciting. This is going to be one of the most exciting fields right now because it is really in an infant stage and just exploding in the market.
Mathematics for machine learning. My name is Richard Kirshner with the Simplilearn team. That's Get Certified, Get Ahead. We're going to cover mathematics for machine learning. So today's agenda is going to cover data and its types. Then we're going to dive into linear algebra and its concepts, calculus, statistics for machine learning, probability for machine learning, hands-on demos. And of course, thrown in there in the middle is going to be your matrices and a few other things to go along with all this. Data and its types. Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers. And then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So we talk about types of data. We have, in our types of data, we have a qualitative, categorical. You think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range. If you have 10,000 to 20,000, number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true-false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative, numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually, a lot of times discrete could be put into true-false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's where we're talking about a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle, AB, is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart, or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these, because these are such primary. This is what we're here to talk about, is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have 2 variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept. Which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. I kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had a reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is A row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, smaller case a for the top row. Or, I mean, you can see where they can go all kinds of different directions as far as the value. You just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have 2 matrices of 2 by 2, and you just add each individual number in that matrix. And then when you get to the bottom, you have, in this case, the solution is 12, 10 plus 2 is 12, 5 plus 3 is 8, and so on. And the same thing with subtraction. Now again, you're counting matrices. You want to check your dimensions of the matrix. The shape. You'll see shape come up a lot in programming. So when we're talking about dimensions, we're talking about the shape. If the 2 shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5. 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at two variable. So this is a two variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3. 1 times 3 plus 4 times 5. 6 times 2 plus 3 times 3. 6 times 3 plus 3 times 5. And it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of two matrices. Okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind, because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one. And it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to eigenvectors vectors and eigenvalues. values. Eigenvectors, vectors, the vectors that don't change their span while transformation, and eigenvalues, the scalar values that are associated to the vectors. Conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your eigenvector. 2 is the eigenvalue. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your eigenvalue. And you can see here, vector after line transition, we have 3a. A is the eigenvector, 3 is the eigenvalue. So A doesn't change. That's whatever we started with. That's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the eigenvalues. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook, and we'll create a new notebook called linear algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create two different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our two arrays, 10, 15, 29. And I went ahead and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as A plus B, I can also do A plus B dot T. And you're going to see that that will come out the same, the 30, 24, whether I transpose A and B or transpose them both at the end. And likewise, we can very easily subtract two vectors. I can go A minus B. And we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down scalar so you can remember that. And what we're talking about here is I have this array here, U, and if I go A times U, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a two-dimensional vectors. It is the equivalent to matrix multiplication. And remember, we were talking about matrix multiplication, where it is the, well, let's walk through it. We'll go ahead and start by defining two NumPy arrays. We'll have 10, 20, 25, 6, or our U and our V. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of U comma V. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here. There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma n means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is a plus b, and you should already guess because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do a minus b and do our matrix subtraction. And we look at this, we have what? 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is, of course, 10. 10 minus 8 is 2. 4 minus 46 is minus 42, and so forth. So same as the subtraction as before, we just call it matrix subtraction. It's identical. Now, if you remember up here, we had scalar addition, where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply, if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a NumPy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that, you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication, and you can mix and match. When you get into really complicated back-end stuff, this becomes more common because you've got layers upon layers of data, and so you'll end up with a matrix and a set of vector matrices you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the scikit looking at sklearn, where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times, you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the scikit. And if we can do, up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this where we have the 2 matrices, you can see we have a very complicated array that, of course, comes out on there for our dot. And just to reiterate it, we have our transpose of matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers, and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you can be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1, depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here, is that you create this preset matrix, and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do, to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind, 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then, of course, it equals the dot, A inverse of A with an identity shape of A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we go ahead and have here's our array. We'll go ahead and run this. And you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down, 2, 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably really is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up or at least remember where to look it up. We took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So it helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic. Traffic opens up, and I accelerate again up to the speed limit, and maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating, and if I hit the brakes, it'd go the other way. So the rate of change of speed with respect of time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to 0 in order to approximate the acceleration. So the idea is that instead of, if you ever took a basic calculus class, they would draw bars down here and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. Looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from c to d and a to b of f of x of y dx dy equals the sum of a to b, sum of c to d of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals a change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? Speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I mean, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick. Gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. In On the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is, and this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Sidekick and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff, because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current X. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. We're just saying if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's so we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot in with the sklearn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits in built-in code. And so from, we'll just do, it's actually docs.scipy.org, and we're looking at the scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught, there's your start value. So your function, your start value, there's all kinds of things that come in here that we can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. What this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly if you're working in a domain that deals with viruses and T cells and how does, where does that come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you got to be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup or our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. Let's say we're studying economics of an area. We know pretty much that based on their culture and where they came from, they might need to be separated. And so And when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call her expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups they're in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group, or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say, this is what it is, then everybody assumes that's what it is for everybody. And so you got to be very careful of that, and it's a very unethical thing to kind of do. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are so many different terms in statistics to break it up. So we're talking about a particular setup. So we're talking about descriptive and inferential statistics. The base of the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we're going to take that from the small population to a large population. So if you're working with a drug company, you might look at the data and say, these people were helped by this drug. They did 80% better as far as their health, or 80% better survival rate than the people who did not have the drug. So we can infer that that drug will work in the greater populace and will help people. So that's where you get your inferential. So we are predicting how it's going to affect the greater population. So descriptive statistics. It is used to describe the basic features of data and form the basis of quantitative analysis of data. So we have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your interquartile range, your variance, and your standard deviation. And we're going to look at all these a little deeper here in a second. But one of them you can think of is how the data differences, what's the max, min range, all that stuff is your spread. And anything that's just a single number is usually your central tendencies, measure of central tendencies. So we talk about the mean. It is the average of the set of values considered. What is the average outcome of whatever's going on? And then your median separates the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it so that the average is much higher than if you took those outliers out, where the median would, by separating the high from the low, might give you a much lower number. You might look at it and say, oh, that's odd. Why is the average so much higher than the median? Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. You might find that the most common income, like in the U.S., was at one point $24,000 a year, where the average was closer to $80,000. And it's like, wow, what a difference. Well, there's some people who have a lot of money, and so that skews that way up. So the average person is not making that kind of money. And then you look at the median income, and you're like, well, the median income is a little bit closer to the average. So it does create a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. And we look at the measure of central tendencies. The mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, if we have 0 through 10, and we take half the numbers and put them on one side of the line, half the numbers on the other side of the line, we end up with 5 in the middle. And then the mode. What mark was scored by most of the students in a test? In a simple case where most people scored like an 82% and got certain problems wrong, easy to figure out. Not so easy when you have different areas where like you have like the, let's go back to economy. A little bit more difficult to calculate if you have a large group that makes 30,000 and a slightly bigger group that makes 26,000. So what do you put down for the mode? Certainly there's a number of ways to calculate that, and there's actually different variations depending on what you're doing. So now we're looking at a measure of spread, range. What's the difference between the highest and the lowest value? First thing you want to look at, it's we had everybody in the test scored between 60 and 100%. Somebody got 100%, or maybe 60 to 90%. It was so hard that a lot of people could not get 100%. Then you have your interquartile range. Quartiles divide a rank-ordered data set into 4 equal parts. Very common thing to do as part of all the basic packages, whether you're working in data frames with pandas, whether you're working in Scala, whether you're working in R. You'll see this come up where they have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the standard deviation. It is the measure of the variance or the dispersion of a set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed. And then based on the error, I might graph the standard deviation and the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread. Marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is. And then there's the first quarter, the second quarter, and the third quarter based on splitting it apart by those values. And to understand the variance and standard deviation, we first need to find out the mean. So here's our calculating the average there. We end up at approximately 66 for the average. And then we look at that and the variance. Once we know the means, we can do equals the marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have like if you're putting all this stuff together, you end up with an error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. And if you were looking at a predictable model, you would be looking at the deviation based on the error. How much error does it have? And that's, again, really important to know. If your prediction is predicting something, what's the chance of it being way off or just a little bit off? Now that we've looked at the tools, as far as some of the basics for doing your statistics and what we're talking about, let's go ahead and pull up a little demo and show you what that looks like in Python code, so you can get some little hands-on here. For that, let's go back into our Jupyter Notebook in Python. Now, almost all of this you can do in NumPy. Last time we worked in NumPy. This time we're going to go ahead and use pandas. And if you remember from pandas on here, this is basically a data frame, rows, columns. Let's just go ahead and do a print df.head and run that. And you can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all those hand calculations and add everything together and divide by the total, we can do something very simple on this, like use the command mean in pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. And we go ahead and print this out, and you can see that the average income on here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And the median is very similar, except it actually is just median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And then the median, whoops, let's put a median here, df salary, that way it displays a little better. We can see the median is 54,000. So the halfway mark is significantly below the average. Why? Because we have somebody in here who makes 189,000. Darn you, Rosie, for throwing off our numbers. But that's something you'd want to notice. This is the difference between these is huge, and so is what is the meaning behind that when you're studying a populace and looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make in this little tiny sample. And so we'll go ahead and do the mode. And you can see here with the mode, it's at 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000. So half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min will pull up your minimum, and then dot max pulls up the maximum. Pretty straightforward on as far as translating it and knowing what your lowest value and what your highest value is here, which you'll use to generate like a spread later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute the mode. Although the standard one's pretty good. We can of course do the range, which is your max minus your min. So now we have a range of 149,000 between the upper end and the lower end. And you might want to be looking up the individual values on all of these. But it turns out there is a describe feature in pandas. And so in pandas, we can actually do df salary describe. And if we do this, you can see we have that there's 7 setups. Here's our mean, our standard deviation, which we didn't compute yet, which should just be a .std. And you got to be a little careful because when it computes it, it looks for axes and things like that. We have our minimum value, and here's our quartiles, our maximum value, and then of course the name salary. So these are the basic statistics. You can pull them up and just describe. This is a dictionary, so I could actually do something like in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically. But just in case, I always put it in there. Import matplot library, pyplot is PLT. That's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary df salary, salary.plot history title, salary distribution, color gray, plot AXV line, salary, the mean value. So we're going to take the mean value. Color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here we are taking on our plot. So here's the data. Here's our data frame printed out so you can see it with the salaries. And we're looking at the salary distribution. And just look at this, the way the salary is distributed. You have our, in this case we did, let's see, we had red for the median. We have violet for our average or mean. And you can just see how it really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average, and here's the median. And so as you look at this, you can say, wow, based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, what the average salary is. So some of the things you want to take away in addition to this is that it's very easy to plot an AXV line. These are these up and down lines for your markers. And as you display the data, I mean, you can add all kinds of things to this and get really complicated. Keeping it simple is pretty straightforward. I look at this and I can see we have a major outlier out here. We can definitely do a histogram and stuff like that. But picture's worth 1,000 words. What you really want to make sure you take away is that we can do a basic describe, which pulls all this information out, and we can print any of the individual information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also do describe mean. So if you're doing a lot of statistics, being able to, it doesn't have the print on there, so it's only going to print the last one, which happens to be the mean. You can very easily reference any one of these. And then you can also, if you're doing something a little bit more complicated and you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture of movie ratings, and if we took this group of people and said, hey, how many people like the movie, dislike it, can't say, and then you ask just a random person who comes out of the movie who hasn't been in this study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or a 10 or 11% chance of can't say. So that's real basics of what we're talking about, is you're going to infer that the next person is going to follow these statistics. So let's look at point estimation. It is a process of finding an approximate value for a population's parameter, like mean or average, from random samples of the population. Let's take an example of testing vaccines for COVID-19. Vaccines and flu bugs, all of that, it's a pretty big thing of how do you test these out and make sure they're going to work on the populace. A group of people are chosen from the population. Medical trials are performed. Results are generalized for the whole population. So here's our small group up here where we've selected them. We run medical trials on them, and then the results work for the population. Nice diagram with the arrows going back and forth and the very scary COVID virus in the middle of one. And let's take a look at the applications of inferential statistics. Very central is what they call hypotheses testing, and the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis, assumption, by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis. We execute the test, and we make a decision. And so when you're talking about a hypothesis, you're usually trying to disprove it. If you can't disprove it and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who are given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people: Nick, Rob, Imlia, and Summer. Now Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e. whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e. his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of Rob not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do work. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very high probability when on day 12 he still hasn't gotten the job cleaning the room. So we come up to our important terminologies. We have null hypothesis, a general statement that states that there is no relationship between 2 measured phenomena or no association among the groups. Alternative hypothesis. Contrary to the null hypothesis, it states whenever something is happening, a new theory is preferred instead of an old one. And so the 2 hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it, it's about proving that the things have no correlation. Null hypothesis says these 2 have 0 relation to each other. Where the alternative hypothesis says, hey, we found a relation, this is what it is. We have p-value. The p-value is a probability of finding the observed or more extreme results when the null hypothesis of a study question is true. And the t-value. It is simply the calculated difference represented in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you can look at the t-value as being specific to the test you're doing, where the p-value is derived from your t-value, and you're looking for what they call the 5% or the 0.05, showing that it has a high correlation. So digging in deeper, let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. And this is a good one because the null value here isn't that you don't have any drug. The null value here is that it's better than the existing drug. The new drug doesn't lower the blood pressure more than the existing drug. Now, if we get that, that says our null hypothesis is correct. There is no correlation, and the new drug is not doing its job. The alternative hypothesis, the new drug does significantly lower the blood pressure more than the existing drug. Yay, we got a new drug out there. And that's our alternative hypothesis, or the H1 or HA. And we look at the p-value, results from the evidence like medical trials showing positive results which will reject the null hypothesis. And again, they're looking for a 0.05 or 5%. and the t-value comparing all the positive test results and finding means of different samples in order to test hypothesis. So this is specific to the test. What percentage of increase did they have? And this leads us to the confidence intervals. A confidence interval is a range of values we are sure our true values of observations lie in. Let's say you asked a dog owner around you and asked them, how many cans of food do you buy for your per year for your dog? Through calculations, you got to know that on an average, around 95% of the people bought around 200 to 300 cans of food. Hence, we can say that we have a confidence interval of 300, where 95% of our values lie in that data spread. And the graph really helps a lot, so you can start seeing what you're looking at here, where you have the 95%. You have your peak. In this case, it's a normal distribution, so you have the nice bell curve equal on both sides. It's not asymmetrical. And 95% of all the values lie within a very small range, and then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability is a measure of the likelihood of an event to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of its occurrence. So any event cannot be predicted with total certainty. It can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather prediction, stock prediction. If you've studied physics and chaos theory, even the location of the chair you're sitting on has a probability that it might move 3 feet over. Granted, that probability is 1 in I think we calculated it as under 1 in trillions upon trillions. So the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of a random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each. There's how often you're going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this is one of the cases, is rolling 2 dice and gambling. There's also a binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case, and let's consider the game of football between 2 clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series. So we look at the total games, and we're looking at 5 different games or matches. Let's say that the winning chance for Barcelona is 75% or 0.75. That means that each game, they have a 75% chance that they're going to win that game. And losing chances are 25% or 0.25. clearly 0.75 plus 0.25 equals 1. So that accounts for 100% of the game. Probability for getting k wins in n matches is calculated. And we're talking like, so if you have 5 games and you want to know if I play, how many wins in those 5 games should I get? What's the percentage on those? And the probability for getting k wins in n matches is calculated by p x equals k equals nck p to the k q to the n minus k. Here, p is the probability of success and q is the probability of failure. And so we can do total games of n equals 5, where k equals 0, 1, 2, 3, 4, 5. P, which is the chance of winning, is 0.75. Q, the chance of losing, equals 1 minus P, which equals 1 minus 0.075, which equals 0.25. The probability that Barcelona will lose all of the matches can then just plug in the numbers, and we end up with a 0.0009765,625. So a very small chance they're going to lose all their matches. And we can plug in the value for 2 matches. Probability that Barcelona will win at least 2 matches is 0.0878. And of course we can go on to the probability that Barcelona will win 3 matches, the 0.26, and of course 4 matches, and so on. And it's always nice to take this information and let's find the cumulative discrete probabilities for each of the outcomes. Where Barcelona has won 3 or more matches, x equals 3, x equals 4, x equals 5. And we end up with the p equals 0.264 plus 0.395 plus 237, which equals 0.89. In reality, the probability of Barcelona winning the series is much higher than 0.75. And it's always nice to put out a nice graph so you can actually see the number of wins to the probability and how that pans out with our binomial case. Continuing in our important terminology. Location. The location of the center of the graph depends on the mean value. And this is some very important things. So much of the data we look at, and when you start looking at probabilities, almost always has a normalized look, like the graph in the middle. But you do have left skewed, where the data is skewed off to the left, and you have more stuff happening off to the left, and you have right skewed data. And so when this comes up and these probabilities come up where they're skewed, it's really important to take a closer look at that. Mostly you end up with a normalized set of data, but you got to also be aware that sometimes it's a skewed data. And then the height. Height of the slope inversely depends upon the standard deviation. So you can see down here the standard deviation is really large. It kind of squishes it out. And if the standard deviation is small, then most of your data is going to hit right there in the middle. You're going to have a nice peak. And so being aware of this, that you might have a probability that fits certain data, but it has a lot of outliers. So if you have a really high standard deviation, if you're doing stock market analysis, this means your predictions are probably not going to make you much money. Where if you have a very small deviation, you might be right on target and set to become a millionaire. Which leads us to the z-score. Z-score tells you how far from the mean a data point is. It is measured in terms of standard deviations from the mean. Around 68% of the results are found between 1 standard deviation. Around 95% of the results are found between 2 standard deviations. And you read the symbols. Of course, they love to throw some Greek letters in there. We have mu minus 2 sigma. Mu is just a quick way. It's a kind of funky U. It just means the mean. And then the sigma is the standard deviation, and that's the O with the little arrow off to the right, or the little waggly tail going up, the O with the line on it. So mu minus 2 sigma is your 95% of the results are found between 2 standard deviations. Central limit theorem. This goes back to the skew. If you remember, we were looking at the skew values on this previous slide. Have left skewed, normalized, and right skewed. When we're talking about it being skewed or not skewed, the distribution of the sample means will be approximately normally distributed, evenly distributed, not skewed, if you take large random samples from the population with the mean, mu, and the standard deviation, sigma, with replacement. And you can see here, of course, we have our mu minus 2 sigma and the spread down here, the mean, the median, and the mode. And so when you're talking about very large populations, these numbers should come together and you shouldn't have a skewed value. If you do, that's a flag that something's wrong. That's why this is so important to be aware of what's going on with your data, where your samples are coming from, and the math behind it. And if you're going to do all this, we got to jump into conditional probability. The conditional probability of an event A is a probability that the event will occur given the knowledge that an event B has already occurred. And you'll see this as Bayes' theorem, B-A-Y-E-S, Bayes. And this is read, I mean, you have these funky looking little P brackets, A, B. This is the probability of A being true while B is already true. And you have the probability of B being true when A is already true, so P, B of A. The probability of A being true divided by the probability of B being true. And we talk about Bayes' theorem, which occurred back in the 1800s when he discovered this. This is such an important formula. And it's not, if you actually do the math, you could just kind of do xy equals jk, and then you divide them out, and you're going to see the same math. But it works with probabilities, which makes it really nice. And so if you have you might have 8 or 9 different studies going on in different areas. Different people have done the studies, they brought them together. If we look at today's COVID virus, the virus spread, certainly the studies done in China versus the studies the way they're done in the US, that data is different in each of those studies. But if you can find a place where it overlaps, where they're studying the same thing together, you can then compute the changes that you need to make in one study to make them equal. And this is also true if you have a study of one group and you want to find out more about it. So this formula is very powerful, and it really has to do with the data collection part of the math and data science, and understanding where your data is coming from and how you're going to combine different studies in different groups. And we'll go ahead and go into a use case. Let's find out the chance of a person getting lung disease due to smoking. And this is kind of interesting the way they word this. Let's say that according to medical report provided by the hospital, states that around 10% of all patients they treated suffered lung disease. So we have kind of a generic medical report. They further found out by a survey that 15% of the patients that visit them smoke. So we have 10% that are lung disease, and 15% of the patients smoke. And finally, 5% of the people continued smoke even when they had lung disease. Not the brightest choice, but it is an addiction, so it can be really difficult to kick. And so we can look at the probability of A, prior probability of 10% people having lung disease. And then probability B, probability that a patient smokes is 15%. And the probability of B, if B then A, the probability of a patient smokes even though they have lung disease is 5%. And probability of A is B, probability that the patient will have lung disease if they smoke. And then when you put the formulas together, you get a nice solution here. You get the probability of A of B, probability that the patient will have lung disease if they smoke. And you can just plug the numbers right in, and we get a 3.33% chance. Hence, there is a 3.33% chance that a person who smokes will get a lung disease. So we're going to pull up a little Python code. Always my favorite. Roll up the sleeves. Keep in mind, we're going to be doing this kind of like the back-end way, so that you can see what's going on. And then later on, we're going to create, we'll get into another demo which shows you some of the tools that are already pre-built for this. Let's start by creating a set. So we're going to create a set with curly braces. This means that our set has only unique values. So you have a list, you have your tuples, which can never change, and then you have, in this case, the set. So 4, 7, you can't create a 4, 7, comma 4. It'll delete the 4 out. So it's only unique values. And if you use dictionaries, quick reminder, this should look familiar because it is a dictionary where you have a value, and that value is assigned to, or that key is assigned to a value. So you could have a key value set up as a dictionary. So it's like a dictionary without the value. It's just the keys, and they all have to be unique. And if we run this, we have a set of 4, 7. We can also take a list, a regular setup, and I'm going to go ahead and just throw in another number in here, 4, and run it. And you can see here, if I take my list 1, 2, 3, 4, 4, and I convert it to a set, and here it is, my set from list equals set, my list. The result is 1, 2, 3, 4, so it just deletes that last 4 right out of there. And with the sets, you can also go in there and print, here is my set, 3 is in the set, and then if you do 3 in my set, that's going to be a logic function. And 1 in my set, 6 is not in the set, and so forth. If we run this, we get 3 is in the set true, 1 is in the set false, because 3, 5, 7 is another 1. 6 is in the set, 6 is not in the set, so not in my set. You can also use this with a list. We could have just used 3, 5, 7, and it would have the same response on there. Is 3 in? Usually you do if 3 is in, but 3 in my set still works on just a regular list. And we'll go ahead and do a little iteration. We're going to do kind of the dice one. Remember 1, 2, 3, 4, 5, 6. And so we're going to bring in an iteration tool and import product as product. And I'll show you what that means in just a second. So we have our 2 dice. We have dice A, and it's going to be a set of values. You can only have 1 value for each one. That's why they put it in a set. And if you remember from range, it is up to 7. So this is going to be 1, 2, 3, 4, 5, 6. It will not include the 7. And the same thing for our dice B. And then what we're going to do is we're going to create a list, which is the product of A and B. So what's A plus B? And if we go ahead and run this, it'll print that out, and you'll see, in this case, when they say product, because it's an iteration tool, we're talking about creating a tuple of the 2. So we've now created a tuple of all possible outcomes of the dice, where dice A is 1, 2, 3, 1 to 6, and dice B is 1 to 6. And you can see 1 to 1, 1 to 2, 1 to 3, and so forth. And you remember we had a slide on this earlier, where we talked about all the different outcomes of a dice. We can play around with this a little bit. We can do in dice equals 2, dice faces 1, 2, 3, 4, 5, 6. Another way of doing what we did before, and then we can create an event space where we have a set, which is the product of the dice faces, repeat equals in dice. And we'll go ahead and just run this. And you can see here, it just again puts it through all the different possible variables we can have. And then if we wanted to take the same set on here and print them all out like we had before, we can just go through for outcome and event space, outcome and equals. So the event space is creating a sequence. And as you can see here, when we print it out, it stacks them versus going through and putting them in a nice line. And we'll go ahead and do something. Let's go print. Since we have the end printing with a comma, that just means it's not going to hit the return going down to the next line. And we'll go ahead and do the length of our event space. That'll be an important variable we're going to want to know in a minute. And of course, if I get carried away with my typing of length, we'll print it twice and it'll give me an error. So we have 36 different possible variations here. And we might want to calculate something like, what about the multiple of 3? What if we want to have the probability of the multiple of 3 in our setup? And so we can put together the code for the outcome and event space of x, y equals outcome. If x plus y, remainder 3, so we're going to divide by 3 and look at the remainder, and it equals 0, then it's a favorable outcome. And we're going to pop that outcome on the end there. And we'll turn it into a set. So the favorable outcome equals a set. Not necessary because we know it's not going to be repeating itself, but just in case, we'll go ahead and do that. And if we want to print out the outcome, we can go ahead and see what that looks like. And you can see here, these are all multiples of 3. 1 plus 2 is 3, 5 plus 4 is 9, which divided by 3 is 3, and so forth. And just like we looked up the length of the one before, let's go ahead and print the length of our F outcome so we can see what that looks like. There we go. And of course I did forget to add the print in the middle because we're looping through and putting an end on the setup on there, so we're going to put the print in there. And if I run this, you can see we end up with 12. So we have 36 total options. We have 12 that are multiple, that add up to a multiple of 3. And we can easily compute the probability of this by simply taking the length of our favorable outcome over the length of the event space. And if we print it out, let me put that in there, probability, last line, so we can just type it in, we end up with a 0.3333 chance. And it's roughly a third. And we might want to make this look nice, so let's go ahead and put in another line there. The probability of getting the sum, which is a multiple of 3, is 0.3333. We can compute the same thing for 5 dice. And if we do this for 5 dice and go ahead and run it, you can see we just have a huge amount of choices. So it just goes on and on down here. And we can look at the length of the event space. And we have over 7,776 choices. That's a lot of choices. And if we want to ask the question like we did above, what is the sum, where the sum is a multiple of 5 but not a multiple of 3, we can go through all of these different options, and then you can see here D1, D2, D3, D4, D5 equals the outcome. And if you add these all together and the division by 5 does not have a remainder of 0, but the remainder is also of a division by 3 is not equal to 0. So the multiple of 5 is equal to 0, but the multiple of 3 is not. We can just append that on here, and then we can look at that favorable outcome. We'll go ahead and set that, and we'll just take a look at this. What's our length of our favorable outcome? It's always good to see what we're working with. And so we have 904 out of 776. And then, of course, we can just do a simple division to get the probability on here. What's the probability that we're going to roll a multiple of 5 when you add them together, but not a multiple of 3? And so we're just going to divide those two numbers, and you can see here we get 0.116255, or 11.62%. And so you can really have a nice visual that this is not really complicated math right here on probabilities. It's just how many options do you have, and how many of those are you possibly going to be able to come up with the solution you're looking for. And this leads us to a confusion matrix. A confusion matrix is a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. And so you'll see on the left we have the predicted and the actual. And we have a negative, false negative, positive, true positive, and then we have false positive and true negative. And you can think of this as your predicted model. What does that mean? That means if you divided your data and you used 2/3 of it to create the model, you might then test it against an actual case for the last third to see how well it comes out. How many times was it true positive versus false positive? It gave a false positive response. And you can imagine in medical situations, this is a pretty big deal. You don't want to give a false positive. So you might adjust your model accordingly so you don't have a false positive. Say with a COVID virus test, it'd be better to have a false negative and they go back and get retested than to have 30% false positives where then the test is pretty much invalid. So in a use case like cancer prediction, let's consider an example where a cancer prediction model is put to the test for its accuracy and precision. Actual result of a person's medical report is compared with the prediction made by the machine learning model. And so you can see here, here's our actual predicted, whether they have cancer or not. You know, cancer, a big one. You don't want to have a false positive. I mean, a false negative. In other words, you don't want to have it tell you that you don't have cancer when you do. So that would be something you'd really be looking for in this particular domain. You don't want a false negative. And this is, again, you know, you've created a model. You have hundreds of people or thousands of pieces of data that come in. There's a real famous case study where they have the imagery and all the measurements they take, and there's about 36 different measurements they take. And then if you run a basic model, you want to know just how accurate it is. How many negative results do you have that are either telling people they have cancer that don't, or telling people that don't have cancer that they do. And then we can take these numbers and we can feed them into our accuracy, our precision, and our recall. So accuracy, precision, and recall. Accuracy metric to measure how accurately the results are predicted. And this is your total true, where you got the right results, you add them together, the true positive, the true negative, over all the results. So what percentage of them were accurate versus what were wrong. When we talk about precision, is a metric to measure how many of the correctly predicted cases are actually turned out to be positive. So we have a precision on true positive. Again, if you're talking about like COVID testing with the viruses, you really want this to be a high number. You want this that to be the center point, where you might have the opposite if you're dealing with cancer, where you want no false negatives. So this is your metric on here. Precision is your test positive, true positive plus false positive. And then your recall, how many of the actual positive cases we were able to predict quickly with our model. So test positive is the test positive plus the false negative on there. And we'll want to go ahead and do a demo on the naive Bayes classifier. Before I get too far into naive Bayes classifier, because we're going to pull it from the sklearn or the scikit, let's go ahead. Kind of an interesting page here for classifiers. When you go into the sklearn kit, there's a lot of ways to do classification. And I'll just zoom up in here so you can see some of the titles. There's everything from the nearest neighbor, linear, but we're going to be focusing on the naive Bayes over here. And this is just a sample data set that they put together, and you can see how some of these have a very different output. The naive Bayes, remember, is set up as probably the most simplified calculator or set of predictions out there. And so what we've been talking about with the true false and stuff like that, where there's a belief that there is a independent assumption between the features, where the features are very assumed to have some kind of connection, then we can go ahead and use that for the prediction. And so that's what we're using as a naive Bayes classifier versus many of the other classifiers that are out there. For this, we're going to use the social network ads. It's a little data set on here. And let me go ahead and just open that up, the file. Here we go. It has user ID, gender, age, estimated salary, purchased. And so we have, you can see the user ID, male, 19, estimated salary, 19,000, and purchased 0. So it's either going to make a purchase or not. So look at that last one, 0, 1. We should be thinking of binomials. We should be thinking of simple naive Bayes classifier kind of setup. So if we close this out, we're going to go ahead and import our NumPy as NP. We're going to nice to have a good visual of our data, so we'll put in our matplot library. Here's our pandas, our data frame. And then we're going to go ahead and import the data set. And the data set's going to be, we're going to read it from the social network ads.csv. Then we're going to print the head just so you can see it again, even though I showed you it in the file. And x equals the data set iLocation, 2, 3 values, and y is going to be the 4, column 4. Let me just run this so it's a little easier to go over that. You can see right here we're going to be looking at 0, 1, 2 is age and estimated salary, so 2, 3. And that's what iLocation just means, that we're looking at the number versus a regular location. Regular location, you'd actually say age and estimated salary. And then column 4 is, did they make a purchase? They purchased something. So those are the three columns we're going to be looking at when we do this. And we've gone ahead and imported these and imported the data. So now our data set is all set with this information in it. And we'll need to go ahead and split the data up. So we need from the sklearn model selection, we can import train test split. This does a nice job. We can set the random state so it randomly picks the data. And we're just going to take 25% of it's going to go into the test, our X test and our Y test, and the 75% will go to X train and Y train. And that way, once we create our model, we can then have data to see just how accurate or how well it has performed with our prediction. The next step in pre-processing our data is to go ahead and do feature scaling. Now, a lot of this will start to look familiar. If you've done a number of the other modules and setup, you should start noticing that we bring in our data, we take a look at what we're working with, we go ahead and split it up into training and testing. In this case, we're going to go ahead and scale it. Scale it means we're putting it between a value of -1 and 1, or someplace in the middle ground there. This way, if you have any huge you don't have this huge setup. If we go back up to here where salary is 20,000 versus age 35. Well, there's a good chance with a lot of the back-end math that 20,000 will skew the results and the estimated salary will have a higher impact than the age, instead of balancing them out and letting the calculations weigh them properly. And finally, we get to actually create our naive Bayes model. And then we're going to go ahead and import the Gaussian naive Bayes. And the Gaussian is the most basic one. That's what we're looking at now. It turns out, though, if you go to the sklearn kit, they have a number of different ones you can pull in there. There's Bernoulli, I've never used that one, categorical, complement, and here's our Gaussian. So there's a number of different options you can look at. Gaussian, when you come to the naive Bayes, is the most commonly used. So we're talking about the naive Bayes. That's usually what people are talking about when they're pulling this in. And one of the nice things about the Gaussian, if you go to their website, to sklearn, the naive Bayes Gaussian, there's a lot of cool features. One of them is you can do partial fit on here. That means if you have a huge amount of data, you don't have to process it all at once. You can batch it into the Gaussian NB model, and there's many other different things you can do with it as far as fitting the data and how you manipulate it. We're just doing the basics, so we're going to go ahead and create our classifier. We're going to equal the Gaussian NB, and then we're going to do a fit. We're going to fit our training data and our training solution, so X train, Y train. And we'll go ahead and run this. It's going to tell us that it ran the code right there. And now we have our trained classifier model. So the next step is we need to go ahead and run a prediction. We're going to do our Y predict equals the classifier.predict X test. So here we fit the data, and now we're going to go ahead and predict. And now we get to our confusion matrix. So from the sklearn metrics, you can import your confusion matrix. Just as saves you from doing all the simple math, it does it all for you. And then we'll go ahead and create our confusion metrics with the Y test and the Y predict. So we have our actual and we have our predicted value. And you can see from here, this is the chart we looked at. Here's predicted, so true positive, false negative, true negative. And if we go ahead and run this, there we have it, 65, 3, 7, 25. And in this particular prediction, we had 65 were predicted the truth as far as a purchase. They're going to make a purchase, and we guessed 3 wrong. And then we had 25 we predicted would not purchase, and 7 of them did. So there's our confusion matrix. At this point, if you were with your shareholders or a board meeting, you would start to hear some snoozing if they were looking at the numbers. And you say, hey, here's my confusion matrix. So let's go ahead and visualize the results. We're going to pull from the matplot library colors, import listed color map. And this is actually, my machine's going to throw an error because this is being because of the way the setup is. I have a newer version on here than when they put together the demo. And we need our X set and our Y set, which is our X train and Y train. And then we'll create our X1, X2, and we'll put that into a grid. And we set our X set minimum stop and our X set max stop. And if you come all the way over here, we're going to step 0.01. This is going to give us a nice line, is what that's doing. And then we're going to plot the contour, plot the X limit, plot the Y limit, and put the scatter plot in there. Now let's go ahead and run this. To be honest, when I'm doing these graphs, there's so many different ways to do that. There's so many different ways to put this code together. To show you what we're doing, it's a lot easier to pull up the graph and then go back up and explain it. So the first thing we want to note here when we're looking at the data is this is the training set. And so we have those who didn't make a purchase. We've drawn a nice area for that. That's defined by the naive Bayes setup. And then we have those who did make a purchase, the green. And you can see that some of the green dots fall into the red area and some of the red dots fall into the green. So even our training set isn't going to be 100%. We couldn't do that. And so when we're looking at our different data coming down, we can kind of arrange our X1, X2 so we have a nice plot going on, and then we're going to create the contour. That's that nice line that's drawn down the middle on here with the red-green. That's what this is doing right here with the reshape. And notice that we had to do the dot T. If you remember from NumPy, if you did the NumPy module, you end up with pairs, X1, X2, X1, X2, next row, and so forth. You have to flip it so it's all one row. You have all your X1s and all your X2s. So this is what we're kind of looking for right here on this setup. And then the scatter plot is, of course, your scattered data across there. We're just going through all the points. That puts these nice little dots onto our setup on here. And we have our estimated salary and our age. And then, of course, the dots are, did they make a purchase or not? And just a quick note, this is kind of funny. You can see up here where it says X set, Y set equals X train, Y train, which seems kind of a little weird to do. This is because this is probably originally a definition. So it's its own module that could be called over and over again. And which is really a good way to do it, because the next thing we're going to want to do is do the exact same thing, where we're going to visualize the test set results. That way we can see what happened with our test group, our 25%. And you can see down here we have the test set, and if you look at the two graphs next to each other, this one obviously has 75% of the data, so it's going to show a lot more. This is only 25% of the data. You can see that there's a number that are kind of on the edge as to whether they could guess by age and income they're going to make a purchase or not. But that said, it still is pretty clear. It's pretty good as far as how much the estimate is and how good it does. Now, graphs are really effective for showing people what's going on, but you also need to have the numbers. And so we're going to do from sklearn, we're going to import metrics, and then we're going to print our metrics classification report from the y-test and the y-predict. And you can see here we have precision. Precision of zeros is 90. There's our recall, 0.96. We have an F1 score and a support. And we have our precision, the recall on getting it right. And then we can do our accuracy, the macro average, and the weighted average. So you can see that it pulls in pretty good as far as how accurate it is. You could say it's going to be about 90% is going to guess correctly that they're not going to purchase. And we had an 89% chance that they are going to purchase. And then the other numbers as you get down have a little bit different meaning, but it's pretty straightforward on here. Here's our accuracy, and here's our micro average and the weighted average and everything else you might need. And if you forgot the exact definition of accuracy, it is the true positive, true negative over all of the different setups. Precision is your true positive over all positives, true and false. And recall is a true positive over true positive plus false negative. And we can just real quick flip back there so you can see those numbers on here. Here's our precision, here's our recall, and here's our accuracy on this.
This tutorial is about object detection. We will walk you through a TensorFlow code using which we will do object detection in images. We will tell you what are the libraries that are required, a little bit about the COCO dataset, and then we will show you the implementation code itself, a demo of the code. Alright, so let's get started. So what is the TensorFlow Object Detection API? It is an open source framework which is actually provided by the TensorFlow team, and there are trained models available and the sample code is also available which we can use in order to easily detect objects in images and videos. This is pretty robust and can detect objects fairly quickly, and this is very easy for people to use as well. People with very less or no knowledge of machine learning or deep learning can also, with a little bit of Python programming knowledge, can actually use this API, this library, to build object detection applications. This is a list of libraries that are required and they have been shown in the code as well. The exact purpose of each of this library, why it is required, is out of the scope of this tutorial, but we will see in the code as we walk through some of these libraries how and why they are used. The COCO dataset, COCO stands for Common Objects in Context. So this dataset consists of 300,000 images of 90 most commonly found objects like chairs and tables and so on and so forth. So this model has been trained, or in fact a set of models have been trained on this data set, and this is pretty good to detect the most common objects in the images and videos. So with that, let's get into the code. Alright, so the first part is to import all these libraries, and this we have shown you in the slides as well. Again, a large part of this will be for doing some helper functions and maybe for visualizing the images and so on and so forth. So that's the reason they are required. As I said, the exact details of each and every library probably is out of scope, but these are needed. So as a first step, maybe you just go ahead and include these libraries and run the code, and maybe at a later point we can discuss what each of these libraries does. Now this will work with TensorFlow version higher than 1.4. So if you are having TensorFlow version below 1.4, you may have to upgrade to a higher version. So let me go ahead and execute the cell, and we also need this line of code to make sure that once we run this object detection, the labeled images are displayed within this notebook, and many of you by now must be familiar with this. And we will import a few utility libraries, and you will see that we will be using some of these for visualization purpose. So once the objects are detected, we need to display the information, what that object is, and then what percentage of confidence the model has. So all these details, that's the utility functions that are stored here. And then the next part is to prepare the model. As I mentioned, we will be using an existing trained model. The TensorFlow team has actually provided these models. The one that we will be using is SSD with the mobile net, but you can actually use any one of the ones that are listed in this URL. Let me just quickly take you through this URL. These are a bunch of models, trained models that are readily available for anybody to use. It is open source, and let me scroll down. The only thing is that if there are some of them where the accuracy is much higher but they take longer, and there are some where the accuracy is not so high and they are much faster. So they are faster but the accuracy may not be that very high. So you can play around with some of these, and we in this particular exercise or in this particular tutorial, we are using this SSD model, which is SSD MobileNet version 1. So that's the model that we'll be using. So in this cell, we are primarily creating a bunch of variables with the various, for example, the name of the model, the path, and so on and so forth, so that we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, and then you kind of extract or you freeze the model. So that's the reason they are called frozen models, so that others can just use this without any further training. So this is where we download and extract our model locally. So this will take a little while. Let me see if I can wait or maybe pause the video and come back once it is done. Might take a little while. Let's see if it completes. I have a pretty high speed network, but even then it takes some time, so that's good. But this part is over. Now let us see this part, and yes, both are done. So once that is done, we need to load some label mapping. Basically what this will do is, your model, as you may be aware by now, if you do some classification, the model will actually not give any output as a text. It will give some numbers. So if there are 5 classes, it will say, okay, this belongs to model class 1 or 2 or 3 or 5 and so on, the numbers. Now each of these will obviously, the numbers will not make any sense to the outside world, so we need to do some small mapping. So in this case, let's say 1 may be a chair, 2 may be a table, 3 may be a balloon, and so on. So that kind of number to text mapping we need to do, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, so that the NumPy array is what gets processed and used by the model to do the detection part of it. So that is what this method is all about. So we will be later on we will be calling that function. And next is preparation for detection. So here we are basically telling where the images are stored and how many images, or what is the naming convention or format of the images. Now if you want, you can modify this code. For example, currently I have test_images as my folder. So let me go and show this to you. So this is under my object detection folder. I have another subfolder where I am storing my images, which is text_images. Now you can rename this folder and give some other name, and then in your code you can probably give that particular name for the subfolder. Similarly, the format of these files, what is the name and format of these files? Here it is in a very simple format, which is the names of the files are like beach 1, beach 2, beach 3, and so on. So I have taken beach as the theme. So I have images which are related to beaches. So this is beach 1, beach 2, and then beach 3. I have a few others, but we will use these 3 for our demo. And so that's what I'm saying here. The name of the images will be beach something.jpg, which is JPEG format, and in this curly braces basically will be filled with either 1, 2, or 3 based on in this particular for loop. Okay, so that is what this is doing. Alright, so the next step is to run inference on these images in a loop, and what we are basically doing here is getting these images one by one and then running through the model to find out what are the objects that can be detected, and then against each of the object a box will be drawn and it will be labeled with the name and the percentage of accuracy or confidence that the model detects these objects. Okay, so that is the function here, and so let me just run that piece of code. And here is basically where we are calling this function. So we are loading these images and then we are calling this function for each image, and then we are displaying this using the matplotlib library. So let's run this. It will take one image at a time and then detect the images. Now the beauty is that the same format of the code can be used for doing object detection in a video. So we have another video for doing object detection in a video. So most of the code out there will be reused from here, and the only thing is that instead of reading the images from the local storage, we read the frames from the video, and there is a neat little video reader that is available and it will be shown in the other video, and frame by frame we read the video and then pass on to this function, and it will act as if each of these frames is an image, and then it will do the same object detection on the entire video. So that's in a separate video. Just look out for that. And actually the information about that is provided in the cards, the eye symbol. So that's the video object detection in video. That's the separate tutorial. All right, so now that we have all the pieces together, the last cell is where the whole action takes place. So let's run this and see how it looks. So it will take probably a little while, and there are about 3 images. Let's see what it detects. There we go. So good. So the first one, it has detected a person, and that too with 97% accuracy, which is I think pretty good. Okay, and then the next image, it detects umbrella and chair. There are a few other objects, but it's not able to detect. It has detected umbrella with 63% accuracy, or confidence rather, and the chair with 58%. Again, not bad. Then let's see the next image. So here, these are actually balloons, hot air balloons, but the model thinks it is a kite, which is probably not that bad. It sees there is something in the sky, and therefore probably it thinks it is a kite, and it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images. And with that, we come to the end of this tutorial.
Welcome to the Neural Network tutorial. My name is Richard Kirschner. I'm with the Simplilearn team. What's in it for you? Well, today we're going to cover what is a neural network, what can neural networks do, how does a neural network work, types of neural networks, and then we're going to jump into a use case to classify between the photos of dogs and cats. And we'll do that on the Keras with the TensorFlow in the back, but it's a Python script, so that's always my favorite part, is when we dive into the actual script. So what is a neural network? So hi guys, I heard you want to know what a neural network is. Here we have, looks like you just went shopping at a red tag sale. My robot's back. So as a matter of fact, you have been using neural network on a daily basis. In today's world, it's just amazing how much we use our new technology. We're not even aware of it. When you ask your mobile assistant to perform a search for you, like saying your Google or Siri or whoever you use, Amazon Web. Self-driving cars, so that's the newest thing coming out. They're just now trying to make those legal in different states in the US and around the world. Even in the UK, they now have self-driving cars going up and down the streets. Pretty amazing. These are all neural network driven. Computer games use it. So a lot of computer games are driven by neural networks in the back end as part of the game system and how it adjusts to the players. And it's also used in processing the map images on your phone. So every time you do a navigation someplace and it opens it up, they now use neural networks to help you find the quickest way to get there. Neural network. A neural network is a system or hardware that is designed to operate like a human brain. In today's development, this is so important to understand because we don't have anything else to compare it to. I'm sure someday in the future, the computer will redefine, or the neural network, or the AI, artificial intelligence, will redefine what these mean. But as far as we can today's world, in today's commercial development, we have to compare it to what humans do. So we want to compare how it operates to a human brain and how it solves problems like a human does. What can a neural network do? And really, we're just going to dive in deeper to what we just covered and look at other examples. So what can a neural network do? Well, let's list out the things neural networks can do for you. Translate text. Boy, we got Google Translate, and Microsoft has their own Translate. They have some really cool, they actually have an earpiece that's supposed to start translating as you talk. What a cool technology. What a cool time to live. Identify faces. Can you imagine all the uses for facial identification? In the case of our sample, or our code that we're going to look at later, we'll be identifying dogs and cats, so not quite as detailed as understanding whose face belongs to who. I'm waiting for the Google glasses to come out so I can see who's who and identify faces as I'm walking around, have a little name tag over them. Not out there yet, but boy, we are close. We can identify the faces, and they have all kinds of technologies to bring that information back to us. Recognize speech goes along with the translate text. So now as you're talking into your assistant, it can use that to do commands, turn lights on, all kinds of things you can do with recognizing speech. Read handwritten text. They're starting to translate all these old text documents that they've had in storage. Instead of doing it individually where somebody's going through each text by themselves in a room. You can picture like an old Raiders of the Lost Ark theme where he's in the back, archaeologist studying the text. Now it's fed into a computer. They take a picture. They even use neural networks to take a scroll that is so messed up that they can't undo the scroll, and they x-ray it, and then they use that x-ray to translate the text off of it without ever opening the scroll. I mean, just way cool stuff they're starting to do with all this. And of course, control robots. What would be a neural network without bringing in the robots? And we have our own favorite robot in the middle who goes to our red tag cell and goes shopping for us. So, these are just a few of the wonderful things that neural networks are being applied to. It's such an infant stage technology. What a wonderful time to jump in. And there are a lot of other things it goes into. I mean, we could spend just forever talking about all the different applications from business to whatever you could even imagine. They're now applying neural networks to help us understand. So now that we talked a little bit about all the cool things you can do with a neural network, let's dive in and say, how does a neural network work? So now we've come far enough to understand how neural network works. Let's go ahead and walk through this in a nice graphical representation. They usually describe a neural network as having different layers. And you'll see that we've identified a green layer, an orange layer, and a red layer. The green layer is the input. So you have your data coming in. It picks up the input signals and passes them to the next layer. The next layer does all kinds of calculations and feature extraction. It's called the hidden layer. A lot of times there's more than one hidden layer. We're only showing one in this picture, but we'll show you how it looks like in a more detail in a little bit. And then finally we have an output layer. This layer delivers the final result. So the only two things we see is the input layer and the output layer. Now let's make use of this neural network and see how it works. Wonder how traffic cameras identify vehicles' registration plate on the road to detect speeding vehicles and those breaking the law? They got me going through a red light the other day. Well, last month. That's like the horrible thing. They send you this picture of you and all your information because they pulled it up off of your license plate and your picture. I shouldn't have gone through the red light. So here we are, and we have an image of a car, and you can see the license plate on there. So let's consider the image of this vehicle and find out what's on the number plate. The picture itself is 28 by 28 pixels, and the image is fed as an input to identify the registration plate. Each neuron has a number called activation that represents the grayscale value of the corresponding pixel range. And we range it from 0 to 1. 1 for a white pixel and 0 for a black pixel. And you can see down here we have an example where one of the pixels is registered as like 0.82, meaning it's probably pretty dark. Each neuron is lit up when its activation is close to 1. So as we get closer to black on white, we can really start seeing the details in there. And you can see again the pixel shows us one up there. It's like part of the car, and so it lights up. So pixels in the form of arrays are fed to the input layer. And so we see here the pixel of a car image fed as an input. And you're going to see that the input layer, which is green, is 1 dimension, while our image is 2 dimension. Now, when we look at our setup that we're programming in Python, it has a cool feature that automatically does the work for us. If you're working with an older neural network pattern package, you then convert each one of those rows so it's all one array. So you'd have like row 1 and then just tack row 2 onto the end. You can almost feed the image directly into some of these neural networks. The key is, though, is that if you're using a 28 by 28 and you get a picture of this 30 by 30, shrink the 30 by 30 down to fit the 28 by 28. So you can't increase the number of input, in this case green dots. It's very important to remember when you work on neural networks. And let's name the inputs x1, x2, x3 respectively. So each one of those represents one of the pixels coming in. And the input layer passes it to the hidden layer. And you can see here we now have 2 hidden layers in this image, in the orange, and each one of those pixels connects to each one of those hidden layers. And the interconnections are assigned weights at random. So they get these random weights that come through. If x1 lights up, then it's going to be x1 times this weight going into the hidden layer. And we sum those weights. The weights are multiplied with the input signal, and a bias is added to all of them. So as you can see here, we have x1 comes in, and it actually goes to all the different hidden layers nodes, or in this case, whatever you want to call them, network setup, the orange dots. And so you take the value of x1, you multiply it by the weight for the next hidden layer. So x1 goes to hidden layer 1, x1 goes to hidden layer 2, x1 goes to hidden layer 1 node 2, hidden layer 1 node 3, and so on. And the bias, a lot of times they just put the bias in as like another green dot or another orange dot, and they give the bias a value 1, and then all the weights go in from the bias into the next node. So the bias can change. We always just remember that you need to have that bias in there. There's things that can be done with it. Generally, most of the packages out there control that for you, so you don't have to worry about figuring out what the bias is. But if you ever dive deep into neural networks, you got to remember there's a bias, or the answer won't come out correctly. The weighted sum of the input is fed as an input to the activation function to decide which nodes to fire and for feature extraction. As the signal flows within the hidden layers, the weighted sum of inputs is calculated and is fed to the activation function in each layer to decide which nodes to fire. So here's our feature extraction of the number plate. And you can see these are still hidden nodes in the middle. And this becomes important. We're going to take a little detour here and look at the activation function. So we're going to dive just a little bit into the math, so you can start to understand where some of the games go on when you're playing with neural networks and you're programming. So let's look at the different activation functions. Before we move ahead, here's our friendly red tag shopping robot. And so one is the sigmoid function. And the sigmoid function, which is 1 over 1 plus e to the minus x, takes the x value, and you can see where it generates almost a 0 and almost a 1 with a very small area in the middle where it crosses over. And we can use that value to feed into another function. So if it's really uncertain, it might have a 0.1 or 0.2 or 0.3, but for the most part it's going to be really close to 1 and really close to, in this case, 0 to 1. The threshold function. So if you don't want to worry about the uncertainty in the middle, you just say, oh, if x is greater than or equal to 0, if not, then x is 0. So it's either 0 or 1. Really straightforward. There's no in between in the middle. And then you have what they call the ReLU function. And you can see here where it puts out the value, but then it says, well, if it's over 1, it's going to be 1. And if it's less than 0, it's 0. So it kind of just dead ends it on those two ends, but allows all the values in the middle. And again, this, like the sigmoid function, allows that information to go to the next level. So it might be important to know if it's a 0.1 or a minus 0.1. The next hidden layer might pick that up and say, oh, this piece of information is uncertain, or this value has a very low certainty to it. And then the hyperbolic tangent function. And you can see here it's 1 minus e to the minus 2x over 1 plus e to the minus 2x. And it's very much along the same theme. A little bit different in here in that it goes between minus 1 and 1. So you'll see some of these, they go 0 to 1, but this one goes minus 1 to 1. And if it's less than 0, it's, it doesn't fire. And if it's over 0, it fires. And it also still puts out a value. So you still have a value that you can get off of that, just like you can with the sigmoid function and the ReLU function. Very similar in use. And I believe originally used to be everything was done in the sigmoid function. That was the most commonly used. And now they just kind of use more the ReLU function. The reason is, one, it processes faster because you already have the value and you don't have to add another compute the 1 over 1 plus e to the minus x for each hidden node. And the data coming off works pretty good as far as putting it into the next level if you want to know just how close it is to 0. How close is it not to functioning? Is it minus 0.1, minus 0.2? Usually they're float values. You get like minus 0.00138 or something. So, important information, but the ReLU is most commonly used these days as far as the setup we're using. But you'll also see the sigmoid function very commonly used also. Now that you know what an activation function is, let's get back to the neural network. So finally, the model would predict the outcome of applying a suitable activation function to the output layer. So we go in here, we look at this, and we have the optical character recognition, OCR, is used on the images to convert it into a text in order to identify what's written on the plate. And as it comes out, you'll see the red node, and the red node might actually represent just the letter A. So there's usually a lot of outputs when you're doing text identification. We're not going to show that on here, but you might have it even in the order. It might be what order the license plate's in. So you might have A, B, C, D, E, F, G, the alphabet plus the numbers, and you might have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So it's a very large array that comes out. It's not a small amount of, we show 3 dots coming in, 8 hidden layer nodes, 2 sets of 4. We just show 1 red coming out. A lot of times this is, 28 times 28. If you did 30 times 30, that's 900 nodes. So 28 is a little bit less than that just on the input. And so you can imagine the hidden layer is just as big. Each hidden layer is just as big, if not bigger. And then the output is going to be, there's so many digits. It's a lot. It's a huge amount of input and output. But we're only showing you just, it'd be hard to show in one picture. And so it comes up, and this is what it finally gets out on the output, is it identifies a number on the plate. And in this case, we have 08-D-03858. Error in the output is back propagated through the network and weights weights are adjusted to minimize the error rate. This is calculated by a cost function. When we're training our data, this is what's used. And we'll look at that in the code when we do the data training. So we have stuff we know the answer to, and then we put the information through, and it says, yes, that was correct, or no. Because remember, we randomly set all the weights to begin with. And if it's wrong, we take that error. How far off are you? Are you off by, if it was like -1, you're just a little bit off. If it's like -300 was your output, remember when we're looking at those different options? Hyperbolic or whatever, and we're looking at the REL. The REL doesn't have a limit on top or bottom. It actually just generates a number. So if it's way off, you're going to have to adjust those weights a lot. But if it's pretty close, you might adjust the weights just a little bit. And you keep adjusting the weights until they fit all the different training models you put in. So you might have 500 training models, and those weights will adjust using the back propagation. It sends the error backward. The output is compared with the original result, and multiple iterations are done to get the maximum accuracy. So not only does it look at each one, but it goes through it and just keeps cycling through the data, making small changes in the network until it gets the right answers. With every iteration, the weights at every interconnection are adjusted based on the error. We're not going to dive into that math because it is a differential equation and it gets a little complicated. But I will talk a little bit about some of the different options they have when we look at the code. So we've explored a neural network. Let's look at the different types of artificial neural networks. And this is like the biggest area growing, is how these all come together. Let's see the different types of neural network. And again, we're comparing this to human learning. So here's a human brain. I feel sorry for that poor guy. So we have a feed-forward neural network. Simplest form of they call it an ANN, a neural network. Data travels only in one direction, input to output. This is what we just looked at. So as the data comes in, all the weights are added, it goes to the hidden layer, all the weights are added, it goes to the next hidden layer, all the weights are added, and it goes to the output. The only time you use the reverse propagation is to train it. So when you actually use it, it's very fast. When you're training it, it takes a while because it has to iterate through all your training data. And you start getting into big data because you can train these with a huge amount of data. The more data you put in, the better trained they get. The applications, vision and speech recognition, actually they're pretty much everything we talked about. Almost all of them use this form of neural network at some level. Radio basis function neural network. This model classifies the data point based on its distance from a center point. What that means is that you might not have training data, so you want to group things together and you create central points, and it looks for all the things, some of these things are just like the other. If you've ever watched the Sesame Street as a kid, that dates me. So it brings things together. And this is a great way, if you don't have the right training model, you can start finding things that are connected you might not have noticed before. Applications, power restoration systems. They try to figure out what's connected, and then based on that, they can fix the problem if you have a huge power system. Cohonen self-organizing neural network. Vectors of random dimensions are input to discrete map comprised of neurons. So they basically find a way to draw, and they say dimensions, or vectors, or planes, because they actually chop the data in 1 dimension, 2 dimension, 3 dimension, 4, 5, 6. They keep adding dimensions and finding ways to separate the data and connect different data pieces together. Applications used to recognize patterns in data, like in medical analysis. The hidden layer saves its output to be used for future prediction. Recurrent neural networks. So the hidden layers remember its output from last time, and that becomes part of its new input. You might use that especially in robotics or flying a drone. You want to know what your last change was and how fast it was going to help predict what your next change you need to make is to get to where the drone wants to go. Applications, text-to-speech, conversation model. So, I talked about drones, but, just identifying on Lex or Google Assistant or any of these, they're starting to add in, I'd like to play a song on my Pandora and I'd like it to be at volume 90%. So you now can add different things in there and it connects them together. The input features are taken in batches like a filter. This allows a network to remember an image in parts. Convolutional neural network. Today's world in photo identification and taking apart photos and trying to, have you ever seen that on Google where you have 5 people together? This is the kind of thing separates all those people so then it can do a face recognition on each person. Applications used in signal and image processing. In this case, I use facial images or Google picture images as one of the options. Modular neural network. It has a collection of different neural networks working together to get the output. So, wow, we just went through all these different types of neural networks, and the final one is to put multiple neural networks together. And I mentioned that a little bit when we separated people in a larger photo, individuals in the photo, and then do the facial recognition on each person. So one network is used to separate them, and the next network is then used to figure out who they are and do the facial recognition. Applications still undergoing research. This is the cutting edge. You hear the term pipeline, and there's actual in Python code and in almost all the different neural network setups out there, they now have a pipeline feature usually. And it just means you take the data from one neural network and maybe another neural network, or you put it into the next neural network, and then you take 3 or 4 other neural networks and feed them into another one. So how we connect the neural networks is really just cutting edge, and it's so experimental. I mean, it's almost creative in its nature. There's not really a science to it because each specific domain has different things it's looking at. So if you're in the banking domain, it's going to be different than the medical domain, than the automatic car domain. And suddenly figuring out how those all fit together is just a lot of fun and really cool. So we have our types of artificial neural network. We have our feed-forward neural network. We have our radial basis function neural network. We have our Cohennon self-organizing neural network, recurrent neural network, convolution neural network, and modular neural network, where it brings them all together. And the colors on the brain do not match what your brain actually does, but they do bring it out that most of these were developed by understanding how humans learn. And as we understand more and more of how humans learn, we can build something in the computer industry to mimic that, to reflect that. And that's how these were developed. So, exciting part, use case, problem statement. So this is where we jump in. This is my favorite part. Let's use the system to identify between a cat and a dog. If you remember correctly, I said we're going to do some Python code, and you can see over here my hair is kind of sticking up over the computer, a cup of coffee on one side, and then a little bit of old school, a pencil and a pen on the other side. Yeah, most people now take notes. I love the stickies on the computer. That's great. That is my computer. I have sticky notes on my computer in different colors. So not too far from today's programmer. So the problem is we want to classify photos of cats and dogs using a neural network. And you can see over here we have quite a variety of dogs in the pictures and cats, and just sorting out it is a cat is pretty amazing. And why would anybody want to even know the difference between a cat and a dog? Okay, why? Well, I have a cat door. It'd be kind of fun that instead of having like a little collar with a magnet on it, which is what my cat has, the door would be able to see, oh, that's the cat. That's our cat coming in. Oh, that's the dog. We have a dog too. That's the dog I want to let in. Maybe I don't want to let this other animal in because it's a raccoon. So you can see where you could take this one step further and actually apply this. You could actually start a little startup company idea, a self-identifying door. So this use case will be implemented on Python. I am actually in Python 3.6. It's always nice to tell people the version of Python because that does affect sometimes which modules you load and everything. And we're going to start by importing the required packages. I told you we're going to do this in Keras. So we're going to import from Keras models, a sequential from the Keras layers, conversion 2D or CONV 2D, max pooling 2D, flatten, and dense. And we'll talk about what each one of these do in just a second. But before we do that, let's talk a little bit about the environment we're going to work in. And in fact, let me go ahead and open the website, Keras's website, so we can learn a little bit more about Keras. So here we are on the Keras website, and it's keras.io. That's the official website for Keras. And the first thing you'll notice is that Keras runs on top of either TensorFlow, CNTK, and I think it's pronounced Thano or Theano. What's important on here is that TensorFlow, and the same is true for all these, but TensorFlow is probably one of the most widely used currently packages out there with the Keras. And of course, tomorrow this is all going to change. It's all going to disappear and they'll have something new out there. So make sure when you're learning this code that you understand what's going on and also know the code. I mean, when you look at the code, it's not as complicated once you understand what's going on. The code itself is pretty straightforward. And the reason we like Keras, and the reason that people are jumping on it right now and it's such a big deal is if we come down here, let me just scroll down a little bit, they talk about user friendliness, modularity, easy extensibility, work with Python. Python's a big one because a lot of people in data science now use Python. although you can actually access Keras other ways. If we continue down here is layers. And this is where it gets really cool. When we're working with Keras, you just add layers on. Remember those hidden layers we were talking about? And we talked about the RELU activation. You can see right here. Let me just up that a little bit in size. There we go. That's big. I can add in an RELU layer, and then I can add in a softmax layer in the next instance. We didn't talk about softmax. So you can do each layer separate. Now, if I'm working in some of the other kits I use, I take that and I have one setup, and then I feed the output into the next one. This one I can just add hidden layer after hidden layer with the different information in it, which makes it very powerful and very fast to spin up and try different setups and see how they work with the data you're working on. And we'll dig a little bit deeper in here. And a lot of this is very much the same, so when we get to that part, I'll point that out to you also. Now, just a quick side note, I'm using Anaconda with Python in it, and I went ahead and created my own package, and I called it the Keras Python 3.6 because I'm in Python 3.6. Anaconda is cool that way. You can create different environments real easily. If you're doing a lot of different experimenting with these different packages, you probably want to create your own environment in there. And the first thing is you can see right here, there's a lot of dependencies. A lot of these you should recognize by now if you've done any of these videos. If not, kudos for you for jumping in today. Pip install numpy, scipy, the scikit-learn, pillow, and h5py are both needed for the TensorFlow, and then putting the Keras on there. And then you'll see here, and pip is just a standard installer that you use with Python. You'll see here that we did pip install TensorFlow, since we're going to do Keras on top of TensorFlow. And then pip install, and I went ahead and used the GitHub. So git plus git, and you'll see here github.com. This is one of their releases, one of the most current release on there that goes on top of TensorFlow. And you can look up these instructions pretty much anywhere. This is for doing it on Anaconda. Certainly you'd want to install these if you're doing it in Ubuntu server setup. You'd want to get, I don't think you need the H5PY in Ubuntu, but you do need the rest in there because they are dependencies in there, and it's pretty straightforward. And that's actually in some of the instructions they have on their website. So you don't have to necessarily go through this. Just remember their website on there. And then when I'm under my Anaconda Navigator, which I like, you'll see where I have environments, and on the bottom I created a new environment and I called it Keras Python 36, just to separate everything. You can say I have Python 30.5 and Python 3.6. I used to have a bunch of other ones, but I kind of cleaned house recently. And of course, once I go in here, I can launch my Jupyter Notebook, making sure I'm using the right environment that I just set up. This, of course, opens up my, in this case, I'm using Google Chrome. And in here, I could go and just create a new document in here. And this is all in your browser when you use the Anaconda. Do you have to use Anaconda in Jupyter Notebook? No. You can use any kind of Python editor, whatever setup you're comfortable with and whatever you're doing in there. So let's go ahead and go in here and paste the code in. And we're importing a number of different settings in here. We have import sequential. That's under the models, because that's the model we're going to use as far as our neural network. And then we have layers, and we have conversion 2D, max pooling 2D, flatten, dense. And you can actually just kind of guess at what these do. We're working in a 2D photograph. And if you remember correctly, I talked about how the actual input layer is a single array. It's not in 2 dimensions, it's 1 dimension. All these do is these are tools to help flatten the image. So it takes a 2-dimensional image and then it creates its own proper setup. You don't have to worry about any of that. You don't have to do anything special with the photograph. You let the Keras do it. And we're going to run this, and you'll see right here they have some stuff that is going to be depreciated and changed, because that's what it does. Everything's being changed as we go. You don't have to worry about that too much. If you have warnings, if you run it a second time, the warning will disappear. And this is just imported these packages for us to use. And Jupyter's nice about this, that you can do each thing step by step. And I'll go ahead and also zoom in there. A little Control+. That's one of the nice things about being in a browser environment. So here we are back. Another sip of coffee. If you're familiar with my other videos, you notice I'm always sipping coffee. I always have in my case, latte next to me, an espresso. So the next step is to go ahead and initialize, we're going to call it the CNN, or classifier neural network. And the reason we call it a classifier is because it's going to classify it between 2 things. It's going to be cat or dog. So when you're doing classification, you're picking specific objects. It's a true or false, yes, no, it is something or it's not. So first thing, we're going to create our classifier, and it's going to equal sequential. So their sequential setup is the classifier. That's the actual model we're using. That's the neural network. So we call it a classifier. And the next step is to add in our convolution. And let me just do let me shrink that down in size so you can see the whole line. And let's talk a little bit about what's going on here. I have my classifier and I add something. What am I adding? Well, I'm adding my first layer. This first layer we're adding in is probably the one that takes the most work to make sure you have it set correct. And the reason I say that is this is your actual input. And we're going to jump here to the part that says input shape equals 64 by 64 by 3. What does that mean? Well, that means that our picture's coming in, and there's these pictures. Remember we had like the picture of the car was 128 by 128 pixels? Well, this one is 64 by 64 pixels. And each pixel has 3 values. That's where these numbers come from. And it is so important that this matches. I mentioned a little bit that if you have like a larger picture, you have to reformat it to fit this shape. If it comes in as something larger, there's no input nodes. There's no input neural network there that will handle that extra space. So you have to reshape your data to fit in here. Now, the first layer is the most important because after that, Keras knows what your shape is coming in here and it knows what's coming out. And so that really sets the stage. Most important thing is that input shape matches your data coming in. And you'll get a lot of errors if it doesn't. You'll go through there and picture number 55 doesn't match it correctly. And guess what it does? It usually gives you an error. And then the activation, if you remember we talked about the different activations on here. We're using the ReLU model. Like I said, that is the most commonly used now because one, it's fast. It doesn't have the added calculations in it. It just says here's the value coming out based on the weights and the value going in, and from there, you know, it's if it's over 1, then it's good, or over 0, it's good. If it's under 0, then it's considered not active. And then we have this conversion 2D. What the heck is conversion 2D? I'm not going to go into too much detail in this because this has a couple of things it's doing in here. A little bit more in depth than we're ready to cover in this tutorial. But this is used to convert from the photo because we have 64 by 64 by 3 and we're just converting it to two-dimensional kind of setup. So it's very aware that this is a photograph and that different pieces are next to each other. And then we're going to add in a second convolutional layer. That's what the CONV stands for, 2D. So these are hidden layers. So we have our input layer and our 2 hidden layers, and they are two-dimensional because we're dealing with a two-dimensional photograph. And you'll see down here that on the last one we add a max pooling 2D, and we put a pool size equals 2, And so what this is that as you get to the end of these layers, one of the things you always want to think of is what they call mapping and then reducing. Wonderful terminology from the big data. We're mapping this data through all these layers, and now we want to reduce it to only 2 sets. In this case, it's already in 2 sets because it's a 2D photograph. But we had, 2 dimensions we actually have 64 by 64 by 3. So now we're just getting it down to a 2 by 2, just the two-dimensional instead of having the third dimension of colors. And we'll go ahead and run these. We're not really seeing anything on our run script because we're just setting up. This is all set up. And this is where you start playing because maybe you'll add a different layer in here to do something else to see how it works and see what your output is. That's what makes Keras so nice is I can, with just a couple flips of code, put in a whole new layer that does a whole new processing and see whether that improves my run or makes it worse. And finally, we're going to do the final setup, which is to flatten. Classifier add a flatten setup, and then we're going to also add a dense layer, and then we're going to add in another dense layer, and then we're going to build it. We're going to compile this whole thing together. So let's flip over and see what that looks like. And we've even numbered them for you. So we're going to do the flattening. And flatten is exactly what it sounds like. We've been working in a two-dimensional array of picture, which actually is in 3 dimensions because of the pixels. The pixels have a whole other dimension to it of 3 different values. And we've kind of resized those down to 2 by 2. But now we're just going to flatten it. I don't want to have multiple dimensions being worked on by Tensor and by Keras. I want just a single array. So it's flattened out. And then step 4, full connection. So we add in our final 2 layers, and you could actually do all kinds of things with this. You could actually leave out this some of these layers and play with them. You do need to flatten it. That's very important. Then we want to use the dense. Again, we're taking this and we're taking whatever came into it. So once we take all those the 2 dimensions or 3 dimensions as they are, and we flatten it to 1 dimension, we want to take that and we're going to pull it into units of 128 128. They got that. You can say, where did they get 128 from? You could actually play with that number and get all kinds of weird results. But in this case, we took the 64 plus 64 is 128. You could probably even do this with 64 or 32. Usually you want to keep it in the same multiple of whatever the data shape you're already using is in. And we're using the activation, the RELU, just like we did before. And then we finally filter all that into a single output. And it has how many units? 1. Why? Because we want to know whether true or false. It's either a dog or a cat. You could say 1 is dog, 0 is cat. Or maybe you're a cat lover and it's 1 is cat and 0 is dog. And if you love both dogs and cats, you're going to have to choose. And then we use the sigmoid activation. If you remember from before, we had the RELU and there's also the sigmoid. The sigmoid just makes it clear it's yes or no. We don't want any kind of in-between number coming out. And we'll go ahead and run this, and you'll see it's still all in setup. And then finally we want to go ahead and compile. And let's put the compiling our classifier neural network. And we're going to use the optimizer Atom. And I hinted at this just a little bit before. Where does Atom come in? Where does an optimizer come in? Well, the optimizer is the reverse propagation. When we're training it, it goes all the way through and says error, and then how does it readjust those weights? There are a number of them. Atom is the most commonly used, and it works best on large data. Most people stick with the Atom because when they're testing on smaller data, see if their model is going to go through and get all their errors out before they run it on larger data sets. They're going to run it on Atom anyway, so they just leave it on Atom, most commonly used. But there are some other ones out there. You should be aware of that you might try them if you're stuck in a bind, or you might explore that in the future. But usually Atom is just fine on there. And then you have 2 more settings. You have loss and metrics. We're not going to dig too much into loss or metrics. These are things you really have to explore Keras because there are so many choices. This is how it computes the error. There's so many different ways on your back propagation and your training. So we're using the Atom model, but you can compute the error by standard deviation squared. They use binary cross entropy. I'd have to look that up to even know what that is. There's so many of these. A lot of times you just start with the ones that look correct, that are most commonly used, and then you have to go read the Keras site and actually see what these different losses and metrics and what different options they have. So we're not going to get too much into them other than to reference you over to the Keras website to explore them deeper. But we are going to go ahead and run them, and now we've set up our classifier. So we have an object classifier, and if you go back up here you'll see that we've added in step 1, we added in our layer for the input. We added a layer that comes in there and uses the RELU for activation, and then it pulls the data. So this is, even though these are 2 layers, the actual neural network layer is up here, and then it uses this to pull the data into a 2x2. So into a 2-dimensional array from a 3-dimensional array with the colors. Then we flatten it. So there's our adder flatten. And then we add another dense, what they call dense layer. This dense layer goes in there and it downsizes it to 128. It reduces it. So you can look at this as we're mapping all this data down the 2-dimensional setup, and then we flatten it. So we map it to a flattened map, and then we take it and reduce it down to 128. And we use the RELU again. And then finally we reduce that down to just a single output, and we use the sigmoid to do that, to figure out whether it's yes, no, true, false, in this case cat or dog. And then finally, once we put all these layers together, we compile them. That's what we've done here. And we've compiled them as far as how it trains to use these settings for the training, back propagation. So if you remember, we talked about training our setup. And when we go into this, you'll see that we have 2 data sets. We have one called the training set and the testing set. And that's very standard in any data processing, is you need to have, that's pretty common in any data processing, is you need to have a certain amount of data to train it, and then you got to know whether it works or not. Is it any good? And that's why you have a separate set of data for testing it, where you already know the answer, but you don't want to use that as part of the training set. So in here we jump into part 2, fitting the classifier neural network to the images. And then from Keras, and let me just zoom in there. I always love that about working with Jupyter notebooks. You can really see. We're going to come in here. We do the Keras pre-processing an image, and we import image data generator. It's so nice of Keras. It's such a high-end product right now going out. And since images are so common, they already have all this stuff to help us process the data, which is great. And so we come in here. We do train data gen, and we're going to create our object for helping us train it, for reshaping the data so that it's going to work with our setup. And we use an image data generator. and we're going to rescale it. And you'll see here we have 1 point, which tells us it's a float value on the rescale over 255. Where does 255 come from? Well, that's the scale in the colors of the pictures we're using. Their value from 0 to 255. So we want to divide it by 255 and it'll generate a number between 0 and 1. They have shear range and zoom range, horizontal flip equals true, and this of course has to do with if the photos are different shapes and sizes. Like I said, it's a wonderful package. You really need to dig in deep to see all the different options you have for setting up your images. For right now though, we're going to just stick with some basic stuff here, and let me go ahead and run this code. And again, it doesn't really do anything because we're still setting up the pre-processing. Let's take a look at this next set of code. And this one is just huge. We're creating the training set. So the training set is going to go in here and it's going to use our train data gen we just created, .flow from directory. It's going to access, in this case, the path, data set, training set. That's a folder. So it's going to pull all the images out of that folder. Now, I'm actually running this in the folder that the data set's in. So if you're doing the same setup and you load your data in there and you're doing this, make sure wherever your Jupyter Notebook is saving things to that you create this path, or you can do the complete path if you need to, C:/, etc. And the target size, the batch size, and class mode is binary. So the classes, we're switching everything to a binary value. Batch size, what the heck is batch size? Well, that's how many pictures we're going to batch through the training each time. And the target size, 64 by 64. A little confusing, but you can see right here that this is just a general training, and you can go in there and look at all the different settings for your training set. And of course, with different data, we're doing pictures, there's all kinds of different settings depending on what you're working with. Let's go ahead and run that and see what happens. And you'll see that it found 800 images belonging to one classes. So we have 800 images in the training set. And if we're going to do this with the training set, we also have to format the pictures in the test set. Now, we're not actually doing any predictions. We're not actually programming the model yet. All we're doing is preparing the data. So we're going to prepare a training set and the test set. So any changes we make to the training set at this point also have to be made to the test set. So we've done this thing, we've done a train data generator, we've done our training set, and then we also have, remember, our test set of data. So I'm going to do the same thing with that. I'm going to create a test data gen, and we're going to do this image data generator. We're going to rescale 1 over 255. We don't need the other settings, just the single setting for the test data gen. And we're going to create our test set. We're going to do the same thing we did with the test set, except that we're pulling it from the test set folder. And we'll run that, and you'll see in our test set we found 2,000 images. That's about right. We're using 20% of the images as test and 80% to train it. And then finally we've set up all our data. We've set up all our layers, which is where all the work is cleaning up that data, making sure it's going in there correctly. And we are actually going to fit it. We're going to train our data set. And let's see what that looks like. And here we go. Let's put the information in here. And let's just take a quick look at what we're looking at with our fit generator. We have our classifier.fit generator. That's our back propagation. So the information goes through forward with a picture, and it says, oh, you're either right or you're wrong, and then the error goes backward and reprograms all those weights. So we're training our neural network. And of course we're using the training set. Remember, we created the training set up here, and then we're going steps per epoch. So it's 8,000 steps. Epoch means that's how many times we go through all the pictures. So we're going to rerun each of the pictures, and we're going to go through the whole data set 25 times. But we're going to look at each picture during each epoch 8,000 times. So we're really programming the heck out of this and going back over it. And then they have validation data equals test set. So we have our training set, and then we're going to have our test set to validate it. So we're going to do this all in one shot. And we're going to look at that, and they're going to do 200 steps for each validation. And we'll see what that looks like in just a minute. Let's go ahead and run our training here. And we're going to fit our data. And as it goes, it says epoch 1 of 25. You start realizing that this is going to take a while. On my older computer, it takes about 45 minutes. I have a dual processor. We're processing 10,000 photos. That's not a small amount of photographs to process. So if you're on your laptop, which I am, it's going to take a while. So let's go ahead and go get our cup of coffee and a sip and come back and see what this looks like. So I'm back. You didn't know I was gone. I was actually a lengthy pause there. I made a couple changes, and let's discuss those changes real quick and why I made them. So the first thing I'm going to do is I'm going to go up here and insert a cell above, and let's paste the original code back in there. And you'll see that the original thing was steps per epoch 8,000, 25 epochs, and validation steps 2,000. And I changed these to 4,000 epochs, or 4,000 steps per epoch, 10 epochs, and just 10 validation steps. And this will cause problems if you're doing this as a commercial release. But for demo purposes, this should work. And if you remember, our steps per epoch, that's how many photos we're going to process. In fact, let me go ahead and get my drawing pen out. And let's just highlight that right here. Well, we have 8,000 pictures we're going through. So for each epoch, I'm going to change this to 4,000. I'm going to cut that in half. So it's going to randomly pick 4,000 pictures each time it goes through an epoch. And the epoch is how many processes. So this is 25, and I'm just going to cut that to 10. So instead of doing 25 runs through 8,000 photos each, which you can do the math of 25 times 8,000, I'm only going to do 10 through 4,000. So I'm going to run this 40,000 times through the processes. And the next thing I noted you'll want to notice is that I also changed the validation step. And this would cause some major problems in releasing because I dropped it all the way down to 10. What the validation step does is it says we have 2,000 photos in our trainings or in our testing set. And we're going to use that for validation. Well, I'm only going to use a random 10 of those to validate. So not really the best settings, but let me show you why we did that. Let's scroll down here just a little bit. And let's look at the output here and see what's going on there. So I've got my drawing tool back on, and you'll see here it lists a run. So each time it goes through an epoch, it's going to do 4,000 steps. And this is where the 4,000 comes in. So that's where we have epoch 1 of 10, 4,000 steps. So it's randomly picking half the pictures in the file and going through them. And then we're going to look at this number right here. That is for the whole epoch. And that's 2,411 seconds. And if you remember correctly, you divide that by 60, you get minutes. If you divide that by 60, you get hours. Or you can just divide the whole thing by 60 times 60, which is 3,600. If 3,600 is an hour, this is roughly 45 minutes right here. And that's 45 minutes to process half the pictures. So if I was doing all the pictures, we're talking an hour and a half per epoch times 36. Or no, 25. They had 25 up above. 25. So that's roughly a couple days of processing. Well, for this demo, we don't want to do that. I don't want to come back the next day. Plus, my computer did a reboot in the middle of the night. So we look at this and we say, okay, we're just testing this out. My computer that I'm running this on is a dual core processor, runs 0.9 gigahertz per second. For a laptop, it was good about 4 years ago, but for running something like this, it's probably a little slow. So we cut the times down, and the last one was validation. We're only validating it on a random 10 photos. And this comes into effect because you're going to see down here where we have accuracy, value loss, value accuracy, and loss. Those are very important numbers to look at. So the 10 means I'm only validating across 10 pictures. That is where, here we have value, this is ACC is for accuracy. Value loss, we're not going to worry about that too much, and accuracy. Now accuracy is while it's running, it's putting these two numbers together. That's what accuracy is. And value accuracy is at the end of the epoch. What's our accuracy at the end of the epoch? What is it looking at? In this tutorial, we're not going to go so deep, but these numbers are really important when you start talking about these two numbers reflect bias. That is really important. I'll just put that up there. And bias is a little bit beyond this tutorial, but the short of it is if this accuracy, which is being our validation per step, is going down, and the value accuracy continues to go up, that means there's a bias. That means I'm memorizing the photos I'm looking at. I'm not actually looking for what makes a dog, what makes a cat. I'm just memorizing them. And so the more this discrepancy grows, the bigger the bias is. And that is really the beauty of the Keras neural network. It has a lot of built-in features like this that make that really easy to track. So let's go ahead and take a look at the next set of code. So here we are into part 3. We're going to make a new prediction. And so we're going to bring in a couple tools for that, and then we have to process the image coming in and find out whether it's an actual dog or cat, if we can actually use this to identify it. And of course the final step of part 3 is to print prediction. We'll go ahead and combine these, and of course you can see me there adding more sticky notes to my computer screen, hidden behind the screen, and last one was don't forget to feed the cat and the dog. So let's go ahead and take a look at that and see what that looks like in code and put that in our Jupyter notebook. All right, and let's paste that in here. And we'll start by importing NumPy as NP. NumPy is a very common package. I pretty much import it on any Python project I'm working on. Another one I use regularly is pandas. They're just ways of organizing the data. And then NP is usually the standard in most machine learning tools as a return for the data array. Although, you can use a standard data array from Python. And we have cross pre-processing, import image. This should all look familiar because we're going to take a test image and we're going to set that equal to, in this case, cat or dog 1, as you can see over here. And let me get my drawing tool back on. So let's take a look at this. We have our test image we're loading, and in here we have test image 1, and this one data hasn't seen this one at all, so this is all new. Oh, let me shrink the screen down. Let me start that over. So here we have my test image, and we went ahead and the cross processing has this nice image setup. So we're going to load the image and we're going to alter it to a 64 by 64 print. So right off the bat, we're going to cross is nice that way. It automatically sets it up for us so we don't have to redo all our images and find a way to reset those. And then we use all those to set the image to an array. So again, we're all in pre-processing the data, just like we pre-processed before with our test information and our training data. And then we use the NumPy. Here's our NumPy. That's from our right up here, import NumPy as NP. Expand the dimensions test image axes equals 0. So it puts it into a single array. And then finally, all that work, all that pre-processing, and all we do is we run the result. We click on here and we go result equals, and let's just take a quick look and just see what that is. And you can see when I ran it, it comes up dog. And if we look at those images, there it is, cat or dog, image number 1. That looks like a nice floppy-eared lab. Friendly with his tongue hanging out. It's either that or a very floppy-eared cat. I'm not sure which. But according to our software, it says it's a dog. And we have a second picture over here. Let's just see what happens when we run the second picture. We can go up here and change this from dog image 1 to 2. We'll run that, and it comes down here and says cat. You can see me highlighting it down there as cat. So our process works. We are able to label a dog and a cat just from the pictures. There we go, cleared my drawing tool. And the last thing I want you to notice, when we come back up here to when I ran it, you'll see it has an accuracy of 1 and the value accuracy of 1. Well, the value accuracy is the important one because the value accuracy is what it actually runs on the test data. Remember, I'm only validating it on a random 10 photos. And those 10 photos just happen to come up 1. Now, when they ran this on the server, it actually came up about 86%. This is why cutting these numbers down so far for a commercial release is bad. So you want to make sure you're a little careful of that when you're testing your stuff, that you change these numbers back when you run it on a more enterprise computer other than your old laptop that you're just practicing on or messing with. And we come down here and again, we had the validation of cat. And so we have successfully built a neural network that could distinguish between photos of a cat and a dog. Imagine all the other things you could distinguish. Imagine all the different industries you could dive into with that, just being able to understand those two different pictures. What about mosquitoes? Could you find the mosquitoes that bite versus the mosquitoes that are friendly? It turns out the mosquitoes that bite us are only 4% of the mosquito population, if even that, maybe 2%. There's all kinds of industries that use this, and there's so many industries that are just now realizing how powerful these tools are. Just in the photos alone, there is a myriad of industries sprouting up. And I said it before, I'll say it again, what an exciting time to live in with these tools that we get to play with. So, key takeaways. Well, we covered what is a neural network. We use all kinds of processing, the map images on your phone. We talked about things that a neural network can do. Translate text, identify faces, all the way to control robots. Lots of exciting things. How does a neural network work? So we discussed that with the different layers, going from the picture to the input layer, to the hidden layers and their weights, to the final output layer. We also talked about how it does the math and computing the output as yes or no, categorically true, false. We discussed types of artificial neural networks. A lot of vocabulary there from the feed-forward neural network, which is the most commonly used. That's the neural network we used is a feed-forward neural network that does backward propagation to train. And there's a lot of other ones out there. There's the radial biases, the Cohennon self-organizing recurrent neural network, convolutional neural network, modular neural network. The big one was modular because it incorporates pieces of all the other ones so that whatever you're working on now is a huge conglomerate of multiple networks. Just all cutting edge. All of it's new. People even working on it don't even know where it's going. Again, very exciting times. And finally, we dug through my favorite part. You can see with my latte on one side, my old school pens and pencil, and all my sticky notes working away. That's not actually me, by the way. You probably guessed that. And we walked through and actually did a cat and dog photo, a simple cat and dog photo, and you could see where some of the problems are in processing large amounts of photographs and data, where that starts to become going from a single machine on my laptop with its lower amount of resources all the way to big data. How if you're processing hundreds and thousands of these photos, this now needs to be set up on an enterprise machine or even on a cluster of computers. Again, significantly past the scope of this. The neat part about it, though, is once you write this code, most of this code, they now have tools that you can almost take the same ideas, if not the actual code, and push it right onto a cluster computation. So really cool times for this. Welcome to the RNN tutorial. That's the Recurrent Neural Network. My name is Richard Kirschner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you? We will start with, of course, the fundamentals. What is a neural network and popular neural networks? It's important to know the framework we're in and what we're going to be looking at specifically. Then we'll touch on why a recurrent neural network, what is a recurrent neural network, and how does an RNN work. One of the big things about RNNs is what they call the vanishing and exploding gradient problem. So we'll look at that. And then we're going to be using a use case study. It's going to be in Keras on TensorFlow. Keras is a Python module for doing neural networks and deep learning. And in there, there's what they call long short-term memory, LSTM. And then we'll use the use case to implement our LSTM on the Keras. So when you see that LSTM, that is basically the RNN network. And we'll get into that. The use case is always my favorite part. Before we dive into any of this, we're going to take a look at what is an RNN, or an introduction to the RNN. Do you know how Google's autocomplete feature predicts the rest of the words a user is typing? I love that autocomplete feature. As I'm typing away, it saves me a lot of time. I can just kind of hit the enter key and it autofills everything and I don't have to type as much. Well, first there's a collection of large volumes of most frequently occurring consecutive words. This is fed into a recurrent neural network. Analyzes the data by finding the sequence of words occurring frequently and builds a model to predict the next word in the sentence. And then Google, what is the best food to eat in Las, I'm guessing you're going to say Las Mexico. No, it's going to be Las Vegas. So the Google search will take a look at that and say, hey, the most common autocomplete is going to be Vegas in there. And usually it gives you 3 or 4 different choices. So it's a very powerful tool. It saves us a lot of time, especially when we're doing a Google search, or even in Microsoft Words has some people get very mad at it because it autofills with the wrong stuff. But you're typing away and it helps you autofill. I have that in a lot of my different packages. It's just a standard feature that we're all used to now. So before we dive into the RNN and getting into the depths, let's go ahead and talk about what is a neural network. Neural networks used in deep learning consist of different layers connected to each other and work on the structure and functions of a human brain. You're going to see that thread, human brain and human thinking, throughout deep learning. The only way we can evaluate an artificial intelligence or anything like that is to compare it to human function. Very important note on there. And it learns from huge volumes of data, and it uses complex algorithms to train a neural net. So in here we have image pixels of 2 different breeds of dog. One looks like a nice floppy-eared lab, and one a German Shepherd. Both wonderful breeds of animals. That image then goes into an input layer. That input layer might be formatted at some point because you have to let it know, different pictures are going to be different sizes and different color content. Then it'll feed into hidden layers. So each of those pixels or each point of data goes in and then splits into the hidden layer, which then goes into another hidden layer, which then goes to an output layer. RNN, there's some changes in there which we're going to get into. So it's not just a straightforward propagation of data like we've covered in many other tutorials. And finally you have an output layer, and the output layer has 2 outputs. It has one that lights up if it's a German Shepherd and another that lights up if it's a Labrador. So it identifies the dog's breed. Such networks do not require memorizing the past output. So our forward propagation is just that. It goes forward and it doesn't have to rememorize stuff. And you can see there, that's not actually me in the picture, dressed up in my suit. I haven't worn a suit in years. So as we're looking at this, we're going to change it up a little bit. Before we cover that, let's talk about popular neural networks. First, there's the feed-forward neural network, used in general regression and classification problems. And we have the convolutional neural network, used for image recognition. Deep neural network, used for acoustic modeling. Deep belief network, used for cancer detection. And recurrent neural network, used for speech recognition. Now, taken a lot of these and mixed them around a little bit, so just because it's used for one thing doesn't mean it can't be used for other modeling. But generally, this is where the field is, and this is how those models are generally being used right now. So we talk about a feed-forward neural network. In a feed-forward neural network, information flows only in the forward direction, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. And so you can see here we have our input layer. I was talking about how it just goes straight forward into the hidden layers. So each one of those connects and then connects to the next hidden layer, connects to the output layer. And of course we have a nice simplified version where it has a predicted output, and they refer to the input as X a lot of times and the output as Y. Decisions are based on current input, no memory about the past, no future scope. Why recurrent neural network? Issues in feed-forward neural network. So one of the biggest issues is because it doesn't have a scope of memory or time, a feed-forward neural network doesn't know how to handle sequential data. It only considers only the current input. So if you have a series of things, and because 3 points back affects what's happening now, and what your output affects what's happening, that's very important. So whatever I put as an output is going to affect the next one. A feed-forward doesn't look at any of that. It just looks at this is what's coming in. And it cannot memorize previous inputs. So it doesn't have that list of inputs coming in. Solution to feed-forward neural network. You'll see here where it says recurrent neural network, and we have our X on the bottom going to H going to Y. That's your feed forward. But right in the middle it has a value C, so there's a whole other process. So it's memorizing what's going on in the hidden layers, and the hidden layers, as they produce data, feed into the next one. So your hidden layer might have an output that goes off to Y, but that output goes back into the next prediction coming in. What this does is this allows it to handle sequential data. It considers the current input and also the previously received inputs. And if we're going to look at general drawings and solutions, we should also look at applications of the RNN. Image captioning. RNN is used to caption an image by analyzing the activities present in it. A dog catching a ball in midair. That's very tough. I mean, we have a lot of stuff that analyzes images of a dog and the image of a ball, but it's able to add one more feature in there that's actually catching the ball in midair. Time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And we'll dive into that in our use case and actually take a look at some stock. One of the things you should know about analyzing stock today is that it is very difficult. And if you're analyzing the whole stock, the stock market at the New York Stock Exchange in the US produces somewhere in the neighborhood, if you count all the individual trades and fluctuations by the second, it's like 3 terabytes a day of data. So we're only going to look at one stock. Just analyzing one stock is really tricky. In here, we'll give you a little jump on that, so that's exciting, but don't expect to get rich off of it immediately. Another application of the RNN is natural language processing. Text mining and sentiment analysis can be carried out using RNN for natural language processing. And you can see right here the term natural language processing, when you stream those 3 words together, is very different than if I said processing language naturally. So the time series is very important when we're analyzing sentiments. It can change the whole value of a sentence just by switching the words around. Or if you're just counting the words, you might get one sentiment where if you actually look at the order they're in, you get a completely different sentiment. When it rains, look for rainbows. When it's dark, look for stars. Both of these are positive sentiments, and they're based upon the order of which the sentence is going in. Machine translation. Given an input in one language, RNN can be used to translate the input into a different languages as output. I myself am very linguistically challenged. But if you study languages and you're good with languages, you know right away that if you're speaking English, you would say big cat. And if you're speaking Spanish, you would say cat big. So that translation is really important to get the right order, to get, there's all kinds of parts of speech that are important to know by the order of the words. Here this person is speaking in English and getting translated. And you can see here a person is speaking in English in this little diagram. I guess that's denoted by the flags. I have a flag. I own it. No. But they're speaking in English and it's getting translated into Chinese, Italian, French, German, and Spanish languages. Some of the tools coming out are just so cool. So somebody like myself who's very linguistically challenged, I can now travel into worlds I would never think of, because I can have something translate my English back and forth readily, and I'm not stuck with a communication gap. So let's dive into what is a recurrent neural network. Recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. Sounds a little confusing. When we start breaking it down, it'll make more sense. And usually we have a propagation forward neural network with the input layers, the hidden layers, the output layer. With the recurrent neural network, we turn that on its side. So here it is, and now our X comes up from the bottom into the hidden layers into Y, and they usually draw it very simplified, X to H, with C as a loop, A to Y, where A, B, and C are the perimeters. A lot of times you'll see this kind of drawing in here, digging closer and closer into the H and how it works. Going from left to right, you'll see that the C goes in, and then the X goes in. So the X is going upward bound, and C is going to the right. A is going out. And C is also going out. That's where it gets a little confusing. So here we have X in, C in, and then we have Y out and C out. And C is based on HT minus 1. So our value is based on the Y and the H value are connected to each other. They're not necessarily the same value because H can be its own thing. And usually we draw this, or we represent it as a function. H of T equals a function of C, where H of T minus 1, that's the last H output, and X of T going in. So it's the last output of H combined with the new input of X, where HT is the new state, FC is a function with the parameters C, that's a common way of denoting it, HT minus 1 is the old state coming out, and then X of T is an input vector at time of step T. Well, we need to cover types of recurrent neural networks. And so the first one is the most common one, which is a one-to-one single output. One-to-one neural network is usually known as a vanilla neural network, used for regular machine learning problems. Why? Because vanilla is usually considered kind of just a real basic flavor. But because it's very basic, a lot of times they'll call it the vanilla neural network, which is not the common term, but it is, like kind of a slang term. People will know what you're talking about usually if you say that. Then we run one to many, so you have a single input, and you might have multiple outputs. In this case, image captioning, as we looked at earlier, where we have not just looking at it as a dog, but a dog catching a ball in the air. And then you have many-to-one network, takes in a sequence of inputs. Examples, sentiment analysis, where a given sentence can be classified as expressing positive or negative sentiments. And we looked at that as we were discussing, if it rains, look for a rainbow. So positive sentiment, where rain might be a negative sentiment if you were just adding up the words in there. And then, of course, if you're going to do a one-to-one, many-to-one, one-to-many, there's many-to-many networks, takes in a sequence of inputs and generates a sequence of outputs. Example, machine translation. So we have a lengthy sentence coming in English and then going out in all the different languages. Just a wonderful tool. Very complicated set of computations. If you're a translator, you realize just how difficult it is to translate into different languages. One of the biggest things you need to understand when we're working with this neural network is what's called the vanishing gradient problem. While training an RNN, your slope can be either too small or very large, and this makes training difficult. When the slope is too small, the problem is known as vanishing gradient. And you'll see here they have a nice image, loss of information through time. So if you're pushing not enough information forward, that information is lost, and then when you go to train it, you start losing the third word in the sentence or something like that, or it doesn't quite follow the full logic of what you're working on. Exploding gradient problem. Oh, this is one that runs into everybody. When you're working with this particular neural network, when the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. Issues in gradient problem: long training time, poor performance, bad accuracy. And I'll add one more in there. Your computer, if you're on a lower end computer testing out a model, will lock up and give you the memory error. Explaining gradient problem. Consider the following two examples to understand what should be the next word in the sequence. The person who took my bike and blank. A thief. The students who got into engineering with blank from Asia. And you can see in here we have our x value going in, we have the previous value going forward, and then you back propagate the error like you do with any neural network. And as we're looking for that missing word, maybe we'll have the person took my bike and blank was a thief, and the student who got into engineering with a blank were from Asia. Consider the following example, the person who took the bike, so we'll go back to the person who took the bike was blank a thief. In order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. So, was a thief is singular. The student who got into engineering, well, in order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. And so you can see here the students who got into engineering with blank were from Asia. It might be sometimes difficult for the error to back propagate to the beginning of the sequence to predict what should be the output. So when you run into the gradient problem, we need a solution, the solution to the gradient problem. First, we're going to look at exploding gradient, where we have three different solutions depending on what's going on. One is identity initialization. So the first thing we want to do is see if we can find a way to minimize the identities coming in instead of having it identify everything, just the important information we're looking at. Next is to truncate the back propagation. So instead of having whatever information it's sending to the next series, we can truncate what it's sending. We can lower that particular set of layers, make those smaller. And finally is a gradient clipping. So when we're training it, we can clip what that gradient looks like and narrow the training model that we're using. When you have a vanishing gradient, the opposite problem, we can take a look at weight initialization, very similar to the identity, but we're going to add more weights in there so it can identify different aspects of what's coming in better. Choosing the right activation function. That's huge. So we might be activating based on one thing and we need to limit that. We haven't talked too much about activation functions, so we'll look at that just minimally. There's a lot of choices out there. And then finally there's long short-term memory networks, the LSTMS. And we can make adjustments to that. So just like we can clip the gradient as it comes out, we can also expand on that. We can increase the memory network, the size of it, so it handles more information. And one of the most common problems in today's setup is what they call long-term dependencies. Suppose we try to predict the last word in the text. The clouds are in the, and you probably said sky. Here we do not need any further context. It's pretty clear that the last word is going to be sky. Suppose we try to predict the last word in the text. I have been staying in Spain for the last 10 years. I can speak fluent. Maybe you said Portuguese or French. No, you probably said Spanish. The word we predict will depend on the previous few words in context. Here we need the context of Spain to predict the last word in the text. It's possible that the gap between the relevant information and the point where it is needed to become very large. LSTMs help us solve this problem. So the LSTMs are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. All recurrent neural networks have the form of a chain of repeating modules, of neural network connections. In standard RNNs, this repeating module will have a very simple structure such as a single tangent H layer. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. LSTMS are a special kind of recurrent neural network, capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. As you can see, the deeper we dig into this, the more complicated the graphs get. In here, I want you to note that you have x at t minus 1 coming in, you have x at t coming in, and you have x at t plus 1. And you have h at t minus 1, and h at t coming in, and h at t plus 1 going out. And of course, on the other side is the output A. In the middle, we have our tangent H, but it occurs in 2 different places. So not only when we're computing the x at t plus 1 are we getting the tangent H from x at t, but we're also getting that value coming in from the x at t minus 1. So the short of it is as you look at these layers, not only does the propagate through the first layer, goes into the second layer and back into itself, but it's also going into the third layer. So now we're kind of stacking those up. And this can get very complicated as you grow that in size. It also grows in memory too, and in the amount of resources it takes. But it's a very powerful tool to help us address the problem of complicated, long sequential information coming in, like we were just looking at in the sentence. And when we're looking at our long short-term memory network, there's 3 steps of processing in the LSTMS that we look at. The first one is we want to forget irrelevant parts of the previous state. A lot of times, like, is, as, in, a, unless we're trying to look at whether it's a plural noun or not, they don't really play a huge part in the language, so we want to get rid of them. Then selectively update cell state values. So we only want to update the cell state values that reflect what we're working on. And finally, we want to only output certain parts of the cell state. So whatever's coming out, we want to limit what's going out too. And let's dig a little deeper into this. Let's just see what this really looks like. So step 1 decides how much of the past it should remember. First step in the LSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the sigmoid function. It looks at the previous state, h of t minus 1, and the current input, x of t, and computes the function. So you can see over here we have a function of t equals the sigmoid function of the weight of f, the h at t minus 1, and then x of t, plus, of course you have a bias in there with any of our neural networks, so we have a bias function. So f of t equals forget gate, decides which information to delete that is not important from the previous time step. Considering an LSTM is fed with the following inputs from the previous and present time step. Alice is good in physics. John, on the other hand, is good in chemistry. So, previous output. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our current input. So as we look at this, the first step is the forget gate realizes there might be a change in context after encountering the first full stop. Compares with the current input sentence of x of t. So we're looking at that full stop and then compares it with the input of the new sentence. The next sentence talks about John, so the information on Alice is deleted. Okay, that's important to know. So we have this input coming in, and if we're going to continue on with John, then that's going to be the primary information we're looking at. The position of the subject is vacated and is assigned to John. And so in this one, we've seen that we've weeded out a whole bunch of information, and we're only passing information on John, since that's now the new topic. So step 2 is then to decide how much should this unit add to the current state. In the second layer, there are 2 parts. One is the sigmoid function, and the other is the tangent h. In the sigmoid function, it decides which values to let through, 0 or 1. Tangent h function gives the weightage to the values which are passed, deciding their level of importance, -1 to 1. And you can see the 2 formulas that come up. The I of t equals the sigmoid of the weight of I, h of t minus 1, x of t plus the bias of I. And the c of t equals the tangent of h of the weight of c of h of t minus 1, x of t plus the bias of c. So our I of t equals the input gate, determines which information to let through based on its significance in the current time step. If this seems a little complicated, don't worry, because a lot of the programming is already done when we get to the case study. Understanding, though, that this is part of the program is important when you're trying to figure out what to set your settings at. You should also note when you're looking at this, it should have some semblance to your forward propagation neural networks, where we have a value assigned to a weight plus a bias. Very important steps in any of the neural network layers, whether we're propagating into the information from one to the next, or we're just doing a straightforward neural network propagation. Let's take a quick look at this, what it looks like from the human standpoint, as I step out of my suit again. Consider the current input at x of t. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our input. Input gate analyzes the important information. John plays football and he was a captain of his college team is important. He told me over the phone yesterday is less important, hence it is forgotten. This process of adding some new information can be done via the input gate. Now this example is as a human form, and we'll look at training this stuff in just a minute. But as a human being, if I wanted to get this information from a conversation, maybe it's a Google Voice listening in on you or something like that, how do we weed out the information that he was talking to me on the phone yesterday? Well, I don't want to memorize that he talked to me on the phone yesterday, or maybe that is important. But in this case, it's not. I want to know that he was the captain of the football team. I want to know that he served. I want to know that John plays football and he was the captain of the college football team. Those are the two things that I want to take away as a human being. Again, we measure a lot of this from the human viewpoint, and that's also how we try to train them so we can understand these neural networks. Finally, we get to step 3, decides what part of the current cell state makes it to the output. The third step is to decide what will be our output. First, we run a sigmoid layer, which decides what parts of the cell state make it to the output. Then we put the cell state through the tangent h to push the values to be between -1 and 1, and multiply it by the output of the sigmoid gate. So when we talk about the output of t, we set that equal to the sigmoid of the weight of 0 of the h of t minus 1, back one step in time, by the x of t, plus of course the bias. The h of t equals the out of t times the tangent h of c of t. So our O of t equals the output gate, allows the passed in information to impact the output in the current time step. Let's consider the example to predicting the next word in the sentence. John played tremendously well against the opponent and won for his team. For his contributions, Brave blank was awarded player of the match. There are going to be a lot of choices for the empty space. Current input, Brave, is an adjective. Adjectives describe a noun. John could be the best output after Brave. Thumbs up for John, awarded player of the match. And if you were to pull just the nouns out of the sentence, team doesn't look right because that's not really the subject we're talking about. Contributions, brave contributions, or brave team, brave player, brave match. So you look at this and you can start to train this neural network. So it starts looking at it and goes, oh no, John is what we're talking about. So brave is an adjective. John's going to be the best output. And we give John a big thumbs up. And then of course we jump into my favorite part, the case study. Use case implementation of LSTM. Let's predict the prices of stocks using the LSTM network based on the stock price data between 2012 and 2016. We're going to try to predict the stock prices of 2017. And this will be a narrow set of data. We're not going to do the whole stock market. It turns out that the New York Stock Exchange generates roughly 3 terabytes of data per day. That's all the different trades up and down of all the different stocks going on. And each individual one second to second or nanosecond to nanosecond. But we're going to limit that to just some very basic fundamental information. So don't think you're going to get rich off this today. But at least you can give a step forward in how to start processing something like stock prices, a very valid use for machine learning in today's markets. Use case implementation of LSTM. Let's dive in. We're going to import our libraries. We're going to import the training set and get the scaling going. Now, if you watch any of our other tutorials, a lot of these pieces just start to look very familiar because it's a very similar setup. But let's take a look at that. And just a reminder, we're going to be using Anaconda, the Jupyter Notebook. So here I have my Anaconda navigator. When we go under environments, I've actually set up a Keras Python 3.6. I'm in Python 3.6. And nice thing about Anaconda, especially the newer version, I remember a year ago messing with Anaconda in different versions of Python in different environments. Anaconda now has a nice interface. And I have this installed both on a Ubuntu Linux machine and on Windows, so it works fine on there. You can go in here and open a terminal window, and then in here, once you're in the terminal window, this is where you're going to start installing, using pip to install your different modules and everything. Now we've already pre-installed them, so we don't need to do that in here. But if you don't have them installed in your particular environment, you'll need to do that. And of course, you don't need to use the Anaconda or the Jupyter. You can use whatever favorite Python IDE you like. I'm just a big fan of this because it keeps all my stuff separate. You can see on this machine I have specifically installed one for Keras, since we're going to be working with Keras under TensorFlow. When we go back to home, I've gone up here to application, and that's the environment I've loaded on here, and then we'll click on the Launch Jupyter Notebook. Now I've already, in my Jupyter Notebook, have set up a lot of stuff so that we're ready to go. Kind of like Martha Stewart's in the old cooking shows. We want to make sure we have all our tools for you so you're not waiting for them to load. And if we go up here to where it says New, you can see where you can create a new Python 3. That's what we did here underneath the setup, so it already has all the modules installed on it. And I'm actually renamed this. If you go under File, you can rename it. I'm calling it RNN Stock. And let's just take a look at start diving into the code. Let's get into the exciting part. Now we've looked at the tool, and of course you might be using a different tool, which is fine. Let's start putting that code in there and seeing what those imports and uploading everything looks like. Now, first half is kind of boring when we hit the run button, because we're going to be importing NumPy as NP. That's the number Python, which is your NumPy array, and the matplot library, because we're going to do some plotting at the end, and our pandas for our data set. Our pandas as PD. And when I hit run, it really doesn't do anything except for load those modules. Just a quick note, let me just do a quick draw here. Oops, Shift-Alt, there we go. You'll notice when we're doing this setup, if I was to divide this up, oops, I'm going to actually, let's overlap these, here we go. This first part that we're going to do is our data prep. A lot of prepping involved. In fact, depending on what your system is, since we're using Keras, I put an overlap here, but you'll find that almost maybe even half of the code we do is all about the data prep. And the reason I overlap this with Keras, let me just put that down because that's what we're working in, is because Keras has like their own preset stuff, so it's already pre-built in, which is really nice. So there's a couple steps a lot of times that are in the Keras setup. We'll take a look at that to see what comes up in our code as we go through and look at stock. And then the last part is to evaluate. And if you're working with shareholders or classroom, whatever it is you're working with, the evaluate is the next biggest piece. So the actual code here, Keras is a little bit more, but when you're working with some of the other packages, you might have like 3 lines. That might be it. All your stuff is in your pre-processing and your data. Since Keras is cutting edge and you load the individual layers, you'll see that there's a few more lines here and Keras is a little bit more robust. And then you spend a lot of times, like I said, with the evaluate, you want to have something you present to everybody else and say, hey, this is what I did, this is what it looks like. So let's go through those steps. This is like a kind of just general overview. And let's just take a look and see what the next set of code looks like. And in here we have a dataset train, and it's going to be read using the PD, or pandas, .read_CSV, and it's the Google stock price train.csv. And so under this we have training set equals dataset train.iLocation, and we've kind of sorted out part of that. So what's going on here? Let's just take a look at it. Let's look at the actual file and see what's going on there. Now if we look at this, ignore all the extra files on this, I already have a train and a test set where it's sorted out. This is important to notice because a lot of times we do that as part of the pre-processing of the data. We take 20% of the data out so we can test it, and then we train the rest of it. That's what we use to create our neural network. That way we can find out how good it is. But let's go ahead and just take a look and see what that looks like as far as the file itself. And I went ahead and just opened this up in a basic WordPad text editor just so we can take a look at it. Certainly you can open up an Excel or any other kind of spreadsheet. And we note that this is a comma-separated variables. We have a date, open, high, low, close, volume. This is the standard stuff that we import into our stock, and we're the most basic set of information you can look at in stock. It's all free to download. In this case, we downloaded it from Google. That's why we call it the Google stock price. And it specifically is Google. This is the Google stock values from, as you can see here, we started off at 1/3/2012. So when we look at this first setup up here, we have a dataset train equals PD_CSV. And if you noticed on the original frame, let me just go back there, they had it set to home Ubuntu downloads Google stock price train. I went ahead and changed that because we're in the same file where I'm running the code. So I've saved this particular Python code, and I don't need to go through any special paths or have the full path on there. And then of course we want to take out certain values in here. And you're going to notice that we're using our data set, and we're now in pandas. So pandas, basically it looks like a spreadsheet. And in this case we're going to do iLocation, which is going to get specific locations. The first value is going to show us that we're pulling all the rows in the data. And the second one is we're only going to look at columns 1 and 2. And if you remember here from our data, as we switch back on over, columns, we always start with 0, which is the date. And we're going to be looking at open and high, which would be 1 and 2. We'll just label that right there so you can see. Now, when you go back and do this, you certainly can extrapolate and do this on all the columns. But for the example, let's just limit a little bit here so that we can focus on just some key aspects of stock. And then we'll go up here and run the code. And again, I said the first half is very boring. Whenever you hit the run button, it doesn't do anything because we're still just loading the data and setting it up. Now that we've loaded our data, we want to go ahead and scale it. We want to do what they call feature scaling. And in here, we're going to pull it up from the sklearn or the skKit preprocessing import min-max scaler. And when you look at this, you got to remember that biases in our data, we want to get rid of that. So if you have something that's like a really high value, let's just draw a quick graph. And I have something here like maybe the stock has a value, one stock has a value of 100, and another stock has a value of 5. You start to get a bias between different stocks. And so when we do this, we go ahead and say, okay, 100 is going to be the max, and 5 is going to be the min, and then everything else goes, and then we change this, so we just squish it down. I like the word squish. So it's between 1 and 0. So 100 equals 1, or 1 equals 100, and 0 equals 5. And you can just multiply. It's usually just a simple multiplication we're using. Multiplication. So it's going to be minus 5 and then 100 divided, or 95 divided by 1. So, or whatever value is divided by 95. And once we've actually created our scale, we've telling us going to be from 0 to 1. We want to take our training set and we're going to create a training set scaled. And we're going to use our scaler, SC, and we're going to fit. We're going to fit and transform the training set. So we can now use the SC, this particular object, we'll use it later on our testing set. Because remember, we have to also scale that when we go to test our model and see how it works. And we'll go ahead and click on the run. Again, it's not going to have any output yet because we're just setting up all the variables. Okay, so we paste the data in here, and we're going to create the data structure with the 60 time steps and output. First note, we're running 60 time steps, and that is where this value here also comes in. So the first thing we do is we create our xtrain and ytrain variables, and we set them to an empty Python array. Very important to remember what kind of array we're in and what we're working with. And then we're going to come in here, we're going to go for I in range 60 to 1258. There's our 60 time steps. And the reason we want to do this is as we're adding the data in, there's nothing below the 60. So if we're going to use 60 time steps, we have to start at point 60 because it includes everything underneath of it. Otherwise, you'll get a pointer error. And then we're going to take our xtrain and we're going to append training set scaled. This is a scaled value between 0 and 1. And then as I is equal to 60, this value is going to be 60 minus 60 is 0. So this actually is 0 to I. So it's going to be 0 to 60, 1 to 61. Let me just circle this part right here. 1 to 61, 2 to 62, and so on and so on. And if you remember, I said 0 to 60. That's incorrect because it does not count. Remember, it starts at 0, so this is a count of 60. So it's actually 59. Important to remember that as we're looking at this. And then the second part of this that we're looking at, so if you remember correctly, here we go. We go from 0 to 59 of I, and then we have a comma, a 0 right here. And so finally, we're just going to look at the open value. Now, I know we did put it in there for 1 to 2. If you remember correctly, it doesn't count the second one, so it's just the open value we're looking at, just open. And then finally, we have ytrain.append training set I to 0. And if you remember correctly, I comma 0. If you remember correctly, this is 0 to 59, so there's 60 values in it. So when we do I down here, this is number 60. So we're going to do this is we're creating an array, and we have 0 to 59. And over here we have number 60, which is going into the ytrain. It's being appended on there. And then this just goes all the way up. So this is down here is 0 to 59, and we'll call it 60 since that's the value over here, and it goes all the way up to 1258. That's where this value here comes in. That's the length of the data we're loading. So we've loaded two arrays. We've loaded one array that has, which is filled with arrays from 0 to 59, and we loaded one array which is just the value. And what we're looking at, you want to think about this as a time sequence. Here's my open. What's the next one in the series? So we're looking at the Google stock, and each time it opens, we want to know what the next one, 0 through 59, what's 60? 1 through 60, what's 61? 2 through 62, what's 62? And so on going up. And then once we've loaded those in our for loop, we go ahead and take xtrain and ytrain equals np.array xtrain.nparray ytrain. We're just converting this back into a numpy array. That way we can use all the cool tools that we get with numpy array, including reshaping. So if we take a look and see what's going on here, we're going to take our xtrain, we're going to reshape it. Wow, what the heck does reshape mean? That means we have an array, if you remember correctly, so many numbers by 60. That's how wide it is. And so when you do xtrain.shape, that gets one of the shapes. And you get xtrain.shape of 1 gets the other shape. And we're just making sure the data is formatted correctly. And so you use this to pull the fact that it's 60 by, in this case, where's that value? 60 by 1199, 1258 minus 60, 1199, and we're making sure that that is shaped correctly. So the data is grouped into 1199 by 60 different arrays. And then the 1 on the end just means at the end, because when you're dealing with shapes and NumPy, they look at this as layers. And so the end layer needs to be 1 value. That's like the leaf of a tree, where this is the branch, and then it branches out some more, and then you get the leaf. np.reshape comes from and using the existing shapes to form it. We'll go ahead and run this piece of code. Again, there's no real output. And then we'll import our different Keras modules that we need. So from Keras models, we're going to import the sequential model. We're dealing with sequential data. We have our dense layers. We have actually 3 layers we're going to bring in. Our dense, our LSTM, which is what we're focusing on, and our dropout. And we'll discuss these 3 layers more in just a moment. But you do need with the LSTM, you do need the dropout, and then the final layer will be the dense. But let's go ahead and run this, and they'll import our modules. And you'll see we get an error on here. And if you read it closer, it's not actually an error, it's a warning. What does this warning mean? These things come up all the time when you're working with such cutting-edge modules that are completely being updated all the time. We're not going to worry too much about the warning. All it's saying is that the H5PY module, which is part of Keras, is going to be updated at some point. And if you're running new stuff on Keras and you start updating your Keras system, you better make sure that your H5Pi is updated too, otherwise you're going to have an error later on. And you can actually just run an update on the H5Pi now if you wanted to. Not a big deal, we're not going to worry about that today. And I said we were going to jump in and start looking at what those layers mean. I meant that. And we're going to start off with initializing the RNN, and then we'll start adding those layers in. And you'll see that we have the LSTM and then the dropout. LSTM, then dropout. LSTM, then dropout. What the heck is that doing? So let's explore that. We'll start by initializing the RNN, regressor equals sequential, because we're using the sequential model, and we'll run that and load that up. And then we're going to start adding our LSTM layer and some dropout regularization. And right there should be the cue, dropout regularization. And if we go back here and remember our exploding gradient, well, that's what we're talking about. The dropout drops out unnecessary data, so we're not just shifting huge amounts of data through the network. So we go in here, let's just go ahead and add this in. I'll go ahead and run this. And we had 3 of them, so let me go ahead and put all 3 of them in, and then we can go back over them. There's the second one, and let's put 1 more in. Oops, put that in, and we'll go ahead and put 2 more in. I said 1 more in, but it's actually 2 more in, and then let's add 1 more after that. And as you can see, each time I run these, they don't actually have an output. So let's take a closer look and see what's going on here. So we're going to add our first LSTM layer in here. We're going to have units 50. The units is the positive integer, and it's the dimensionality of the output space. This is what's going out into the next layer. So we might have 60 coming in, but we have 50 going out. We have a return sequence, because it is a sequence data, so we want to keep that true. And then you have to tell it what shape it's in. Well, we already know the shape by just going in here and looking at xtrain shape. So input shape equals the xtrain shape of 1, 1. It makes it real easy. You don't have to remember all the numbers that put in 60 or whatever else is in there. You just let it tell the regressor what model to use. And so we follow our STM with a dropout layer. Now, understanding the dropout layer is kind of exciting because one of the things that happens is we can overtrain our network. That means that our neural network will memorize such specific data that it has trouble predicting anything that's not in that specific realm. To fix for that, each time we run through the training mode, we're going to take 0.2 or 20% of our neurons and just turn them off. So we're only going to train on the other ones. And it's going to be random. That way, each time we pass through this, we don't overtrain. These nodes come back in the next training cycle. We randomly pick a different 20. And finally, I see a big difference as we go from the first to the second and third and fourth. The first thing is we don't have to input the shape. Because the shape's already, the output units is 50 here, the next step automatically knows this layer is putting out 50, and because it's the next layer, it automatically sets that and says, oh, 50 is coming out from our last layer. It's coming out, goes into the regressor, and of course we have our dropout. And that's what's coming into this one, and so on, and so on. And so the next 3 layers, we don't have to let it know what the shape is. It automatically understands that. And we're going to keep the units the same. We're still going to do 50 units. It's still a sequence coming through, 50 units and a sequence. Now, the next piece of code is what brings it all together. Let's go ahead and take a look at that. And we come in here, we put the output layer, the dense layer. And if you remember up here, we had the 3 layers. We had LSTM, dropout, and dense. Dense just says we're going to bring this all down into one output. Instead of putting out a sequence, we just want to know the answer at this point. And let's go ahead and run that. And so in here, you notice all we're doing is setting things up, one step at a time. So far, we've brought in our, way up here, we brought in our data, we brought in our different modules, we formatted the data for training it, we set it up, we have our X train and our Y train. We have our source of data and the answers we know so far that we're going to put in there. We've reshaped that. We've come in and built our Keras. We've imported our different layers. And we have in here, if you look, we have 5 total layers. Now, Keras is a little different than a lot of other systems because a lot of other systems put this all in one line and do it automatic, but they don't give you the options of how those layers interface, and they don't give you the options of how the data comes in. Keras is cutting edge for this reason. So even though there's a lot of extra steps in building the model, this has a huge impact on the output and what we can do with these new models from Keras. So we brought in our dense, we have our full model put together, our regressor. So we need to go ahead and compile it, and then we're going to go ahead and fit the data. We're going to compile the pieces so they all come together, and then we're going to run our training data on there and actually recreate our regressor so it's ready to be used. So let's go ahead and compile that, and I can go ahead and run that. And if you've been looking at any of our other tutorials on neural networks, you'll see we're going to use the optimizer Atom. Atom is optimized for big data. There's a couple other optimizers out there beyond the scope of this tutorial, but certainly Atom will work pretty good for this. And loss equals mean squared value. So when we're training it, this is what we want to base the loss on. How bad is our error? Well, we're going to use the mean squared value for our error and the Atom optimizer for its differential equations. You don't have to know the math behind them, but certainly it helps to know what they're doing and where they fit into the bigger models. And then finally we're going to do our fit, fitting the RNN to the training set. We have the regressor.fit, X-train, Y-train, epochs, and batch size. So we know where this is. This is our data coming in for the X-train. Our Y-train is the answer we're looking for of our data, our sequential input. Epochs is how many times we're going to go over the whole data set. We created a whole data set of X-train. So this is each of those rows, which includes a time sequence of 60. And batch size, another one of those things where Keras really shines, is if you were pulling this, say, from a large file, instead of trying to load it all into RAM, it can now pick smaller batches up and load those indirectly. We're not worried about pulling them off a file today because this isn't big enough to cause the computer too much of a problem to run, not too straining on the resources. But as we run this, you can imagine what would happen if I was doing a lot more than just one column in one set of stock, in this case Google stock. Imagine if I was doing this across all the stocks and I had, instead of just the open, I had open, close, high, low, and you can actually find yourself with about 13 different variables times 60 because there's a time sequence. Suddenly you find yourself with a gig of memory you're loading into your RAM, which will just completely, if you're not on multiple computers or cluster, you're going to start running into resource problems. But for this, we don't have to worry about that. So let's go ahead and run this, and this will actually take a little bit on my computer because it's an older laptop. and give it a second to kick in there. There we go. All right, so we have epic. So this is going to tell me it's running the first run through all the data, and as it's going through, it's batching them in 32 pieces, so 32 lines each time. And there's 1198. I think I said 1199 earlier, but it's 1198. I was off by 1. And each one of these is 13 seconds. So you can imagine this is roughly 20 to 30 minutes runtime on this computer. Like I said, it's an older laptop running at 0.9 gigahertz on a dual processor. And that's fine. What we'll do is I'll go ahead and stop, go get a drink of coffee, and come back, and let's see what happens at the end and where this takes us. And like any good cooking show, I've gotten my latte. I also had some other stuff running in the background, so you'll see these numbers jumped up to like 19 seconds, 15 seconds. But you can scroll through and you can see we've run it through 100 steps, or 100 epics. So the question is, what does all this mean? One of the first things you'll notice is that our loss is over here. It kind of stopped at 0.0014, but you can see it kind of goes down until we hit about 0.014 3 times in a row. So we guessed our epic pretty close, since our loss has remained the same on there. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, dataset test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open, stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, dataset test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open, stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data because that's part of the next data, or it's actually the top 59. So that's what this first setup is over here, is where we're going in, we're doing the real stock price, and we're going to just take the data set test and we're going to load that in. And then the real stock price is our data test location. So we're just looking at that first column, the open price. And then our data set total, we're going to take pandas and we're going to concat. And we're going to take our data set train for the open and our data set test open. And this is one way you can reference these columns. We've referenced them a couple different ways. We've referenced them up here with the 1, 2. But we know it's labeled as a panda set as open. So pandas is great that way. Lots of versatility there. And we'll go ahead and go back up here and run this. There we go. And you'll notice this is the same as what we did before. We have our open data set. We appended our two different, or concatenated our two data sets together. We have our inputs equals data set total length, data set total minus length of data set minus test minus 60 values. So we're going to run this over all of them. And you'll see why this works. Because normally when you're running your test set versus your training set, you run them completely separate. But when we graph this, you'll see that we'll be looking at the part that we didn't train it with to see how well it graphs. And we have our inputs equals inputs dot reshape, so reshaping like we did before. We're transforming our inputs. So if you remember from the transform between 0 and 1. And finally we want to go ahead and take our x test, and we're going to create that x test, and for I in range 60 to 80. So here's our x test, and we're appending our inputs I to 60, which remember is 0 to 59, and I comma 0 on the other side. So it's just the first column, which is our open column. And once again, we take our x test, we convert it to a numpy array. We do the same reshape we did before, and then we get down to the final two lines, and here we have something new. Right here on these last two lines, let me just highlight those or mark them. Predicted stock price equals regressor.predicts x test. So we're predicting all the stock, including both the training and the testing model here. And then we want to take this prediction and we want to inverse the transform. So remember, we put them between 0 and 1. Well, that's not going to mean very much to me to look at a float number between 0 and 1. I want the dollar amounts. I want to know what the cash value is. And we'll go ahead and run this, and you'll see it runs much quicker than the training. That's what's so wonderful about these neural networks. Once you put them together, it takes just a second to run the same neural network that took us, what, a half hour to train? Head and plot the data. We're going to plot what we think it's going to be, and we're going to plot it against the real data, what the Google stock actually did. So let's go ahead and take a look at that in code. And let's pull this code up. So we have our PLT. That's our, if you remember from the very beginning, let me just go back up to the top. We have our matplotlibary.pyplot as PLT. That's where that comes in. And we come down here, we're going to plot, and let me get my drawing thing out again. We're going to go ahead, and PLT is basically kind of like an object. It's one of the things that always threw me when I'm doing graphs in Python, because I always think you have to create an object, and then it loads that class in there. Well, in this case, PLT is like a canvas you're putting stuff on. So if you've done HTML5, you'll have the canvas object. This is the canvas. So we're going to plot the real stock price. That's what it actually is. And we're going to give that color red, so it's going to be in bright red. We're going to label it real Google stock price. And then we're going to do our predicted stock, and we're going to do it in blue, and it's going to be labeled predicted. And we'll give it a title, because it's always nice to give a title to your graph, especially if you're going to present this to somebody, to your shareholders in the office. And the X label is going to be time, because it's a time series. And we didn't actually put the actual date and times on here, but that's fine. We just know they're incremented by time. And then, of course, the Y label is the actual stock price. PLT.legend tells us to build the legend on here so that the color red and real Google stock price show up on there. And then the plot shows us that actual graph. So let's go ahead and run this and see what that looks like. And you can see here we have a nice graph, and let's talk just a little bit about this graph before we wrap it up. Here's our legend I was telling you about. That's why we have the legend to show the prices. We have our title and everything. And you'll notice on the bottom we have a time sequence. We didn't put the actual time in here. Now we could have. We could have gone ahead and plotted the X, since we know what the dates are, and plotted this to dates. But we also know that it's only the last piece of data that we're looking at. So last piece of data, which ends somewhere probably around here on the graph, I think it's like about 20% of the data, probably less than that. We have the Google price, and the Google price has this little up jump and then down, and you'll see that the actual Google, instead of a turn down here, just didn't go up as high and didn't go down. So our prediction has the same pattern, but the overall value is pretty far off as far as stock. But then again, we're only looking at one column. We're only looking at the open price. We're not looking at how many volumes were traded. And like I was pointing out earlier, when we talk about stock, just right off the bat, there's 6 columns. There's open, high, low, close, volume. Then there's how many volume shares. Then there's the adjusted open, adjusted high, adjusted low, adjusted close. They have a special formula to predict exactly what it would really be worth based on the value of the stock. And then from there, there's all kinds of other stuff you can put in here. So we're only looking at one small aspect, the opening price of the stock. And as you can see here, we did a pretty good job. This curve follows the curve pretty well. It has like little jumps on it, bends. They don't quite match up. So this bin here does not quite match up with that bin there, but it's pretty darn close. We have the basic shape of it, and the prediction isn't too far off. And you can imagine that as we add more data in and look at different aspects in the specific domain of stock, we should be able to get a better representation each time we drill in deeper. Of course, this took a half hour for my computer to train, so you can imagine that if I was running it across all those different variables, it might take a little bit longer to train the data. Not so good for doing a quick tutorial like this. So we covered a lot of really cool things in this tutorial today. Hopefully you'll be able to get rich predicting stock, or maybe get a job if you are familiar with the stock domain and business domain. But you can see how this can be applied to all kinds of different tools and trades across different domains. So the biggest takeaways are we had an introduction to the RNN and its setup on there. We went over the popular neural networks that are out there. We discussed what is a recurrent neural network. We went into one of the big problems with the RNN, and that's the exploding gradient problem. We also discussed the long short-term memory networks, which is part of what we're working on. That's the LST, which is part of the RNN setup. And finally, we went through and we predicted the Google stock to see how it did.
Did you know that within just a few lines of code, you can transform an AI model into something far more powerful? Something that responds to questions, connects to live data, pull insights from databases, and even interacts with other apps in real time. That's what LangChain allows you to do. And it's quickly becoming the go-to framework for AI developers. Think about this, you're about to create something amazing, an AI that can think, learn, and grow in ways we once only dreamed of. And here's the best part. You don't need to be an AI expert to make that happen. LangChain is like a toolkit that connects the most advanced large language models like OpenAI's GPT to real-time data, allowing you to build AI applications that are smart, flexible, and highly interactive. LangChain is more than just a way to make AI development easier. It's a framework that allows different language models to work together seamlessly. So whether you want to understand user questions with one LLM, create human-like responses with another, or pull in data from an API or a database, LangChain makes all possible. The framework takes care of heavy lifting, connecting models, managing data flows, and even customizing how your AI interacts with external sources. Now the question is, why is LangChain so popular? It has become one of the most fastest growing open source projects because it's solving a huge problem for developers. The challenge of integrating generative AI and LLMs with external data and complex workflows. As AI becomes more central to our lives in 2024, LangChain is helping developers create smarter, more powerful applications. So whether it's just for chatbots, content creation, or advanced data analysis. In this tutorial, I'll show you exactly how to get started with LangChain, from setting up your environment to building the first AI-powered app. I'll walk you through it. So LangChain makes it possible to train models on our own custom data, opening up more possibilities for building specialized intelligent applications. By the end of this video, you will be ready to start building with LangChain, and trust me, once you see how easy it is, you'll wonder why you didn't start using it sooner. Let's start with a simple question. Why should we use LangChain? Imagine you're working with large language models like GPT-4 or Hugging Face models, and you want to take their capabilities further, like integrating them with your own data sources or allowing them to take action based on information they retrieve. This is where LangChain comes in. LangChain is like an open source framework that allows you to build intelligent applications by connecting large language models with external data sources. It can turn static AI interactions into dynamic, data-aware workflows. One of the best parts is you don't have to manually code everything from scratch. LangChain abstracts away much more complexity of working with LLMs, allowing developers to focus on building functional applications instead of wrangling API calls and managing data pipelines. So LangChain is set to play an even bigger role in AI development because it enables you to harness true power of generative AI by connecting it with real-time data and external tools. So now we have understood what LangChain is. Let us now understand how to install LangChain. So let's start with the installation of LangChain. We'll just simply go to the website, and docs part, and we'll just read through this documentation. So here it has explained what LangChain is and what are the framework consisting of. So we also have these tutorials on how do we install LangChain? Okay, so for installing, you can just simply click on this quick start and see here it has written how do we set up on Jupyter Notebook. So this is the command if you want to install LangChain. We will use the pip command. So just simply you can copy this command pip install LangChain, and you have to open your command prompt or the terminal in your computer, and here you have to simply copy paste the command. So as you can see, it will load all the packages which is required for installing LangChain. So you can see your requirement already satisfied. This is because I had already installed my LangChain before. So we have understood how to install this LangChain by using this command, and you can also install the LLM chain. We'll understand it later. Now let me just show you what else you need to install. First, we have understood this LangChain. Then we have the Pinecone client. So we'll just simply search here Pinecone client, and it will redirect us to this page. So Pinecone client is actually a vector store for storing and retrieving embeddings, which we will use in the later steps. So Pinecone is also used to actually, create secret API keys. So here you can also create the API keys. You can also read the documentation part. So we'll understand how to create API keys using OpenAI. But first, let us install Pinecone client in our system. So we'll again go to command prompt this terminal, and we'll just copy paste pip install Pinecone client. So you can see here it will download and install all the packages required. So it has been installed. Now the third thing we are talking about is OpenAI client. So we'll use OpenAI models for a large language task. So we'll just simply search here OpenAI. Okay, and so it has redirected us to this page, OpenAI platform. And okay, before starting this, so this is the platform here where you can create, export an API key in OpenAI. Okay, so you can see here overview, quick start, concept, everything is there. And to create an API key, we'll just simply click here, and here you have to select this option, create a new secret key. Suppose I give my secret key name, anything you can give. Suppose I give test 1, 2, 3. Okay, and permissions is all, and we create the secret key. Now you need to actually save your key. We'll just copy this key because it will be required later while debugging the code. So we will just copy paste this secret key. We will require it later, and then done. So these are the keys I have created. So actually ChatGPT and other LLM models like OpenAI and Hugging Face uses LangChain to integrate with other APIs to create your own custom LLM models or chatbots. So suppose here we have logged in our ChatGPT here, and if I search here who won the WTC World Cup in 2023. So here it has shown the answer, but for example, if I search who won the cricket match World Cup So here, as you can see, the ChatGPT has given answer as my last knowledge update, the 2024 Men's World Cup has not taken place yet. This is happening because this ChatGPT older version has not been trained on the latest upcoming news or whatever the new technology is. So by using LangChain, you can integrate with other APIs and you can create your own customized LLM models or chatbots, which help you to train your own custom data using various tools and APIs. So before we move on, I've already showed you how to create the secret API key and how you have to store the API key address. So first we have already understood how do we install LangChain here. So by using the pip command, we do it. And so you also need to install Python 3.8 or later installed in your system. So I already have Python installed. And to check that, you can just simply, I already have it installed in my system. So to check that, I'll simply just type here Python -- version and click enter. So as you can see, it has shown me the Python version which is installed in my computer. So the second step is already we have discussed, which is OpenAI API key here. So second step, we have already discussed how do we create our OpenAI API key. So we have to sign up in our OpenAI, then go to the API keys section and then create a new secret key. And these are the keys I have created, and you can just keep it later. Later you'll use that. So now we'll come to the third step, which is create a project directory and setup. So what we do is we have Jupyter installed in our system. So we'll just go to command prompt here and type JUPY, Jupyter Notebook. So it will redirect us to the Jupyter Notebook installed in our system. So if not, we can just simply go from here. It is loading right now, we have to wait. Now you just need to click on this new and Python 3 IPy kernel, because Python is being installed in my system. So we will use Python as our kernel here. And here you can just give the prompts, the command. Before that, you have to create a Python file, which we can also create this Python file in Visual Studio Code. Just simply go to Visual Studio Code here and just simply click on File, New File, and I'll just type here python.py. And you can you have to first store the API key. For this, we use the command open AI underscore API underscore key equal to, and just give your secret key. Okay, you can just simply copy paste here your secret key and just store this. So this ensures that your API key is stored securely and it can be used whenever needed. Now the step 4 is to initialize a project and install the required libraries. So you need to add some additional libraries like Streamlit to make a user interface. So let's add that too in our project folder. You can either create a text file named requirements.txt and then install all these. We have already installed the OpenAI LangChain. We just need to install Streamlit. So here you can just give the command pip install Streamlit. So as you can see, this I have already installed Streamlit before. Same wise, you can also install OpenAI if it is not installed in your system using the command terminal, the Windows PowerShell. So we have understood this, what all packages and what all we need to install. Now the next step is to build your first LangChain app. To create a simple app which uses a input query and the app will generate a response using OpenAI's GPT model. So you have to create a Python file named main.py here. So as you can see, I've already imported this main.py, and this is my code here. Import Streamlit as st from LangChain and the constants I have created, and then I have initialized the OpenAI with our API key. So you have to just type this prompt here. I'm using VS Code here. You can also do it in your Jupyter Notebook. And then to create the Streamlit app, you have to give a title, LangChain demo with OpenAI. So this is the title I have provided. And then the text input for prompt. The prompt is st.text input and enter a prompt. You can just type enter a prompt or whatever you wish to. And then display the response. So if prompt response is LLM.predict prompt, so you can use the predict method for LLM. So here what the app will, so after creating and debugging this in the terminal, so your app will initialize OpenAI using your API key, and the user inputs a prompt through the Streamlit interface. LangChain processes the input and sends it to the OpenAI's GPT model, and the AI generates a response which is then displayed in the app. So now you can use all these prompts to run on your app. So to do this, you can just, to see your app in action, you can just go to the terminal and run the following command, which is streamlit run main.py. So you can just simply go to the terminal here and just simply type the command, which is streamlit run main.py. So by giving this prompt, a new tab in your browser will open displaying the app, and you can also type any question into the input box. So now we have understood all these steps. So this was a quite basic tutorial on how to install LangChain and then, integrate it with the app. You can also customize and expand. So LangChain's flexibility allows you to integrate other APIs also, external data sources, or even add memory to your AI application. So whether you're building a simple chatbot or more complex AI system, the possibilities are endless. So by following all these steps, you will have a fully functioning app running in your system in no time.
So let's start with what is LangGraph. LangGraph is an AI agent framework built by the team behind LangChain. It's designed to let you build complex workflows that involve one or more language models and lets the LLM decide what happens next in the flow. It's highly flexible, supports both Python and JavaScript, and has been growing in the popularity since its release in October 2023. Especially, it's an alternative to other agent frameworks like Crew AI or Microsoft AutoGen. Now that we have a basic understanding on what LangGraph is, let's focus on an example to understand the working principles involved, like decision made referring to the knowledge bases and requirement of human intervention. So how does it works in practice? Let's take an example. Imagine a virtual assistant for a healthcare clinic. A patient sends a message asking to book appointment. The agent might check the patient's medical history, suggest available time slots based on their doctor's schedule. The agent can even pre-fill a form to request a prescription renewal. But let's say the patient is requesting medication that requires doctor's approval. In this case, we need a human doctor or a nurse to review the request before moving forward. LangGraph makes it easy with human-in-the-loop execution, where the workflow can pause, wait for human input, and then continue automatically once it's approved. But let's say it's a critical medication. We probably want a real human doctor to approve it before it's directed to the patient. So guys, LangGraph actually makes this easy using human-in-the-loop execution, so the flow can pause, wait for human input, and then continue. Now that we have a clear understanding of the working principles, and also it's not just the medical support, but also there are a wide range of applications. Let's go through them. Now, let us explore where LangGraph can be useful. The first one is copywriting, generating content by pulling data from multiple sources. LangGraph can combine research from web articles, product specs, and previous campaigns to create high-quality blog posts, ads, or email content automatically. Then you can find its use case in custom analytics, like creating dashboard, summaries, or extracting insights from a database. You can build agents that query databases, clean process data, then generate natural language summaries or visual reports without manual intervention. Finally, you have customer assistants, where you can answer queries via email, WhatsApp, SMS, or even voice. LangGraph can handle multi-channel conversation, maintain context across threads, and escalate issues to a human if needed, all within a seamless flow. You can get personalized recommendations, tailored suggestions based on past user interactions also. By analyzing users' behavior, purchase history, or preferences, LangGraph agents can offer dynamic, relevant suggestions in the real time, improving user engagement. You can also use in research and trend monitoring, like staying up to date with new articles or developments. You can also find its use case in recommendations, like personalized recommendation, which are tailored suggestions based on the past user's interaction. By analyzing user behavior, purchase history, or preferences, LangGraph agents can offer dynamic, relevant suggestions in real time, improving users' engagement. Then you can find in research and trend monitoring. You can stay up to date with the new articles or developments. Agents can continuously monitor specific topics or keywords, summarize key insights, and deliver timely updates to user or internal teams. And finally, in personalized marketing, like crafting messages that match each customer's preferences. LangGraph can generate individualized marketing emails, SMS, or ad copy that reflects each customer's interest, tone, and behavior, boosting response rates. Now you might be wondering, these automations can be done with the help of any other alternatives available in the market. In fact, few of them have already set benchmarks in different domains. So now you'd be wondering what makes LangGraph so special. So let us discuss some of the features of LangGraph. The first one is built-in streaming. LangGraph supports token or message level streaming right off the box, allowing faster and more responsive interactions in real time. Moving the second one, we have async execution. So async execution enables multiple steps to run in parallel, making workflows more efficient and reducing wait times. That brings us to the third feature. The third feature here is persistence. So if I talk about persistence, LangGraph lets you store and reload certain graph state using database. So agents can maintain context even across different sessions of failure. Fourth one is fault tolerance. Imagine one of your workflow tools is inactive or not operational, and your entire flow is disrupted and cannot be fixed unless you restart the flow. But things are different in LangGraph. It helps you by automatically handling call failures. Fifth one, we have human in the loop. So the next feature, if I'm going to talk about, LangGraph supports pausing the workflow, then seamlessly resuming once the human has responded. And we have already understood that in very first example where an AI medical assistant waits for human in loop approach before recommending medication to a patient. Now this brings us to the last feature of the LangGraph, that is state management. LangGraph simplifies decision making by keeping track of all the inputs, outputs, and context variables throughout the entire flow. With the features now we have discussed, let's shift to architecture of LangGraph, or simply put, the core building blocks of LangGraph. So what are the core building blocks of LangGraph? Every LangGraph has the following main component. Let's begin with the first one. First one that we have is nodes. Nodes are like building blocks of your graph, where each code performs a specific function or piece of logic, such as calling an API, processing data, or generating text. Next one that we have all over here is edges. Edges act as connectors that determine the order of execution, ensuring data and control move smoothly from one node to the next. Proceeding further, we have a slightly smarter type of edge that's called conditional edge. The name speaks for itself. Conditional edge add intelligence by branching the workflow, choosing the next step dynamically based on conditions or the current state of information. Lastly, we have a state. State works as shared memory space that tracks of all the inputs, outputs, and variables, ensuring different individual nodes that can access and update information accordingly and consistently. Next, let us dive into powerful architectures. So these are the powerful architectures that are supported. First, we'll go through the router architecture. Router act like traffic controllers, applying conditional logic to decide which prompt, tool, or branch of the workflow should be executed next. Proceeding next one, we have React-style agent architecture. React-style agents follow a reasoning action observation loop where LLM itself chooses the right tool, executes it, and uses the tool's output to refine its next step. Last but not the least, we have reflection patterns. Reflection patterns introduce a review mechanism where one LLM generates content and another LLM evaluates, critiques, and improves it for higher accuracy. With that discussed, let's dive into a practical example for better learning experience. This project is actually designed to read through text and figure out if it's talking about the weather. Not only that, it can pull something like location, temperature, conditions, and even the time. The best part, it works offline with simple rules. And it gets smarter if you connect it to an open API key. You can run it directly from the command line and output the result as JSON object and use the clean web interface to test it on your browser. This tool works in two ways: offline using built-in rules and heuristics, or online with open API key, where LLM makes the decision and extractions more accurate. So guys, you can run it through a simple command line tool or analyze text or files. You can even output result as structured JSON objects. For those who prefer the visual, here is the UI interface you can see, and where you just type the text and see the results. The setup is straightforward with Python, and the project is organized into graphs, heuristics, and simple inputs. Since including an LLM can cost you, so we went rather a simple approach which we can bypass the API keys and even without API key, the project still works, just smarter with the one. The basic requirement for this project is ID and a programming language. The ID we'll be using is called cursor.ai. As you can see, you can download and run this repository on any ID of your choice, like VS Code or Jupyter Notebook. So let's get started with the first file. Our first file here, as you can see, is requirement.txt. This will help us learn about the requirements needed to get started with the project. To run this project, we need a few Python libraries. These include LangGraph, LangChain for building workflow, LangChain OpenAI for LLM support, and Pydantic for handling data models. We'll also use .env to manage environment variables. Finally, the web interface runs on FastAPI, UVCon, and also Jinja 2. Now, let us proceed to the static files. Here we will understand HTML, CSS styles we need to execute this project on. Basically, we will executing this on localhost. To keep it short, this project includes a simple styling setup to make the web interface clean and easy to use. The background is set to dark theme with accent colors for highlight and also muted tones for readability. Forms, buttons, and cards are designed with rounded corners and spacing, giving it a modern and minimal look. Error messages are styled separately, so they stand out clearly. Now let us discuss the command line interface file. This project comes along with a command line interface built using Typer and Rich. With the analyze command, you can analyze a text or a file which contains weather report and see details like location, temperature, conditions, and time. You can print the result in minimal and a nice table. So as you can see, as a raw JSON needed, there is also a current command that fetches the live weather data for any given city using OpenMeteor. This makes it easy to test the workflow directly from your terminal and without needing the web UI. Now let us discuss the app.py file. This is the FastAI web app for the project. It serves a simple homepage where you can enter a location and shows a weather report using clean template. Behind the scene, guys, it uses fetch current weather function to get the live weather data and display its result on the page. Static files and templates are neatly organized, making the web interface lightly and easy to use. Think of this app file as a front desk where users type their query and the backend fetches the actual weather report. Now, let us discuss lives.py. This file handles the live weather data. First, it uses the OpenMeteor geocoding API to turn a city name into latitude and longitude. Then it fetches the current weather for those coordinates, like temperature, wind, and conditions. If the city isn't found, it returns a simple error message. This is a part of the project that connects the workflow to a real-world weather data. This is the most important part of our file. So let us elaborate based on the code blocks. First, there you can see we have the imports HTTPX for making API calls. Next, you can see here we have defined async def geocode city. So this is a helper function which we call it as geocode city. It takes in a city name, calls OpenMeteor geocoding API, and then it returns latitude and longitude for that city. Then we have all over here main function fetch current weather. It first calls geocoding function to get the city's coordinate. If the city isn't found, then it returns the error. And if the city exists, it makes another API call. This API call goes to OpenMeteor forecast API, and this time it's asking for the current weather. Finally, it builds up a dictionary with the city name, coordinates, and the current weather data, and it sends it back. So you can see all over here. So guys, the flow is simple. It takes the city, finds coordinates, fetch the live weather, and returns a structured data. Now, all you have to do is, guys, just run this project. You can type a prompt or the agent window of the Cursor AI to execute this project on the local host. So let's get to the execution phase. This might take a little bit of time. Just a moment while it shoots the localhost address. There you go. You have the localhost address. We can either click as the link is, or we can copy and paste the same URL on the browser. I will use Google Chrome. Now we have a page to enter a location. And there you go. You have the weather report for the given location.
So, what exactly is LangChain? LangChain is an open source framework designed to help developers build applications powered by large language models by providing tools and abstractions to simplify the process of integrating LLMs with external data sources and workflows. Now, imagine you're building an AI application where an LLM model like GPT-4 is needed to generate an initial response to your query. Llama 3 or other versions to refine that response. A custom-built AI agent to decide whether it can answer the query without a hiccup or if it has to fetch external sources to generate a response. Most importantly, a solid memory to store all previous user interactions. Without LangChain, managing all these components manually would require extensive coding. You need to write a custom code snippet to handle API calls to your LLM, like GPT, Llama, create and maintain a dedicated memory space, and most importantly, a fully customized decision-making capable AI agent. Yet in scenarios where you can see an opportunity to scale it up, the possibilities are questionable. This approach leads to a lot of boilerplate code and makes the system complex. LangChain simplifies this by providing an open source framework that helps developers build applications powered by large language models. It enables training prompts, interacting with external data, and adding memory for contextual understanding. Now, let's discuss some of the key features of LangChain. Firstly, LLM support. It works with both closed source GPT-4 and open source models like Llama 3 with simple API integrations. Prompt templates. It allows dynamic prompt customization instead of hard coding queries. Third one is chains. It helps connect multiple tasks like querying an LLM, retrieving data, and processing responses in a seamless workflow. Fourth one is indexes. Supports document loaders and vector databases to pull in external data. Fifth one is memory. It enables applications to retain past interactions, improving contextual awareness. And lastly, the agents. It uses LLMs as reasoning engines to dynamically decide the next step in the workflow. With LangChain, developers can efficiently build AI-powered applications without reinventing the wheel. You can have a detailed briefing on LangChain on the official website. Also, should you wish to try it out, take a quick look at Quick Start page to steps to follow to set up the environment and run LangChain in your local system. Now, let's proceed with the next one in this tutorial, which is LangGraph. So what exactly is LangGraph? By definition, LangGraph is a library within the LangChain's ecosystem. It is a framework for building and managing complex stateful multi-agent LLM applications by modeling workflows as graphs, where nodes represent tasks or states and edges represent a transition between them. Now, let us imagine this. You are in a situation where you need to work with not one, but multiple agents in parallel. But LangChain can just assist you with one. You need much more enhanced platform for this. That's where LangGraph comes into the picture. LangGraph is built upon the existing LangChain and designed for managing agents and multi-agent workflows. While LangChain is excellent for chaining prompts, LangGraph excels at handling structured interactions between multiple agents. If you are building a system where multiple agents collaborate, such as a research assistant or an automation workflow, LangGraph is a great choice. So let's discuss these core components of LangGraph. First one, state. A state is a shared data structure that stores user inputs, agent outcomes, and workflows history. Now, the next one is nodes. You can have one node or also multiple nodes. These nodes are individual components or actions that execute LLM calls, run functions, or interact with external tools. Now, let's go to the third part, which is edges. Edges are nothing but connections between nodes that define execution flow. Unlike traditional directed graphs, nodes in LangGraph can dynamically decide which node to call next. That means the control flow can go in both ways. LangGraph is ideal when you need agents to interact in cyclical workflows or collaborate on complex tasks. You can have a detailed briefing on LangGraph on the official website. Also, should you wish to try it out, take a quick look at the quick start. Using LangGraph is straightforward. You just need to install the package, import it onto your project, and then using the provided classes, you can straightly access LangGraph. Now, let's proceed to the next one, which is LangFlow. Now, what is LangFlow? LangFlow is a visual, low-code framework built upon top of LangChain, enabling developers to easily design and test AI applications, especially those involving multi-agent systems and retrieval augmented generation or RAG. Now, imagine building AI-powered applications like chatbots or data processing tools without writing any code. LangFlow makes this possible with the drag and drop interface. LangFlow is built upon top of LangChain and provides a visual interface for designing LangChain workflows. It is perfect for prototyping LLM applications, allowing users to quickly design workflows, chains, and agents and test them. However, it is not intended for production use, but it is excellent for MVPs, which is minimum viable products. LangFlow is designed to simplify AI-powered app development by providing a drag-and-drop interface. It enables developers to visually design, experiment with, and test LangChain-based workflows. Now, what makes LangFlow different from LangChain and LangGraph? Why use LangFlow? So, there are three major reasons. Firstly, no coding required. Perfect for prototyping AI applications without having to write any code. Second one, visual workflow builder. You can easily design chains, agents, and integrations. Thirdly, quick prototyping. Best suited for MVPs, experimentation, and non-production use cases. So there are two main ways to use LangFlow. First one, via DataStax, a paid cloud-hosted option. Second one, self-hosted. Install locally or on your own cloud server. So once deployed, LangFlow provides a UI where you can drag and connect various components, enabling you to build and test AI workflows seamlessly. You can have a detailed briefing on LangFlow on the official website. Also, should you wish to try it out, take a quick look at Quick Start to work on setting up LangFlow in your local environment. You just need to install the package, import it onto your project, and start using the provided classes. Now, let's move on to the last one, which is LangSmith. So what exactly is LangSmith? So LangSmith is a platform developed by LangChain, designed to streamline the development, testing, debugging, and monitoring of LLM applications, offering tools for observability, evaluation, and prompt engineering. The LLM, Gen AI, AI agents, all the hype was a huge hit. Everybody is interested in developing a custom AI agent to automate and optimize all the redundant CRM tasks and much more. But building an LLM-based application or AI agent is just the beginning. Monitoring, testing, and optimizing are equally crucial. LangSmith is designed to help developers at every stage of an AI application's lifecycle, from prototyping to production. Now, why use LangSmith? So there are three important reasons. Firstly, performance monitoring. It tracks API calls, token usage, errors, and latency. Second one, debugging and evaluation. It ensures models return expected results and avoid unnecessary API costs. Lastly, independent framework. It works with any LLM framework, not just the LangChain-based ones. If your application requires extensive monitoring, debugging, or optimization, LangSmith is a great tool. However, for simple applications without complex tracking needs, it might not be necessary. To integrate LangChain, install the package, set up the environment variables, and use traceable annotations in your code. The LangSmith dashboard provides insights into performance metrics, including token usage, call trends, and error rates. For more details on LangSmith, visit the official page of LangSmith. Also, should you wish to try it out, take a look at the quick start to work on setting up LangSmith in your local environment. You just need to install the package, import it into your project, and start using the provided classes. We will get started by a brief introduction to LLMs and chatbots. Later, we will dive into setting up the development environment. Then, we will understand data collection and preparation. Followed by that, we will understand the implementation of LLMs. Later, we will check into chunking and embedding for vector search or RAG. Followed by that, we will learn implementing query processing and recommendations. Next, we have zero-shot text classification, and lastly, the sentiment analysis with LLMs. Hope I made myself clear with the agenda. Now handing over the session to our experts.
Hi, welcome all. Welcome to Simplilearn session on how to create LLM chatbot. In this course, we are going to talk about what is LLM, what are chatbots. We'll try to see how do we start developing a chatbot using large language models, where we'll try to understand how do we set up the environment. Then we talk about how do we collect and prepare the data for LLMs to understand. Then how do we implement LLMs, chunk and embedding vectors that is required for retrieval augmentation. So that is embeddings of the data chunks. I will talk about those things. We'll further talk about how do we implement query processing and recommendation systems. We'll give an understanding on prompt engineering of zero-shot text classification, which is a type of prompt engineering. And we talk about finally with the sentiment analysis with LLMs. So we can create multiple types of LLMs and we can create sentiment analysis LLM. At the end of the session, we'll try to develop or go through with a piece of code using LangChain to create a chat model using OpenAI APIs, and we will work on that and try to put that into production environment using Streamlit. That would be the agenda for the day. So how do we create LLM chatbots? And we'll start with what is an LLM. LLMs are nothing but large language models which are trained on very huge amount of text, and they have the capability of generating human-like text. So they are slightly enhanced version of the natural language processing tools that we have seen before in the deep neural network architectures, wherein those architectures using LSTM models or GRU models or similar models with respect to or the RNN models, these models were able to understand the text and give an understanding of those texts, that what exactly is the inherent meaning about those text messages. However, the large language models are a step ahead of the previous versions, and they are able to not only understand the text, but they are able to generate the text based upon the information given to them. So that is what we call as a large language models. These are primarily trained on a very huge amount of data. They do not have any kind of predefined resources. They are trained on a very humongous amount of data. Now, how it works? If I talk about how LLM works, LLM typically takes up the huge amount of text and breaks it down into the pieces. We call them as the tokens. Now, what is the tokens? As a very small level, a very basic level, I can say that tokens are nothing but the words. At a very broader perspective, you can understand tokens as words. So words in any context, in any paragraph, let's say you have 10 words or 20 words or 1000, each word can be considered as one token. At times, we can also consider an entire sentence as a word, as a token. So that is dependent upon which kind of modeling technique being used. We are using sentence tokens or we are using word tokens. But yes, at a very basic level, at a very grassroots level, you can think of tokens as simple words which are lemmatized or stemmed. So stemmed or words. Stemming and lemmatization are the basic concepts which are coming from the natural language processing part, where we try to cut down the words to a basic root level, grassroots level words. So that is the idea behind stemming, so that we get similar words for every problem. So just for an example, you can think of a simple example. If I write down few words for you, I can write down a word break. So we were talking about how LLM works. So in general terms, if we talk about how LLM works, LLM will be trying to process my entire text data and create tokens out of it. So out of those tokens, the tokens can be considered as single words or sentences at times, depending upon the mechanism that is being used. But you can, at a very broader level, we can consider tokens as the piece of words, which are at a root level words. For example, breaking will become break, or into will remain into, or breaks will also become break. So depending which are the root words which generates other words, we'll try to contextualize all words into a single entity which are of similar nature. The word transformer might become a transform, architectures might become just an architect. So depending upon different kind of words, we might have some basic root words that will come to the picture. That is what we call as a tokenization, stemming, and natural language processing. So that's what we're trying to do. After tokenization, we get smaller words, as I've mentioned, U words or subwords, and we try to convert them into a vector representation, and we call them as numerical representation of those words. Let's say every single word in my entire word dictionary, I will give them a particular number. Let's say A is at number 1, B is at 2, lamb is at 3, so on and so forth. So each particular word out of my entire contextual words will have a number associated with them. I'm giving a random example. And with that, we can assume that those numbers I can represent in different form, maybe in hex code form, or in a binary coded form, or some other form I can represent them. And we can use that numerical representation of each word in order to understand those words in numerical form, because it would be the numerical representation of the data that will help in making things clearer and understandable, right? After this, LLMs, once we got the relevant tokens, then it uses the attention mechanism. Now, what is an attention mechanism? There's a famous research paper on this, which is Attention is All You Need, published in 2017 from Google Brain team. That paper talks about a self-attention mechanism, which is the primary source of all transformer models. LLMs also use transformer modeling approach. So that is where it contains of a self-attention layer and masked multi-attention layers. So that's the basic underlying principle behind all the LLMs. So we have an encoder block and we have a decoder block, and we work on those two blocks together in order to understand what is the input being given and what could be the potential text that could be generated for the given input. That is what attention mechanism allows us to do. We can discuss the self-attention mechanism in detail in another separate video. That's what transformer talks about. So these are very different deep learning architectures, which actually does not use a neuron kind of thing. If you have studied about deep learning architectures, you would have seen that every deep learning architecture at the hidden level has certain neurons at the center, which takes the input and processes it and gives the output. In LLMs, we use a self-attention mechanism module where we replace those neurons by self-attention blocks. The self-attention blocks has two important portions. One is an encoder, other one is a decoder. And again, certain LLMs may be just coder module, certain LLMs might be just a decoder module, certain would be a combination of both. All the generative ones are the models that are combination of both encoding and decoding part. If I talk about types of chatbots, the chatbots is another example of using large language model. What does chatbot do for us? We ask a question, we put up a prompt, we put up a query in front of a machine, and then machine is able to respond back based upon the query being put up. And there can be two classifications of the chatbot based upon these two versions. The first is the rule-based chatbot, and the second one is AI-based chatbot. What are the rule-based chatbots? So rule-based chatbots are those where they have a defined set of rules and pre-written scripts for a particular question. Let's say, how are you? So if I have mentioned already or defined, if someone asks you, how are you? It will give me a particular answer. If that question is not into the vocabulary, it will say that, sorry, I'm not able to answer that question. I'm not trained onto that part. So those are called as rule-based chatbot or rule-based LLMs. Typically, these kind of rule-based LLMs use decision algorithms or random forest or based algorithms in order to understand and create rules and then give the answers. Typically, that's the underlying logic that goes behind the rule-based chatbots. Typically not into practice too much these days. We have AI-powered chatbots, which are much more responsive and much more better. So we'll use in this class as well, we will work on AI-based chatbot. The rule-based chatbots, which are very simple to implement and very easy to put up through. They will not be able to handle very complex wordings because you will not be able to give sufficient amount of examples. Right? Then you have AI-based chatbots. You can put up any kind of queries. I'm pretty much sure most of us would have used AI-based chatbots like ChatGPT or Anthropic, right, or Gemini. You would have used, some of you might have used those, some common names that I've taken up. So all these are AI-based chatbots, right? Depending upon my requirement, what requirement that we have, what kind of chatbot should I use is very much important, because I need to look at many factors like how much customization is required, what is the cost involved, how do I'm on a deployment, what is my deployment requirements, how much open source do I want it, make it to be the open source availability for this. Last and most important factor is how much is a private data. That means a data which is not available publicly for OpenAI models or open source models to learn from. So do I want to include that data or not? That is also an important factor. If I have to include the data, the type of AI-based chatbots will also vary, because there will be two types of AI-based chatbot. One that we use with the pre-trained models, which will work in this class, and the other one that uses pre-trained models. Along with that, it also takes up a chunk of data, or it can also get trained from some other data as well. That is what we call as RAG approach, retrieval augmented approach. All right. So this is what we have seen so far. Now, setting up the development environment. In order to create a development environment, we can choose many things. There are multiple APIs which are available, but in this particular section, we will use OpenAI API. It is easily and freely available. Right. So we require a coding environment. I'm going to use Jupyter Lab for it. Some institutional libraries. To name few of them, I'm going to use Streamlit. We are going to use LangChain. What else? That would be more than sufficient. NumPy and Matplotlib would also be required. That's it. So these will be few libraries. Whether I want to do a cloud-based deployment or on-premises deployment depends. That dependency needs to be understood, because cloud-based deployments would require a little more resources. We need to ensure about the correct API access. The API access that I'm going to use is my own personal OpenAI access. So I would mention OpenAI key at the place of the code where it is required to put up the OpenAI key. All right. Thank you. We'll require understanding of basic Python understanding. How do we write Python scripts? How do we integrate APIs with the Python scripts? Two important things. We'll use Jupyter Notebook in this case, and VS Code, or either you can use any technology, because we are going to write down a .py file. So whatever you're comfortable with, Jupyter Notebook, VS Code, or just Python working environment, I'm okay with that Python editor. So API access can be requested from OpenAI, Cohere, or Hugging Face. I'm going to use OpenAI in this class. So I'll show you how to gain OpenAI access. You can go to platform.openai.com, register yourself, and you can generate your OpenAI API key. Right. So transformers, I can use LangChain, which will require me to develop the chatbot logic, and that's what we're going to do. We can use Llama Index for data retrieval, or you can use Fast API, Grad.io. That can Fast API and Grad.io will allow me to put the deployment part. But we're not going to use that. You can use cloud-based services like AWS, Azure, or Cloud. We're not going to cover that too as well, because it's not within the scope. So data collection and preparation part. So we need to collect the data in the form of either CSV, JSON, or web scraping data. Go to NumPy, Pandas, create the data, and refine the data. But in this particular section, we are not going to deal with NLTK or Spacy library. We are not going to train the model as of now. We're going to use pre-trained models from OpenAI API. So how do we create LLM chatbots? So that will be little practical parts that we'll try to understand how we can create LLM chatbots. What we require is few understanding. If I'm going to train up a model, for example, I'm going to train up an LLM model, we need a model architecture which can be implemented, which can be downloaded from transfer learning methodologies. You can get all those models either from Hugging Face or directly from Transformers library or directly from TensorFlow or PyTorch, whichever way you're trying to implement. We can get it then from there. Apart from that, what kind of model is required? That is also an important thing. Because if I'm doing a sentiment analysis, I'll require a sentiment analysis. If I'm looking at a question answering approach, I would require a question and answering approach. If I'm requiring general question answers, generic models, I can use generic model like ChatGPT. So depending upon my requirement, I would have to choose the correct model and correct APIs accordingly. That is the first important task that we need to, right? That's we have talked about. If I'm trying to use different LLMs, I require different kind of things. For general versatility, GPT is good. Open source customization, llamas are good. Mistral for efficiency, Falcon for scalability. So right model will depend on many factors like performance, cost, and deployment needs. We can get right models, whatever models that you want from Hugging Face or API-based models. API-based models would include like I have Open API access, and on Open API we have the Chat GPT's 4.0 mini version, which is available for access with me. So I'll use that. Now, how to create an LLM chatbot? For this, we need to understand what is retrieval augmented generation. So what is that? Retrieval augmented generation. Suppose I'm trying to do a search. For example, I typed in a query. What is the role of Python? Just a simple word. What is the role of Python? In this scenario, it will try to find out of my entire context that I've given, what is the role of Python. It will try to find out what are the most relevant words with respect to the question being asked, the meaning that it has, and based upon that, it creates a architecture of most important keywords, and that keyword is called as RAG, or retrieval augmented generation. So after that, it finds out what are the most important keywords, and based upon that, it performs the extensive search through the data that it has and finds out the correct responses, matching keywords from different resources. Then from all different resources, it will learn everything and then come back with my solution. So that is what it is going to do for us. What it allows us to do is the RAG approach is my model or my LLM is not going to give me random vague answers. It's not going to create or generate answers without any context. It will always try to find out some semantic information and give good contextual answers. Same thing happens with the chunking and embedding in vector search. It tries to break down the entire text into smaller manageable pieces. We call them tokens. Again, converted to numbers are called as vectors. Again, it can be done through many other libraries, like chunking and embedding can be done by LangChain's character text splitter. We can do through NLTK, or we can do it from TikToken. TikToken is not to be misunderstood with TikTok. It's a different entity altogether. Token is a library that allows us to tokenize my text. Then we have transformers, like sentence transformers available, which allows me to create the vectors. Vectors means again numerical representation of my text. Then we store that in the database. Any simple database can work for us. Then we look for the similarity scores like cosine similarity, Euclidean similarity scores, or product similarity scores to find out what kind of matching architectures. As I've told you, RAG uses this approach, finds out similar context words. So from there, it will try to get me those similarity words and find out similar contextual information. Then we talk about the implementation of query processing and recommendation. In query processing, the idea again changes nothing but you ask a question, LLM works around with that, again breaks it down into a text form. From text, it converts vectors, and since it's a question, so it becomes a question answer kind of approach. So it will find out 10 answers and try to filter out the best suitable answer for any query that is being done. Now, what is zero-shot text classification? In a zero-shot text classification, I do not train my model explicitly, right? So what that is zero-shot classification, where I'm not putting up any additional resource. What is that meaning is I have a pre-trained model like GPT that is being trained on very generic knowledge. Very generic knowledge that may not be very specific about the context that I'm asking. Say, for example, I have ChatGPT, which is trained on almost everything in the world, but it might not be trained on my organization's specific issues. But I can still ask this question about my organization. It may not be able to give me a very specific answer, but it will be able to give me a generic answer. That is what we call a zero-shot text classification, where I'm not training a LLM on a specific data. Rather, I'm just creating an LLM from a pre-trained model and asking it for new data installation, right? How can you find out some classification models? There are lots and lots of available. I can just show you very quickly. Pre-trained classification model, you can go on to huggingface.co. That would be a place you can find a lot of pre-trained classification models available. You can find out models based upon your requirement. You can go to the models and you can click for the task, whatever task that you're looking. Let's say I'm trying to do some text natural language processing. That's a zero-shot classification. I have many models here. But just for zero-shot classification, these are the models available. I have BART large MNLI from Facebook. That's one of the zero-shot classification model. You can look at that. Go to files and versions. This is the entire model. You can see that you can read out this readme.md file and find out the information about it. So there are a lot of models which are available, which you can use. Again, it's a GitHub, so you can clone this entire part and you can clone it from directly from Hugging Face, clone the repository and use it locally. Okay. So any model can be used. So BART large mini MNLI, that's one classification model that can be used out. There can be a lot of things that can be done in zero-shot classification. Apart from that, you can create transformer pipelines wherein I'm trying to do one transformation followed by another one, and so on. So that can be created up. We can use a scikit-learn matrix like precision, recall, or F1 scores to find out we have correct classification. We can implement those two. Finally, we'll talk about the sentiment analysis with LLMs. LLMs can also be very much useful in doing the sentiment analysis part. So in sentiment analysis, we try to look at how we can determine the emotional tone of any text, allowing or enabling chatbots to understand the user sentiment. So we try to train the chatbots on emotional content, on data which contains emotional aspects. We can define it whether it's a positive or emotion or a negative emotion or sad emotion or a happy emotion. We can train the LLMs on that. And based upon that training, my LLMs would be able to tell me whether any particular emotions being reflected is what kind of emotion it is. It may not be able to mimic that emotion, but it will be able to tell me what emotion has been reflected in the context. It can be with the audio, it can be with the video, or it can be text as well. That is the sentiment analysis. Again, Distilbert is one of the very good classification model for sentiment analysis. That is what we can use. Sentiment analyzer is available with many other sentiment analyzer is available with Distilbert, Robert, Llama. Everywhere we have a sentiment analyzer available. It's one of the class in a pre-trained model which is available to analyze the sentiments. So this is what we will talk about through the entire understanding of your LLMs theoretically. Let's try to practically look at how do we implement that. So I will open up, let me open up my Anaconda Navigator. So I'm going to open up Anaconda Navigator here. I have a pre-written script. I'll walk you through that and I'll explain you each line what it is doing. Hopefully that helps. So here it is. I have just got my Anaconda Navigator opened up. I'm going to open up my Jupyter Lab environment from here. Wait for that to open up. Should be up and running in a moment from now. So once that opens up, we will be able to start doing the coding part of creating a chat GPT kind of approach, where that would be in the implementation of chat GPT through chat GPT open API that we can use at our own local servers or at our own particular end. Essentially, that is a replica of ChatGPT that you can put up. Okay, I already have this piece of code written down for you. So what are we going to do here? So I'll put down certain piece of codes here. This file will be made available in the description too, or you can copy it from here. Okay. So what is each of these things that we're going to do? So I have named that as I have created a Python script here. For that, I've gone to File, New, and I've used a Python file. I went into that option and I create a Python file. First line I wrote down is import Streamlit ST. So this will allow, I'll put up certain libraries to be done. Libraries, import. Prior to that, you might be wondering if I don't have those libraries. So you need to install these. I'm putting that as a comment, pip install. Or if you're using an environment, you need to put that into your environment. So I'll put up that pip install. You need to put up LangChain. I'm using LangChain here. Space. You would require Streamlit, OpenAI. That should be good. And just these two will be good enough. Okay, you need to install these two libraries, LangChain and Streamlit. What I'm using Streamlit for? It's LangChain. I'm just putting this notes. LangChain supports or LangChain for the purpose of building chatbot logic. Okay. And Streamlit for designing UI. So I'm not going to give too much into designing part. I will take a simple UI as of now. Idea is not to do the designing part, designing the user interface. Okay, so a web-based user interface, I'll say that designing a web-based user interface. A separate session on Streamlit can be taken up to design all that part. So Streamlit is a separate library altogether. So we will import Streamlit as ST. That allows me to import Streamlit from LangChain.chat models. Now this submodule allows me to open or connect or call up the keys or OpenAPI keys from the OpenAI servers. Okay. So that is a class that is available, Chat OpenAI, that will allow me to create or contain my OpenAI tools. Then another thing that I need to put up LangChain.chains, conversation. Now what does that do? It allows me to create a chain of conversations. That means suppose if I ask one question, there's an answer given. Then I can ask up a probing question further. So that allows me to remember the previous past as well in context with the current conversation. It allows me to create a conversation chain rather than one question, one answer and stops. Instead of that, it allows me to repeat things on a simultaneous basis. LangChain.memory, that allows me to remember the buffer memory. It allows me to remember my previous conversation. Suppose I have started with one conversation and then I want to continue with another conversation. So my previous conversation can be saved and used. It can be reloaded. OS I'm using for very generic purpose to create environment variables. If you want to create environment variables, otherwise it's your choice. If you can avoid OS as well if you're not using environment variables. So first thing is to set up your OpenAPI API key securely. So for that, I'm creating a variable OpenAI API key and I'm putting that into my Streamlit secrets. Now, where are these Streamlit secrets? Okay, so these are typically stored in a TOML file. I'll just show that. So that will be in your default folder where your Anaconda is installed. You will have a .streamlit folder. You need to go into that and install will be in default user account. Inside that, you will find a under Streamlit folder. You can find there is a file by the name secrets.toml. If it is there, you can put it up. If it is not there, you need to create a new text document like this. Inside this, I've just opened it up. You need to write down anything. I have used the word OpenAI underscore API underscore key is equal to, and you need to mention within quotes your API key, whatever you are using. Put it up here and save this document. Save as, and you go to this place, select all files and save this document as secrets.toml. So that allows you to take your key into or transmit it into your network or transmit it to your model with encryption. So that can be saved up. So you can just need to save that file. I have already done that, secrets.toml. This file contains my API key, right? I already have that file here. So that allows me to tell it, Streamlit, go to the secrets and find open API key if it is available in open secrets. If it is available in there, else you can get it from the environment variable. Or else otherwise you can create up here os.environment. Those who do not want to use that, you can put up os.environ and create up the same variable by the name open. This is an optional thing. So shift open underscore API underscore key, and you can mention is equal to quotes your API key, whatever you want to use, your OpenAI API key. That should work. So I'll put a comment. This is an optional thing, right? We'll get this thing work. I have put this again in statement. This is for the purpose of else os.get environment open API key. So if we do not have a key available in secrets, it will try to fetch it from the environment. All right. Now we need to initialize our LLM model. How do we initialize my LLM model? My LLM is equal to chat OpenAI. That's the name of the function that will connect me to OpenAI servers. OpenAI.API key is equal to OpenAI.API key. I have kept my API key. If you do not have anything else available, just write down your OpenAI key directly here. You don't have to create anything at all. Right? You can paste it up directly here as well. That will expose your OpenAI key, and you may not want to expose that securely. Then the temperature, it's the amount of randomness that we want. Now, what does that mean? It means how much randomly generic answers I want to create, the temperature part. Higher the number, more is the randomness I'm trying to bring into my answers. The bigger the temperature value is, the better your answers would be. Lastly, the model name. Based upon your access to OpenAI API, you would be able to access either some of the models. I am able to access GPT-4 or mini model. I have mentioned that model. If you're able to access GPT-4, you can just mention GPT-4 or whichever model you have an access, or 3.5 turbo, depending upon your access. You can use that particular model. After we have initialized the LLM part, we will move on to the next part where I'll set up the memory part. Now, what is that memory part? In this, on my Streamlit platform, I just wanted to make sure if there is any previous memory available, it should be able to bring that memory for me. If it is not available, I'll start my conversation from a new piece. So I've created a variable memory, if memory not in session state, right? st.session state. A session state is a variable that creates my value, and I'm looking for memory part. If there would be any memory, this flag will be true, whether it will be false. So if memory not in session state, if it is not present, I want to create a memory that I can assign a memory value to it using conversation buffer memory. So whatever memory that we have, I'll start with that memory. So that will be blank at the moment. Then I'll start my conversation. Now this function conversation chain, it actually allows me to create the chain of conversation. The model that I'm going to use is LLM model. The memory is the current memory state, that is blank, currently blank. So as soon as we keep on moving, the memory states gets on updated. Verbose will try to make sure that if there is any kind of warnings or something in between, these are not being displayed. So the verbose false, that ensures that part. So we do not see any warnings or anything. Apart from that, now we need to design the interface. That's the model LLM model part done. We will design our interface. st.set page config. So whatever the web browser page that I'm going to design, I want to put the title as LLM chatbot. Page icon, if you want to put something, let's say put up anything. You can put up a GIF image or whatsoever you want. If I can have, okay, you can leave it. I'm writing down one Simplilearn. I do not have that small images right now. So you can put a page icon like this. Then title. Now this title will appear up in the center of your page, right on the first page on your screen. The LangChain chatbot by Simplilearn. Okay. So that will appear up in there. Now we will now use the same place that will create my interface. That means I'll get a web page whose title will be LLM chatbot. Page icon will look like Simplilearn's name written onto that. Title would be LangChain chatbot by Simplilearn. That will appear up somewhere in the center of my screen. Then I'll put up a blank box to receive user input. So user input is equal to, the name of the function is st text input. St is my Streamlit library. In text input, I'm asking this part to display. Asking you to display the word u followed by key is equal to input. So it will display up a box and the key input will be displayed up within the box. So you get to know that here I have to put in the input value. Then if I get a user input, my response is conversation, which is my conversation chain model that we have created here. Conversation.predict the user input. So based upon the input that I gave, it will create up a response. Once it gets the response, I will add to the memory, to the chat memory. So session state memory dot chat memory dot add user message, predefined function. So I'll put up user input and add AI message as response. I have added two functions there, and then I'm writing up the response. So I'm putting up now on my screen st.write is going to put my response. So I'm writing down a formatted string with a markdown language of bot that will appear in bold and the response. So what are the response from LLM model that has came up, that will be printed up here. At the last, I'm putting up, this is an optional thing, completely optional, wherein I'm trying to tell you, if you want to see the previous histories, you can put that up by doing this. How? So there is a checkbox I'm creating. If st.checkbox show chat history, that will be displayed in front of it. There will be checkbox. So if I select it, this becomes true. If I do not select it, that remains false. For message in st state memory, chat memory messages, I will try to see. See, I have added user messages and AI messages. So that is available in my session state memory, chat memory, right? So I'll go to session state memory, chat memory, and I want to recollect all messages. So I'll retrieve all messages from there, and I'll put up what the role this particular u, if message dot type is human, else bot, and I'll put down the entire content. So that's what will be printed out on my screen. That completes your entire LLM creation part. Let's try to work around this. Now for this, you need to save this file as chatbot.py. Once you have done this, open up your terminal. I'll open up a terminal that is nothing but my Windows terminal, PowerShell terminal, and I'll run this command by putting up Streamlit space run space name of my Python script. So it's chatbot.py. That is my Python script. When I execute this, I press enter key on my keyboard and say that you can now see your Streamlit app. I'll just show you this. You can now view your Streamlit app. It's starting up the app on the back end, but I'll just show you here on your browser. So that has already opened up an app on my browser. I'll show you that. But it says that local URL HTTP localhost 8505 and my network URL is this. So it has got me an IP address URL as well. I can use either one of those. But if I go to my web browser and see, it says that my window title of, I'll show you. You see that LLM chatbot here. That's my title on the top. Put up. I had an emoji to come up, but that did not come up. Alas. But you can see here, LangChain chatbot by Simplilearn. That's what I put up here. That's the name. And it has a context box of you, and I have a box to write down. I have a show chat history option. Let's try to search. What is, or let's say today's news, I'll win Champions League 2025. Now that's a very generic question. I'm pressing enter to apply. If everything is good, my API is running, I would get an answer. It says, I cannot predict the future, so I don't know who will win the Champions League 2025. The tournament is filled with so many talented teams, and anything can happen in football. So you can ask me any question, you can put up any questions. If you don't like, you can put up a new question here. Tell me the names depending upon how much availability of all participating. So depending upon your prompt, you can create up. So it tells me does not know the top teams from various European leagues, including Premier League, La Liga, Serie A, Bundesliga, and League One, along with some lesser known leagues compete for a spot. So we can see some team names that can be there. Essentially, you can also see below, so show chart history. If I put that on, you can look at all the things that has been done in this particular. You can see my chart history is available. So that can be viewed. I removed that show chart history. This chart history will be pardon now. Again, depending upon the machine that you're using, it is running on my local server. So depending upon hardware, it might be slow or fast. That is how you can do it. The next option that we can do is to deploy this. In order to deploy this, you need to go on to deploy option. You have multiple choices available. Like you can go Streamlit Community Cloud, you can go Snowflake, or you can deploy on your custom platforms. If I want to go on Community Cloud, I can click on deploy now. I need to access to my GitHub account. I need to put this code onto GitHub and then I can deploy. That can be discussed in a separate session altogether. So that would be it, everyone. And I would really like you to think of questions and answers. If you have something, put them up into your comment section and we'll definitely respond back. Thank you very much.
I'm going to show you how to create highly realistic digital clone of anyone using HeyGen. This tool is an incredible way to generate lifelike avatars and unlock endless creative possibilities for content creators, businesses, and anyone looking to produce realistic digital representation. So whether you want to create training videos, personalize content, or even bring someone's likeness into your project, this tutorial will walk you through the process step by step. So guys, watch this video till the end if you want to learn more about it. But before we move on, let us first understand what exactly is digital clone. A digital clone is essentially a digital version of a person that mimics their appearance or voice and even behaviors. These clones can be used for a wide variety of purposes, from creating virtual assistant avatars for training videos or personalized messages, to even crafting content for marketing campaigns. The key is that these clones are powered by artificial intelligence, which allows them to mimic the unique trait and characteristics of a real person. Digital clones are created by combining video footage, voice recording, advanced machine learning techniques to produce digital representation that can speak, move, and interact just like the original person. And with tools like HeyGen, this process has become much more easier and accessible. So you can see I'm at the official website of HeyGen. Okay, you can access this website if you go all over here, type HeyGen, and you can also go with type HeyGen digital clone. It will redirect you all over here. Clone yourself AI. So this is the official website. Now the next step is you have to sign up. So you can see all over here there's an option sign up for free. Just click on this. Now there will be various plans that will be there for you. Like for example, there would be the free version where you don't have to pay anything. Then you have the creator plan. Okay. Once you have signed up, it is going to show you the given plan. So first one is the free version. You can try this plan if you are beginner and want to learn about this tool. For most of the users, they can go with the creator plan. You can create up to 5 minutes video long. You can export it and you have also amazing features like utilizing language translation. Then you have team, where minimum 2 seats are there, and you could see it is billed $720 yearly. There are unlimited videos. You can create videos up to 30 minutes, 4K video export, faster video processing, and there is 5 minutes of avatar 4 videos per month. So these are the things. And for larger scale projects, you can also go with the enterprise level plan. It has additional features and scalability options. Now, once you have chosen your plan, you are ready to go. The next step is creating the avatar. So let us click on the free plan, and let's say I'm creating my personal project. Let's right click. You can just click content creator. Let's say we are creating a marketing video. Okay. Now, all over here, we have to create our avatar. So let's try avatar 4. Let's see what it has.
Avatar 4 allows you to turn a...
Now, you can try any sample photo all over here. So you can click on this and you can create an avatar. So like I have selected this avatar, and you could write your script all over here, or you could upload or record audio also. So let's take the help of ChatGPT to create a script. Okay, so let's ask GPT. Okay, so guys, I've taken the help of ChatGPT and I have instantly added a script all over here. Now, let's say custom motion also. So for custom motion, you can again take the help of ChatGPT. Let's ask add. Okay. Now, what I've done is I have taken the help of ChatGPT, and also I have added in the custom motion also to give much more idea like how my avatar is going to do. Now, you could choose the given resolution. Let's say it's 180p, and we cannot do that since I'm on a free tier. So go with the 720p and let's click on generating the video. So guys, for the best result, you can select the motion option. This allows you to actually give much more description about the motion of your avatar. Now, make sure the avatar you are using is well lit, centered and expressive. This will help make avatar appear more natural and lifelike. The more natural the expression, the better the final avatar will look. Now, the third step, we have to record and train. Now, it's time to actually record your subject. The footage does not need to be shot in a professional studio setting. It could be done at home, outdoors, or in any well-lit environment. The key here is to make sure subject speaks clearly and directly into the camera. But for this instance, we are actually using the avatar which is already given by Hagen. Okay, but for the other purpose, if you are creating your own avatar, and also make sure that there is pause between sentences when you are creating a video. For example, you could say something like, hello, my name is your name, and today we are going to show you how to create a digital clone. So add some brief pauses between the sentence, because this is going to help Hagen process the footage more effectively and gives the avatar more human-like cadence. Now let's see how video is created. Let's look into this. Let's select the portrait version. So guys, initially we added the script for our digital clone and we selected this random image and we have given certain script. Now we have used the motion feature of Hagen and let us see how this comes out.
Hey there, I'm your digital assistant, here to show you how our amazing software is revolutionizing the way you edit photos, videos, and more, all powered by cutting-edge AI.
Wow, it sounds so amazing. Just looks like, repeat, it just looks like a real person. For somewhat, it's still recognizable that it's an AI clone, but you can create your own avatars like that. So for section of creating your own avatar, what you need to do is just go all over here, click on create new avatar. Then you could either go with hyper-realistic avatar or custom photo, or you could click on generate. So let us try this feature. Let's say his name and gender is man. So let's take a prompt from ChatGPT. So we could add up all over here and let's select till personality only and paste this. Okay, delete the behavior part and let us try to see the preview, how our avatar looks like based on our text prompts. Now, it has already generated certain a photo for our avatar. Let's select this, click on save. And in this way, you could generate an avatar also by giving the description. So this is a very amazing tool, guys. There's a lot of things you could do all over here. Now you could see you can also add a voice. So let's add this voice, okay? And let us try to see this. And now there is also option to train this model, but this will take some time and also certain credits. Now, if you're someone who is a content creator or you're creating tutorial videos, then this tool, you must check it out. And you can buy the creator plan. That is the most ideal plan for most of the users. And then you could access all these features. So this is our photo. Let us see how our avatar looks like. So now here you could upload the audio also, or you could add a script, and it will take certain time. So let us ask ChatGPT for the same. Now, after this, what you need to do is just add the given script. Okay, you can add the script all over here. Let's say, just add the name. And after this, just click on generate. And let's say, now just add the title and click on submit. It is going to take some time to generate the video. Let us see. Okay, so it's still in line for processing. It might take some time. But apart from that, there is also amazing feature for brand. You could do the branding kit also. So let us explore a bit. So you could see, you could create your own branding logos, or you could create your product images with the help of this tool. Very amazing tool. And it also has amazing integration, like it has HubSpot integration, Adobe Express plugin, Canva app, ChatGPT plugin, and there's a lot of other applications through which this tool can be integrated. And this is Labs. Labs is also a new feature. So someone who is into podcasting, you could also try this amazing feature. Now URL to video is also there. Amazing features like instant highlights, interactive avatar. So as you can see all over here, the video is still in the processing line, and you don't have to wait for this. What you can do is you can explore this platform and create your own avatar. And that's it, guys. We have successfully created our one avatar today using Hygiene. This technology is still evolving, and as it improves, we can expect more lifelike and interactive avatars. Hygiene has incredible potential. Whether you are creating personalized video messages, training content, or just exploring new ways to express yourself digitally, digital clones have potential to revolutionize the way we create content and communicate. Imagine the possibilities: personalized customer support bots, training videos where a presenter is always available, virtual brand ambassadors, or even educational tools that feature instructors who can be physically present.
Hello everyone, I am Mayank and welcome to our YouTube channel. Today we are exploring Hugging Face, an amazing tool that makes working with language and AI super easy. If you are curious about using advanced technology to understand or create text, this video is perfect for you. Hugging Face is a company that helps people use AI models for language tasks like translation, text analysis, or even generating new text. They have created a library called Transformer, which comes with pre-trained models, so you don't have to build everything from scratch. It's simple, powerful, and perfect for developers, researchers, or even beginners. So in this video, I will show you 3 cool things you can do with Hugging Face. Speech to text, turn spoken words into written text easily, great for captions or voice apps. Second one is sentiment analysis. Find out if a text is positive, negative, or neutral. Helpful for understanding reviews or comments. The third one is text generation. Create human-like text that sounds natural. Perfect for chatbots or creative writing. I will also explain some important basics like how pipelines make using Hugging Face models super easy and how tokenization helps AI understand text. By end of this video, you will know how to use Hugging Face to start building your own projects. It's simple, fun, and really powerful. So without any further ado, let's get started. So welcome to this demo part of this video. So here, as you know, we will be doing 3 things. First thing, speech to text recognition. The second thing, text generation from a particular sentence or a word. And the third thing, we will do sentiment analysis. Okay, so we will perform this one by one. So let's start with something called speech to text recognition. Okay, using Hugging Face. So first I will rename this. I will write here Hugging Face speech to text. Okay, Yeah, so first I will install transformers library. It is already installed on my system, but again, just for you guys, I'm doing this. Okay, pip install transformer. So now let's see what is transformers. So transformers is a powerful Python library created by Hugging Face. So that allows you to download, manipulate, and run thousands of pre-trained open source AI model. Fine. So as you can see, requirement already satisfied. It means like already installed. So these transformer models cover multiple tasks across modalities like NLP, natural language processing, computer vision, audio, and multimodal learning, like many things. Fine. So now I will do from transformers import pipeline. Okay, so now let's run it. So now what is pipeline? Okay, so a transformer pipeline describes the flow of data from origin system to destination system. Fine, because you already know transformer means you can run or manipulate thousands of pre-trained open source AI model. So pipeline describes the flow of data from origin system to destination system and defines how to transform the data along the way. Okay, so let's check the versions. Transformers version. Okay, that long tab. Okay, why it is coming? Import transformers. Yeah, so we have currently 4.42.4 version of the transformer. Okay, so I'm using Google Colab. Okay, so you can use either Jupyter Notebook, Visual Code Studio, or Colab. Okay, so now let's import libraries. Import Librosa. Okay, so what is Librosa? So Librosa is a Python package for audio and music analysis, right? Because we are doing speech to text, so we need this. So it provides various functions to quickly extract key audio features and matrices from the audio files. Okay, and this Librosa can also be used to analyze and manipulate audio files in a variety of formats such as WAV wave, MP3, M4A, and like that. Okay, so next we will import Torch. I hope everyone know Torch. So Torch is nothing PyTorch. It is a machine learning library based on the Torch library used for applications such as computer vision and NLP. And originally it was developed by the Meta AI and now the part of Linux Foundation, umbrella. Let's import one more thing. Import. So now let's import IPython. Okay, capital IPython dot display as display. So now you will be wondering what is this IPython display. Okay, so it is an interactive command line for the terminal for Python, and it it can provide a IPython terminal and the web-based notebook platform for Python computing. And this IPython have more advanced features than the Python standard interpreter, and we quickly execute a single line of Python code. Nothing. Okay, for that I'm using this. And the next is from transformers import WAV to vectorizer for CTC and WAV to vectorizer to tokenizer. Okay, so now what is this? So WAV2 vectorizer for CTC is supported by the notebook on how to fine-tune a speech recognition model. Okay, and this tokenizer. So tokenizer is nothing. Tokenization is a conversion of a text into meaningful lexical tokens belonging to categories defined Alexa program. In case of NLP, so those categories include nouns, verbs, adjective, punctuation, etc. Okay, now, and the last library, let's import NumPy as NP. I hope everyone know NumPy. What is NumPy? Again, NumPy is a Python library used for working with arrays. It also has a function, for working in domain like linear algebra, Fourier transform, and matrices, and many others. Fine. I hope everyone know about these library which we have imported. Okay, so let's move forward by tokenizer equals to to tokenizer dot from pre-trained. This is why I love this Google Colab. You will decide just some words and it will show the suggestions. Facebook. So this is again one pre-trained model. Okay, so we are just importing it. Base 960th. This is nothing, the name. Okay, then model equals to WAV2 for CTC dot from pre-trained, then Facebook WAV2 vectorizer 2, then base 960th. Fine. Now let's run it. So now you can see. So we are loading this. Okay, they are downloading. Okay, so you can ignore these warning. So now let's load the audio file. So here I will write audio sampling rate equals to librosa dot load. Okay, so you know about librosa, right? Then I have v dot m4a. So I have already one speech or one audio, you can say. So I will play it, don't worry. Before the final output, I will show you 16,000. Okay, so now I will write okay, I've already loaded, I guess. Okay, no issues. I will load again. Okay, the file is loaded. I will rename it to V. Yeah, fine. So now the error won't come again. We have v.mp4a. Okay, so now we have to do. Okay, let me try it. We have v.mp4a, but I don't know why it is not coming. Okay, let me copy the path. Now it will run, I guess. It's running. Yeah. So now I will write here audio, comma, sampling rate. Okay, now listen carefully. Then I will write display dot audio, then path, comma, autoplay equals to true. Okay.
Hello and welcome. This is an AI voice message.
I guess you heard, but again, let me play it again.
Hello and welcome. This is an AI voice message.
Okay. So it is saying ki, hello and welcome. This is an AI voice message. Fine. So now what I will do, I will input some values. Input values equals to tokenizer, then audio, comma, return tensors equals to pt. Fine. Dot input values. Okay, then here input values. Okay, input values. Okay, yeah. So now logits will come here. So we have to now store the logits, which means non-normalized predictions. Okay, so logits equals to model input values dot logits. Okay, then here I will write logits. Okay, it's running. Done. So now what we will do, we will store predicted IDs, then we will pass the logits to values to softmax to get the predictive value. Okay, so here I will write predicted IDs equals to torch dot arg max. Okay, then logits comma dimension equals to -1. Okay, then I will pass the prediction to the tokenizer decode to the transcription. Okay, so here I will write transcriptions equals to tokenizer dot decode predicted IDs to 0. Running fine. So now let's see our output transcriptions. So now you can see hello and welcome. This is an AI voice message. So now let's play it again.
Hello and welcome. This is an AI voice message.
Amazing, right? So this is how you can use Hugging Face for the speech to text recognition. It's a very small code, line of code, as you can see. Okay, so now let's move forward and do the sentiment analysis, okay, or text generation. So let me open new drive. So yeah, so now I will write here, I will write sentiment slash text generation Hugging Face. Okay, so first of all, let's import the files. So first I will write import warnings, then warnings dot filter warnings. Okay, I will write here ignore Then we'll import NumPy. You already know what is NumPy. And import Panda. So these are some basic Python library, and I hope everyone knows. And import matplotlib for the plots. Matplotlib dot pyplot as plt. Then I will import cbon for the graphs, the statistics graph. Okay, SNS, then SNS dot set. So now we'll import sklearn model train trace split. So sklearn is nothing. Scikit-learn is probably the most useful library for machine learning Python. So this library contains a lot of efficient tools for machine learning and statistical modeling, including classification you can do, regression you can do, clustering you can do from this sklearn. Okay, from sklearn dot model selection import train trace split from sklearn dot matrix import f1 score comma confusion matrix comma ROC AUC curve or score. So again we'll import teams from transformers, import pipeline. Everyone know what is this. Then import torch. Okay, now let's run it. You have too many active session, terminate existing to continue if you are interested in using one more session. Okay, wait. Yeah, fine. Now which one is open, bro? Terminate this, terminate this, terminate this. No. Okay, fine. So now let's do sentiment analysis. So we will explore sentiment analysis using a pre-trained transform model. Okay, the Hugging Face library provides convenient pipeline, as you already know, function that allows us to easily perform sentiment on the text. So now let's first import the necessary dependencies and create a sentiments pipeline using this line. So I will write here classifier equals to pipeline sentiment analysis, then type classifier. Okay, so it will download the pre-trained sentiment analysis pipeline. Pipeline is not defined. How? Okay, error is there. I hope it will run now. Yeah. So now we can pass a single sentence or a list of sentence to the classifier and get the predictive sentiment labels and associate confidence score. Fine. So now just for the testing classifier, so let's write this is a great movie. Okay, now let me run it. So now you can see here label positive. So label positive typically refers to the outcome or a class of interest that the model is designed to predict. So here we are just checking the sentiment analysis model. Okay, so this is why I wrote this. Okay, so let's check one more. This was a great course. Then I did not understood any of it. Now let's check this. Yeah, perfect. And the score, you can see the accuracy score 99%, which is almost close to 100%, and which is amazing. So now you have access to a GPU, so you can also utilize it for the faster processing by specifying the device using the parameter. Okay, so now what I will do, first I will, okay, wait, yeah, fine. So now I will import dataset airline tweets equals to pd dot read. PD means pandas library here we are using. Okay, now first import, I will import here itself. So I have tweets.csv. Okay, tweets.csv. Let it upload. Yeah, done. So now let me airline tweets dot head. Why dot head? Means it will show me the top 5 rows. Okay, 0 1 2 3 4 5. Okay, you can see tweet ID, airline sentiment, neutral, positive, neutral, negative, then this. Okay, so now let's do something. Okay, so what I will do, df means data frame airline tweets, then I will write airline sentiment. We have airline sentiment, this column. Okay, comma text. I need these 2 columns. Okay, df dot head 5. So yeah, so airline sentiment is neutral, and this is what this text is all about. Okay, because these 2 are the main things, text and the sentiment. So now let's make plot, count plot. Then I will write df comma x equals to airline sentiment, then palette equals to with this. Then here I will write plt dot x label airline sentiment. Okay, then plt dot y label count plt dot show. So it will draw one graph. Okay, spelling is wrong. Yeah, so it will show neutral, positive sentiment and the negative. So as you can see, the negative sentences or the sentiments are the more. Okay, so we have now 3 classes which do not match the 2 class available in the Hugging Face pipeline. So therefore we will filter out all the rows which have been labeled as neutral. Okay, so df equals to df, and again df airline sentiment, fine, was not equals to
neutral. Okay, then df target equals to df airline sentiment dot map. Then I will write here positive 1 and the negative 0. Fine. Negative will be 0. Okay. Then print number of rows, comma df dot shape. Okay, so now you can see number of rows are 11,541. Okay, so now I will write predictions 5. It will, okay, predictions is not defined. Okay, so now what I will do, so here I will write text equals to df text and toList dot toList. Then here I will write predictions equals to classifier text. Okay, so here write probabilities equals to prediction, then score if predictions label dot starts with P means positive. Okay, else 1 minus prediction score. Okay, then I will write for prediction and prediction. Why it is not running? This is taking time, too much time. I don't know why. So as you can see, finally we have the output of predictions values. So this depends on system to system. My system took almost 17 minutes 47 seconds to complete. Okay, so now let's run it. Okay, predictions is not defined, bro. Now predictions. Yeah, so now I will write here predictions equals to np dot array. Np means numpy dot array. Then I will write 1 if prediction label is positive dot starts with P. Okay, else 0 for prediction and prediction values. Yep. Okay, fine. So now let's check the accuracy of our model. Print accuracy. Okay, then I will do round up the values. So here I will write np dot mean, then df, then the target, right? Yeah, then I will write equals to predictions, then I will write into 100 comma 2, then I will write percentage. Okay, fine, looks good. Yes. So as you can see, our accuracy is 88.99%, which is very good again. So now let's do some confusion matrix. Confusion matrix, then df target comma predictions comma normalize equals to true. Okay, then I will plot confusion matrix. Okay, df then target comma predictions comma normalize equals to true. Okay, my bad. That here confusion matrix comma labels. Okay, so here I will plot a confusion matrix using Seaborn. Okay, so here I will use ARGS, which is confusion matrix np.nArray, so which is labels list. So I will write plt dot figure, then figure size equals to 8,6. That's SNS dot set font scale equals to 1.4. Okay, then let's create the heat map. Confusion matrix comma and not will be true. Okay, then I will write fmt equals to g, then confusion map equals to blues, then x6 labels equals to labels, then y 6 labels equals to labels. Okay, yes, so now I will write plt dot title will be confusion matrix, then plt dot x label will be predicted values, then plt dot y label will be actual values, then plt dot show. Okay, why the chart is not coming? Okay, so I have to write plot confusion matrix, then I write cm, then negative comma positive. Okay, now the chart will come. Okay, yeah, so now you can see here this is actual, and this is a confusion matrix, and the negative and the positive ratio is there. Okay, so now let's print the now let's check the ROC AUC score. So I will write here print ROC AUC score. Then here I will write ROC AUC score, then TF target, comma, props. Okay, so 94. Okay, so first let me tell you what is this ROC AUC score. So this is the area under the ROC curve. So what it does, it sum up how well a model can produce relative scores to discriminate between positive and the negative instance across all the classification threshold. So with this ROC score of 94, 0.94, which is 94%, we can conclude that a pre-trained sentiment analysis model has achieved a high level of accuracy and effectiveness. So in predicting the sentiment labels. So this indicates that the model is capable of accuracy classifying text into positive or the negative sentiment categories. Okay, so now we'll do text generation. Okay, so text generation involves generating creative and coherent text-based thing. So I will write here text. Okay, so text generation involves generating creative and coherent text based on a given prompt or starting point. So what we will do first, we will import the necessary dependencies and load the data set of the poem. Okay, so here I am write poems. Let me write poems equals to pd.read.csv. Don't worry, I will give you these files. Okay, description box below I will add. So here I will write robot frost, okay, .csv. Fine, and then I will write poems dot head 5, or head, just have to write head. Module pandas has, okay, not dot underscore csv. Yeah, okay, it will show the top 5. Stopping by woods on a snowy evening, fire and ice. The aim was song, collection, content, year of publication. Okay, so now what we will do, we will write content equals to poems content dot drop na to list. Okay, so to generate text, we extract individual lines from the poems and use the pipeline text generation function to create a text generation pipeline. Fine, so here I will write lines equals to, then I will write for poem and content, okay, for line in poem dot split into next line. Okay, then lines dot append, then I will write line dot right strip. To the right it will add. Okay, fine. So now lines equals to line for line in lines if length of line 0, then show me the lines 5. Okay, so now you have seen here whose woods these are. I think I know. Then the next line, his house is in the village though. That's the next line, he will not sing. Okay, like this. So now let's import that pipeline text generation module. Okay, gen equals to pipeline. So these are the some pre-trained model. You already know generation. Okay, so now I will write here lines. Let's run it. Yeah, done. So in line 0 we have whose votes these are. I think I know. Okay, so now we can now generate text by providing a prompt and specifying the parameters such as max length and num return sequence. Okay, why? Because we have imported this text generation module. Okay, for example, see okay, sorry, lines 0 dot max length equals to 20. So now it will generate this to the maximum 20. Okay, till 20 word maximum length. Okay, check. Okay, okay, expression cannot contain perhaps double equals to where? Okay, wait, now it will run. So see, the line was this much only. Whose words these are, I think I know. Whose words these are, think I know. But here, the generated text, I wish to go to church because I feel like. Okay, this is how you can do, text generation. Now let's check for the more. Gen lines 1. Okay, then max length equals to 30, comma, num return sequences equals to 2. Okay, so our first line was this: his house is in the village though. Okay, 0 1 2 3 4 5. Okay, so here you can see his house in the village though. However, you might say that the place was the same with the place this. So these are the generated text. Okay, and this is another return sequence second. So there are two, one and the second. Okay, so now let me import text step. Okay, then creating function wrap x. I don't need this. Then return text wrap dot fill x comma replace white space equals to false comma fix sentence endings equals to true. Okay, so now out equals to generated lines 0 to maximum length equals to 30. Then print wrap out to 0. Then generated text. Okay, so now we are setting the pad tokens to EOS tokens. Okay, so whose these are, I think I know, and this is the maximum 30 till 30. Okay, so now I will write here. Okay, preview equals to. Okay, so now what you can do, you can generate a prompt to generate text on a specific topic like this. Prompt equals to transformers have a wide variety of application in NLP. Okay, so this is my prompt. Okay, this I'm not importing from the data set. Okay, so I will write out equals to gen prompt comma max length equals to 100, print wrap out. Okay, here I will write, anyways, here I will write generated text prompt. Okay, so it is running. Let's wait. Yeah, so okay, some error is there. Okay, so here the issue is with 100 words. We'll go till 50. Yeah, so let me do it again. 100. Yeah, so now you can see we can generate text by giving a prompt. So we have covered 3 topics in this. First thing is speech to text using Hugging Face. Second thing is sentiment analysis using Hugging Face, and the third is text generation using Hugging Face. Okay, and in this text generation we did with 2 methods, one with the data set and second thing with the by giving prompt, like in ChatGPT you can say.
Convolution Neural Network Tutorial. My name is Richard Kirschner with the Simplilearn team. That's www.simplilearn.com. Get it certified, get ahead. Today we're going to be covering the Convolutional Neural Network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in. So it takes that graphic and puts it into the input layer. You have all your hidden layers. And then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulations. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist. So we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer. ReLU is how that is pronounced. And that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally, there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN. What is convolutional neural network? How CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for. And you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto its pixel values, represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it, and we're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first three elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times B. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our A times B product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match 3 different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now obviously when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is. What you do need to understand how a convolution layer works is what is the filter doing. Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges. It might be looking for different parts. We'll cover that in a little bit more detail in a minute. Right now, we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, it's going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, we say linearity, we're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or that backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here, it's turned it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have our rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving 1 over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel. We just do every other one. And this reduces our rectified feature map, which as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value, a little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value and then we're pooling those features together. So instead of think of this as image of the map, think of this as how valuable is a feature in that area? How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image, and then it skips over and says, I see a 3 in this image, and it says, oh, this one is rated as a 4. We don't want to sum it together because then you might have like 5 1s and it'll say 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the 1s will say probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolutional neural network so far. This is where we're at right now. We have our input image coming in, and then we use our filters, and there's multiple filters on there that are being developed to kind of twist and change that data. And so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image. And if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there that is looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions. Some strange data setups that aren't doing images but looking at other things, they can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening is a process of converting all of the resultant 2-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map. Maybe that's the bird wing, and it has values 6, 8, 4, 7, and we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. As you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value, which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer, our final output layer that says bird, cat, or dog. So, quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there because it's all building multiple layers off the different filters. Then goes through the ReLU as its activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it, and then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification in the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated. Not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset, from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird, but we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And then if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. Before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see under data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the image using matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what's going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape, we're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You could look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle, that's this part right here, and then finally we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type, this is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let me just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. you'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus a float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what x0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images. It's very easy to look at them, and they've been reshaped to fit our view and what the matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out. And we'll have our vector coming in and our values equal 10. What this means is that we have the 10 values, the 10 possible labels. And remember, we don't look at the labels as a number, because a car isn't one more than a horse. That'd be just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a numpy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. And let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper. And we'll start by initializing it. Now, there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self-all train batches. So we're going to make an array of all those different images. And then, of course, we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up the self-training images at this point, and that's going to go to a numpy array VStack. And in there, we're going to load up, in this case, the data for D and self, all trained batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a NumPy array. And then it's always nice to get the training length, and that's just a total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images, and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32, and we're going to switch that around so that now we have each of our images that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course, we want to go ahead and they run this where you say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels, and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once, so we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case, I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self-I equal to 0. So what we're looking at here is we're going to create X. We're going to get the next batch from the very initialized. We've already initialized it for 0. So we're going to look at X from 0 to batch size, which we set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self-I plus batch size because the self-I is going to keep changing. And then finally, we increment the self-I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in, and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the CFAR helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into two parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch, to set up the next batch, since we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float64 to float type, or is treated as an NP float64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals tf placeholder tf float32. We just talked about the float64 versus the NumPy float. We're actually just going to keep this at float32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches, that's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder tf float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this, we don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes it's looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a placeholder for that also. And we'll run this, so it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically, but we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. We're going to go ahead and work on our convolutional 2D, our max pool, so we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions, and let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. We just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case, we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the Conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias, shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it, and of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes, and then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the the one that works the best, at least so far. I'm sure that will change. And then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2, or whatever it is, that's what goes into the pooling, of what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally, we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here, we're going to create our normal full layer. So at some point, we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out, create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2x2, and we put in the convolutional one that we just created, the convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so notice to look at the first model and set the data accordingly. Set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flattened layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4x4 going in, let's do 8x8x64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling. And then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat, and then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there in a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a Y-predict, which is going to equal the normal full 1 dropout and 10, because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up on what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, D-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the Y predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer. And then train our optimizer and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4-4 and use different numbers there, they change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. An exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is where the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the mean, the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the back propagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights in your different nodes that are coming out. Here's our node coming out, and it has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one more variable in here. And we're going to create a variable to initialize all the global TF variables. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow and then initializes those variables. So it's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there, which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and Graph as just general graphing. But they talk about a graph session. So we're going to go ahead and run the model. And let's go ahead and walk through this, what's going on here. And let's paste this data in here. And here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run. So we're going to do with TF session as session right here. We've created our variable session. And then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, what is that? 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. In the first process is we're going to do a session run. We're going to take our train. We created our train variable or our optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created. And we have x equals batch 0 coming in, y true, batch 1. Hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf argument y prediction 1, tf.arg max y true, comma 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the TF cast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run accuracy feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this. Oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our current, we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0, it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. First, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because that doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we'd be looking the other way. But 0.0, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. And you can see we finished with this model at 0.5135, so still good. And if we look at when they ran this in the other end, remember there's a lot of randomness that goes into it when we seed the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is. And now that we have a solid running model on accuracy, let's go ahead and take a look at what we covered today. We did cover a lot because this is a very complicated subject, and it's not so much complicated in any individual step. It just has a lot of steps involved. So today we covered what is a convolutional neural network. And you can see we have the pictures coming in to the input layer, to the hidden layers, to the output layer, and then getter rows. We talked about the very basics at the beginning. And we discussed how a CNN recognizes images. And the very basics is we converted the image into a pixel map of zeros and ones. Then we dived into layers in a convolutional neural network. And we had our convolutional layer, our fully convected layer, our ReLU layer, and our pooling layer. And we looked at pooling layer. It reduces the data down to a smaller amount by finding the, first it finds the matches and then it finds the maximum value in that match. And we discussed all the different layers in there. We went into the fully connected layer, which is the neural networks you're probably used to dealing with, where we're just building a forward propagation neural network. And we connected them all together. And you can see here, we took the bird, we did our feature extraction in multiple hidden layers, where we had our convolution, which then generated those little individual filters, and we had our ReLU, and then we took the ReLU, we max pooled those, and then we took all of those pooled values at the end, so they've been reduced to smaller mappings. We've reduced that, and then we fed that into the fully connected layer. And then finally, we went into the use case implementation using CNN, and we walked through a full demo on the coding on there. With that, I want to thank you for joining us today.
Do you know, friends, that according to the lending statistics, the demand for AI and ML specialists is projected to surge by 40% between 2023 to 2027. And on an average, an ML engineer is expected to earn around $133 and $336 per year. So if you are an aspiring ML engineer and thinking about what innovative projects you can show in your portfolio, then your wait is over. Because in this video, I'll be covering 8 amazing ML projects that you can showcase in your resume. So guys, let's start first with a beginner level project. And the first project that we are going to encounter, that is home value prediction. So guys, this project aims to develop a predictive model to estimate the value of residential properties. The model will analyze various features such as location, square, footage, number of bedrooms and bathrooms, age of the property, and other relevant factors. By leveraging historical property data, the model will be able to provide accurate home value predictions, which can be useful for real estate agents, buyers, and sellers. So guys, the programming language that we are going to use all over here will be Python, and machine learning libraries that we will be using will be scikit-learn, TensorFlow, Keras, and for data handling libraries we have Pandas, NumPy, and for visualization we have to use Matplotlib and Seaborn. Now what will be the approach for this one, guys? So guys, the first one that we have a data collection. So here, what is going to happen, guys? So first you have to collect the historical property data from the sources like Zillow, retailer.com. You can also get database from the public real estate databases like Kaggle datasets, where you have Zillow home value prediction. Ensure that the dataset include features like location, where you have latitude, longitude, square footage, number of rooms, year built, property type, and previous sales. The next step that comes is data cleaning. You have to handle the missing values by using imputation techniques or removing incomplete records, removing outliers that may skew the model's prediction, normalize or standardize the data to ensure consistency. The third one that we have is feature engineering. You have to create new features such as proximity to schools, crime rates, and access to the public transportation. Encode categorical variables, example property type, location, using techniques like one-hot encoding. Generate interaction features that capture relationship between existing features. The fourth one that we have is model selection. Use regression models like linear regression, random forest, gradient boosting, neural networks. Experiment with different models to identify the best performing one. Now, in the next phase, all you have to do, guys, is model training and evaluation. Split the data set into training and test sets. Train the model on the training set and evaluate their performance on the testing set using metrics like RSME, which means root mean squared error. You can use cross-validation to ensure the model's robustness and avoid overfitting. The sixth one that we have all over here is hyperparameter tuning. You can optimize the model's hyperparameter using techniques such as grid search or random search to improve accuracy. And if you're looking forward to deploy your model, then you can develop a web interface using Flask or Django to allow users to input property features and get predictions. You can deploy the model on the cloud platform like AWS for scalability. Now, if we talk about the complexity level of this, we all know that it is a beginner level project. Now let us move on to the one more set, that is music genre classification and generation. So guys, this is also one of the most beginner level project. This project aims to develop a system that can classify music tracks into different genres and generate new music composition within specified genre. The goal is to build a model that analyzes audio features to categorize music and uses deep learning techniques to create new music. This project introduces advanced concept of audio processing, deep learning, and generative models. So guys, what will be used in this? So we'll have programming language that will be Python. For audio processing, we'll be using Librosa. For machine learning libraries, we'll be using TensorFlow, Keras, PyTorch. For data handling libraries, we'll be using Pandas, NumPy. For visualization, we'll be using Matplotlib, Seaborn. For the dataset, guys, you can use GTZan music genre dataset, or you can get it from Free Music Archive. So guys, in the first phase, we are going to have data collection. You can obtain datasets containing music tracks and their corresponding genre from the sources, from GTZan music genre dataset and the Free Music Archive. Ensure that a dataset includes diverse genre and substantial number of tracks per genre. Next, we'll go for data preprocessing. Use library Librosa to load and preprocess audio files, including feature extractions such as mil frequency, cepstral coefficients, chroma features, and spectral contrast. You can normalize the extracted features to ensure consistent input for the given models. Now, if we talk about feature engineering, guys, you can extract additional features from the audio files such as tempo, beat, zero crossing rate, etc. Create a feature matrix that represents the extracted audio features. Then go for the model selection. Use convolutional neural network or recurrent neural networks for the music genre classification. Split the dataset into training and testing dataset. Now, if we talk about model training and evaluation, guys, then you can train the selected classification model on the training set. Evaluate the model's performance on the testing set using metrics like accuracy, precision, recall, and F1 score. Use confusion matrices to understand the classification performance across different genres. Now, if we talk about model selection and training for the music generation, what you will do, guys, you can use the generative adversarial networks or recurrent neural networks such as LSTM, long short-term memory for music generation. Train the generative model on the dataset to create new music sequences. Next, we have model training and evaluation. You can train the generative model on sequences of audio features. You can evaluate the generated music by listening tests and by objective metrics like inception score or Friese audio distance. If I talk about hyperparameter tuning, guys, you can optimize the model. You can use the hyperparameters using techniques like grid search or random search to improve performance. If I talk about deployment, guys, you can deploy these models on cloud platforms like AWS. Now, let us move on to our next project. So guys, the complexity of this project is at the beginner level. Now, let us move to the intermediate level projects. Next project that we have all over here is sentiment analysis of Twitter data. This project aims to develop a sentiment analysis model that can classify tweets as positive, negative, or neutral. The goal is to analyze public sentiment on various topics or events using natural language techniques. So guys, what will be used all over here? So in this, we will have programming language like Python, okay, NLP libraries, NLTK Spacey. For machine learning libraries, you can use scikit-learn, TensorFlow, Keras. For data handling libraries, we have Pandas, NumPy. For visualization, we have Matplotlib, Seaborn, and we can use the API Twitter for data collection. Now, how you're going to work on it, guys? So guys, if I talk about the data collection, use a Twitter API to collect tweets based on specific hashtags like keywords or topics. Extract relevant fields like tweet text, user information, timestamp, etc. Then if I talk about data preprocessing, guys, clean the tweet text by removing special characters, links, mentions, hashtags, and stop words. Tokenize the text and perform lemmaization or stemming to reduce the words to their base form. Next, if we talk about feature engineering, guys, you convert the clean text data into numerical representation using TF-IDF, bag of words, or word embedding. Now, if I talk about model selection, guys, you can choose the classification algorithms such as logistic regression, Naive Bayes, or LSTM. Split the data set into training and testing data set. Now, if I talk about model training and evaluation, then you can train the selected model on the training set. Evaluate the model's performance on the testing set using metrics like accuracy, precision, recall, and FN score. Use cross-validation to ensure the model's robustness. If I talk about hyperparameter tuning, guys, you can optimize the model's hyperparameters using grid search or random search to improve the performance. For deployment, which can be optional, you can deploy your model on AWS for real-time sentiment analysis. So if I talk about the complexity level, guys, its complexity is intermediate. So guys, our next project is customer segmentation using k-means clustering. This project aims to segment customers into distinct groups based on their purchasing behavior and demographic information. The objective is to understand customer segments and tailor marketing strategies accordingly. So guys, what programming languages we'll be using? So basically, we'll be using Python. For machine learning libraries, we'll have scikit-learn. For data handling libraries, we'll have pandas, numpy. For visualization libraries, we'll have matplotlib, seaborn. And the dataset source will be e-commerce transaction data. How we are going to work on this one? For data collection, we can obtain a dataset of e-commerce transactions that include customer demographics, purchase history, and product information. Next, we'll have data preprocessing. For data preprocessing, we are going to do the cleaning of the data by handling the missing values and outliers. Then, for feature engineering, we are going to create features like total purchase amount, purchase frequency, and recency of the purchases. Then we are going to proceed for the model selection. You can use k-means clustering to segment the customers into distinct groups. You can determine the optimal number of clusters using methods like elbow methods or Silhouette score. Now, if I talk about model training and evaluation, you can train the k-means model on the processed dataset. You can evaluate the quality of clusters by analyzing intra-cluster and inter-cluster distances. Next, we have the evaluation. You can visualize the clusters using techniques like PCA, principal component analysis, TSNE, etc. Next, we have the hyperparameter tuning. Now you can tune this model and interpret the characteristic of each segment. You can develop a target marketing strategies for each segment based on unique behavior and preferences. Now, deployment is optional. You can develop a dashboard using Flask or Django to visualize customer segments and track marketing campaigns. So guys, if I talk about the complexity of this project, so this is an intermediate level project. So guys, for dataset, you can use the Kaggle's customer segmentation dataset, which is available at the Kaggle's platform. Now, the third intermediate level project that we have all over here is building a chatbot with RASA. This project aims to build an intelligent chatbot using RASA framework. The chatbot will be capable of understanding user queries and providing appropriate responses, making it useful for customer support, personal assistance, or information retrieval. What languages we are going to use? So it will be Python based. We'll have the NLP libraries like RASA, NLTK, Spacy. For machine learning libraries, we are going to have scikit-learn, TensorFlow, Keras, etc. For data handling libraries, we are going to use pandas, numpy. So guys, this was what we are going to do it. And how you can work on this one? By collecting the data, collect the conversation data and FAQs from the target domain. Annotate the data to create training examples for the chatbot. Next comes is data preprocessing. Clean the text data by removing special characters and normalizing the text. You can tokenize and limitize the text to prepare for a training. The third one, we have the models training. You can use RASA's NLU's component to train a model for intent recognition and entity extraction. You can define the dialogue management policies to handle different conversation flows. Next, guys, you can perform the feature engineering and integration. You can integrate the RASA's NLU and core components to build complete chatbot. You can connect the chatbot to messaging platform like Facebook, Messenger, etc. For model selection and testing, what you can do, guys, you can test this chatbot with various inputs to ensure that it handles the scenarios appropriately. And you can also select the right model using this. Now, if I talk about model training, guys, what do you have to do? You have to collect the user feedback and conversational logs to continuously work on training the model. Next, similarly, you have to retrain the model periodically with the new data to see how it is working. So that will be your evaluation. Now, for the hyperparameter tuning, what are you going to do, guys? You have to check in those scenarios where it is able to tune up with those scenarios where it can handle the input appropriately. And next is deployment. So guys, for deploying it, you can use AWS. So guys, for a data set, you can use RASA's open source. So that's a very good data set for you to proceed. So guys, if you talk about difficulty of this project, this is an intermediate level project. Now let us move on to the advanced level projects. For advanced level projects, the first one that comes up to my mind is movie similarity from plot summaries. Now, this project aims to develop a system that can find out recommended movies similar to a given movie based on their plot summaries. By analyzing the textual content of the movie plot summaries, the model will identify similarities and suggest movies with similar themes, storylines, or genres. This project introduces beginners to natural language processing, text similarly measures, and recommendation systems. What languages we are going to use, guys? We'll be using Python, NLP libraries like NLTK, Spacey, machine learning libraries like scikit-learn, data handling libraries like pandas, numpy, visualization we can use numpy, and dataset source will be IMDb or Kaggle. So guys, this process is also involving the data collection, then you have to go for data cleaning, then feature engineering, next model selection. So similar process as I have discussed in other projects, so you have to also go through the same one. Next, what do you have to do, guys? Similarly, what do you have to do? You have to train the model, then evaluate the model, then hypertune it, and finally proceed for the deployment. So this is overall process of this project. Try to research on the website a lot, like how you can extract it. So guys, you can use Kaggle or Towards Data Science to research more about this project. Now guys, if I talk about the difficulty of this project, and this is an advanced level project. Now, let us move on to the next one that we have all over here. That is image segmentation project for brain tumor prognosis. This is a very amazing project and definitely you can put up on your portfolio. Basically guys, this project aims to develop an image segmentation model to identify and delineate brain tumors from MRI scans. The goal is to accurately segment the tumor regions which can aid in prognosis, treatment planning, surgical interventions. This project introduces intermediate level concepts of computer vision, deep learning, and medical image analysis. So guys, what we'll be using all over here? For programming languages, we can use Python. For deep learning libraries, we can use TensorFlow, Keras, PyTorch. For image processing libraries, we can use OpenCV, scikit-image. For data handling libraries, we can use Pandas, NumPy. For visualization, we can use Matplotlib, Seaborn. Now, if I talk about what is the process of developing this project, the first step will be the same, data collection. So next step, you have to go for data pre-processing. Third step, you have to do the model selection where you can use CNN models for image segmentation task. Then you go for model selection. Moving ahead, you're going to have the model training and evaluation. You have to split the data set into training and validation and testing data sets. Next, proceed for the evaluation phase. Okay, evaluate the model with certain metrics. So here I can give you certain idea, like you can use dice coefficient, intersection over union, or accuracy. Then go for hyperparameter tuning, where you have to optimize the model's hyperparameters. You can use grid search or random search as we have discussed. And finally, you can deploy this model on AWS. Now guys, we have come to the final project. This is also a very amazing project, guys. So guys, the complexity level of this project is advanced level. Now, let us move on to our final project, that is the impact of climate change on birds. This is a very amazing project and definitely you can add it on your resume. This project aims to analyze the impact of climate change on the bird population and migration patterns. By examining various climatic factors and their correlation with bird species data, the project seeks to predict how climate change might affect bird behavior and distribution. This project will introduce you some advanced level concepts like time series analysis, environmental data modeling, etc. So guys, what programming languages we'll be using? For data analysis, you can see we'll have Pandas, NumPy. For machine learning libraries, we are going to have scikit-learn, TensorFlow. For visualization, we are going to have Matplotlib, Plotly. For geospatial, we are going to have GeoPandas, Folium. For data source, we are going to have public data sets on bird observation and climate data sources from eBird. Now, what will the process flow for this one, guys? First, you have to proceed for data collection. Gather bird observation from the data like eBird, which provides extensive record of bird sightings. Okay. And for climate data, you can collect it from NOAA, including temperature, precipitation, and other relevant climatic factors over the time. And similar next process will be the data pre-processing. Then you have to proceed for feature engineering. Then you have to go for model selection. Okay. Moving ahead, you have to go for model training, then evaluation, then hyperparameter tuning, and finally, you have to deploy the model. So research about this project, see what models you are going to use. Suppose I can give you a hint about this. You can use time series analysis models like ARIMA, or ML models. You can also use random forest or gradient boosting for predicting impact on the bird population. So guys, use Google exhaustively to research about this project. This is also a very amazing project and it's going to give you a lot of idea. Now, if I talk about the complexity level of this, it is an advanced level project.
Welcome to Deep Learning Interview Questions. My name is Richard Kirshner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Today we're going to help you prepare for interview questions dealing with deep learning. And we're going to go from the very basics of neural networks and deep learning into some of the more commonly used models, so that you can have an understanding of what kind of questions are going to come up and what you need to know in interview questions. We'll start with a very general concept of what is deep learning. This is where we take large volumes of data, in this case on cats and dogs or whatever. A lot of times you use a training setup to train your model. Remember, it's kind of like a magic black box going on there. Then we use that to extract features or extract information, and in this case classify the image of a cat and a dog. So the primary takeaway when we're talking about deep learning is it learns from large volumes of structured and even unstructured data and uses complex algorithms to train neural network. It also performs complex operations to extract hidden patterns and features. And if we're going to discuss deep learning in this very simplified overview, then we also have to go over what is a neural network. This is a common image you'll see of a drawing of a forward propagation neural network. And it's a human brain inspired system which replicate the way humans learn. So this is inspired how our own neurons in our brain fire, but at a much simplified level. Obviously it's not ready to take over the human population and be our leader yet, not for many years. It's very much in its infant stage. But it's inspired by how our brains work. And they use a lot of other inspirations. You can study brains of moths and other animals that they've used to figure out how to improve these neural networks. The most common one consists of 3 layers of network, and this is generally how you view these networks, is you have an input, you have a hidden layer, and an output. And the neural network is broken up into many pieces, but when we focus just on the neural network, it's always on the hidden layers that we're making all the adjustments and figuring out how to best set up those hidden layers for their functions to both train faster and to function better. When we look at this, of course, we have our input, hidden, and output. Each layer contains neurons called as nodes that perform various operations. And you can see here we have the list of the nodes. We have both our input nodes and our output nodes, and then our hidden layer nodes. And it's used in deep learning algorithm like CNN, RNN, GAN, etc. We'll address some of these models a little closer, at least the most common models, as we go down the list and we study the deep learning and the neural network framework. Let's start with what is a multi-layer perceptron, or MLP, a lot of time is referred to. And you'll see these abbreviations. I'll be honest, I have to write them down on a piece of paper and go through them because I never remember what they all mean, even though I play with them all the time. What is a multi-layer perceptron? Well, if you look at the image on the right, it's very similar to what we just looked at. You have your input layer, your hidden layer, and your output layer. And that's exactly what this is. It has the same structure of a single layer perceptron with one or more hidden layers, except the input layer. Each node in the other layers uses a nonlinear activation function. What that means is your input layer is your data coming in, and then your activation function is based upon all those nodes and weights being added together, and then it has the output. MLP uses supervised learning method called backpropagation for training the model. Very key word there is backpropagation. Single layer perceptron can classify only linear separable classes with binary output, 0, 1, but the MLP can classify nonlinear classes. So let's break this down just a little bit. The multi-layer perceptron with an input layer and a hidden layer and an output layer. As you see that it comes in there, it adds up all the numbers and weights depending on how your setup is, that then goes to the next layer, that then goes to the next hidden layer if you have multiple hidden layers, and finally to the output layer. The backpropagation takes the error that it sees. So whatever the output is, it says, hey, this has an error to it, it's wrong. And then sends that error backwards from where it came from. And there's a lot of different functions used to train this based on that error and how that error goes backwards in the nodes. So forward is you get your answers, backward is for training. You see this every day. Even my Google Pixel phone has this. They train the neural network, which takes a lot more data to train than it does to use. And then they load up that neural network into, in this case I have a Pixel 2, which actually has a built-in neural network for processing pictures. And so it's just the forward propagation I use when it processes my photos. But when they were training it, you use the back propagation to train it with the errors they had. We'll be coming back to different models that are used. For right now, though, multi-layer perceptron, MLP. Put that down as your vocabulary word. And, of course, backpropagation. What is data normalization and why do we need it? This is so important. We spend so much time in normalizing our data and getting our data clean and setting it up. So when we talk about data, there's a pre-processing step to standardize the data. So whatever we have coming in, we don't want it to be a 1 gigabyte file here, a 2 gigabyte picture here, and a 3 kilobyte text there. Even as a human, I can't process those all in the same group. I have to reformat them in some way that loops them together so that it's standardized format. We use this data normalization in pre-processing to reduce it and eliminate data redundancy. A lot of times the data comes in and you end up with two of the same images or the same information in different formats. Then we want to rescale values to fit into a particular range for achieving better convergence. What this means is with most neural networks, they form a bias. We've seen this recently in attacks on neural networks where they light up one pixel or one piece of the view and it skews the whole answer. So suddenly, because one pixel is really bright, it doesn't know what to do. Well, when we start rescaling it, we put all the values between, say, -1 and 1, and we change them and refit them to those values. It helps get rid of that bias, helps fix for some of those problems. And then finally, we restructure the data and improve the integrity. We want to make sure that we're not missing values or we don't have partial data coming in. One way to look at this is bad data in, bad data out. So you want clean data in and you want good answers coming out. One of the most basic models used is a Boltzmann machine. So let's address what is a Boltzmann machine. And if you know, we just did the MLP, multi-layer perceptron. So now we're going to come into almost a simplified version of that. And in this we have our visible input layer and we have our hidden layer. The Boltzmann machines are almost always shallow. They're usually just two-layer neural nets that make stochastic decisions whether a neuron should be on or off, true, false, yes, no. First layer is the visible layer, and second layer is the hidden layer. Nodes are connected to each other across layers, but no two nodes of the same layer are connected. Hence it is also known as restricted Boltzmann machine. Now that we've covered a basic MLP or multi-layer perceptron, and we've gone over the Boltzmann machine, also known as the restricted Boltzmann machine, let's talk a little bit about activation formulas. And this is a huge topic that can get really complicated, but it also is automated, so it's very simple. So you have both a complicated and a simple at the same time. So what is the role of activation functions in a neural network? Activation function decides whether a neuron should be fired or not. That's the most basic one. And that actually changes a little bit because it's either whether it's fired or not, in this case activation function, or what value should come out when it's fired. But in these models we're looking at just the Boltzmann restricted layers. So this is what causes them to fire. Either they don't or they do. It's a yes or no, true, false, all or nothing. It accepts the weighted sum of the inputs, the bias, as input to any activation function. So whatever our activation function is, it needs to have the sum of the weights times the input. So each input, if you remember on that model, and let's just go back to that model real quick. And then you always have to add a bias. And you can look at the bias if you remember from your Euclidean geometry. You draw a straight line. Formula for that line has a y coordinate at the end. It's always cx plus m or something like that, where m is where it crosses the y coordinates if you're doing a straight line. With these weights, it's very similar, but a lot of times we just add it in as its own weight. We take it as a node of a one value coming in, and then we compute its new weight, and that's how we compute that bias, just like we compute all the other weights coming in. The node which gets fired depends on the y value, and then we have a step function. And the step function, this is where, remember I said it's going to get complicated and simple all at the same time. We have a lot of different step functions. We have the sigmoid function, we have just a standard step function, we have the ReLU, it's pronounced like ray, the ray from the sun, and lu, like a name, so ReLU function. And we have the tangent h function. And if you look at these, they all have something similar. They all either force it to be one value or the other. They force it to be, in the case of the first three, a 0 or a 1, and in the last one, it's either a -1 or a 1. And you can easily convert that to a 0, 1, yes, no, true, false. And on this, one of the most common ones is the step function itself, because there is no middle value. There is no discrepancy that says, well, I'm not quite sure. But as you get into different models, probably the most commonly used, it used to be the sigmoid was most commonly used, but I see the ReLU used more often. Really, depending on what you're doing, you just have to play with these and find out which one works best, depending on the data in your output. The reason to have a non-0-1 answer or something kind of in the middle is when you're looking at this and it's coming out, you can actually process that middle ground as part of the answer into another neural network. So it might be that the ReLU function says, hey, this is only a 0.6, not a 1. And even though the 1 is what's going into the next neural network or the next hidden layer as an input, the 0.6 value might also be going in there to let you know, hey, this is not a straight up 1 or straight up 0, it's someplace in the middle. This is a little uncertain what's coming out here. So it's a very powerful tool. But in the basic neural network, you usually just use the step function. It's yes or no. Let's take a big step back and take a kind of an overview. The next function is, what is a cost function that we're going to cover? This is so important because this is your end result that you're going to do over and over again and use to decide whether the model is working or not, whether you need to try a different step function, whether you need to try a different activation, whether you need to try a fully different model used. So what is the cost function? Cost function is a measure to evaluate how good your model's performance is. It is also referred as loss or error, used to compute the error of the output layer during backpropagation. There's our backpropagation where we're training our model. That's one of our key words. Mean squared error is an example of a popular cost function. And so here we have the cost function C equals half of y minus y predicted, and then you square that. So the first thing is, real quick, if you haven't done statistics, this is not a percentage. It's not a percentage of how accurate it is. It's just a measurement of the error. And we take that error if we're training it, and we push that error backwards through the neural network, and we use that through the different training functions, depending on what model you're using, to train the neural network. So when you deploy the network, you're usually done training it because it takes a lot of computational force to train it. This is a very simple model. And so you deploy the trained one, but we want to know how your error is. And so how do we do that? Well, you split your data. Part of your data is for training and part of your data is for testing. And then we can also test the error on there. So it's very important. And then we're going to go one more step on this. We got to look at both the local and the global setup. It might work great to test your data on what you have on your computer, but that's different than in the field. So when we're talking about all these different tests in the error test, as far as your loss, you want to make sure that you're in a closed environment when you do your initial testing, but you also want to open that up and make sure you follow up with the testing on the larger scale of data, because it will change. It might not fit the larger scale. There might be something in there in the way you brought the data in specifically, or the data group you used, or any of those could cause an error. So it's very important to remember that we're looking at both the local and the global context of our error. And just one other side note on a lot of the newer models of neural networks, by comparing the error we get on the data, our training data, with a portion of the test data, we can actually figure out how good the model is, whether it's overfitted or not. We'll go into that a little bit more as we go into some of the different models. So we have our output. We're able to figure out the error on it based on the square means usually, although there's other functions used. So we want to talk about what is gradient descent, another vocabulary word. Gradient descent is an optimization algorithm to minimize the cost function or to minimize the error. Aim is to find the local or global minima of a function. Determine the direction the model should take to reduce the error. So As we're looking at this, we have our squared error that we just figured out based on the cost function. It says how bad is my model fitting the data I just put through it. And then we want to reduce that error. So how do you figure out what direction to do that in? Well, it could be that you're looking at just that line of data coming in, so that would be a local minima. We want to know the error of that particular setup coming in. And then you have your global minima. We want to minimize it based on the overall data we're putting through it. And with this, we can figure out the global minimum cost. We want to take all those local minimum costs of each piece of data coming in and figure out the global one. How are we going to adjust this model to fit all the data? We don't want it to be biased just on 3 or 4 lines of data coming in. We want it to kind of extrapolate a general answer for all the data coming in. But this, of course, we mentioned it briefly about back propagation. This is where it really comes in handy, is training our model. Neural network technique to minimize the cost function helps to improve the performance of the network, back propagates the error, and updates the weights to reduce the error. So as you can see here is a very nice depiction of a back propagation. We have our predicted Y coming out, and then we have, since it's a training set, we already know the answer, and the answer comes back, and based on, in case of the square means was one of the functions we looked at, one of the activation functions based on cost function. That cost function then, depending on what you choose for your back propagation method, and there's a number of them, will change the weights. It will change the weight going to each of one of those nodes in the hidden layer, and then based upon the error that's still being carried back, it'll change the weights going to the next hidden layer. And then it computes an error level on that and sends that back up. And you're going to say, well, if it computes the error into the first hidden layer and fixes it, why would it stop there? Well, remember, we don't want to create a biased neural network. So we only make small adjustments on these weights. We don't make a big adjustment that changes everything right off the bat. So no matter how far back you go, you're always going to have a small amount of error, and that's still going to continue to go all the way back up the hidden layers. For right now, focus on the back propagation, is taking that error and moving it backwards on the neural network to change the weights and help program it so that it'll have the correct answers. So far, we've been talking about forward propagation neural networks. Everything goes forwards, goes left to right. But let's take a little detour and let's see what is the difference between a feed-forward neural network and a recurrent neural network. Now this is in the function, not when we're training it using the back propagation. So you've got new information coming in and you want to get the answer. And there's a couple different networks out there, and we want to know, we have a feed-forward neural network and we have a new vocabulary term, recurrent neural network. A feed-forward neural network. Signals travel in one direction from input to output. No feedback loops. Considers only the current input. Cannot memorize previous inputs. One example of one of these feed-forward neural networks, and we've covered a number of them, but one of the ones that has a big highlight nowadays is the CNN, a convolutional neural network. TensorFlow, the one put out by Google, is probably most known for their CNN, where the information goes forward. It first takes a picture, splits it apart, goes through the individual pixels on the picture so it picks up a different reading, then calculates based on that, goes into a regular feed-forward neural network, and then gives your categorization on there. Now, we're not covering the CNN today, but we do have a video out that you can look up on YouTube, put out by Simplilearn, the Convolutional Neural Network. Wonderful tutorial. Check that out and learn a lot more about the Convolutional Neural Network. But you do need to know that the CNN is a forward propagation neural network only. So it's only moving in one direction. So we want to look at a recurrent neural network. Signals travel in both directions, making it a looped network. Considers the current input along with the previous received inputs for generating the output of a layer. Has the ability to memorize past data due to its internal memory. And you can see they have a nice image here. We have our input, and for some reason they always do the recurrent neural network in reverse from bottom up in the images. Kind of a standard, although I'm not sure why. Your X goes into your hidden layer, and your hidden layer, the answer for part of the answer from that it generates feeds back into the hidden layer. So now you have an input of both X and part of the hidden layer, and then that feeds into your output. Now if we go back to the forward, let me just go back a slide, and we're looking at our forward propagation network. One of the tricks you can do to use just a forward propagation network is if you're in what they call a time sequence. That's a good term to remember, or a time series, meaning that it's sequential data. Each term comes after the other. You can trick this by creating your input nodes as with the history. So if you know that you have values 1, 5, and 7 going in, and you know what the output is from what those outputs are, you can expand the input to include the history input. That's one of the ways to trick a forward propagation network into looking at that. But when you do with a recurrent neural network, you let the hidden layer do that for you. It sends that data and reprocesses it back into itself. What are some of the applications of recurrent neural network? The RNN can be used for sentiment analysis and text mining. Getting up early in the morning is good for health. And it's a positive sentiment. One of the catches you really want to look at this when you're looking at the language is that I could switch this around and totally negate the meaning of what I'm doing, so it would no longer be positive. So when you're looking at a sentence, knowing the order of the words is as important as the meaning of the words. You can't just count how many good words there are versus bad words to get a positive sentiment. You now have to know what they're addressing. And there's lots of other different uses. Kids are playing football, or soccer as we call it in the US. RN can help you caption an image. So based on previous information coming in, it refeeds that back in, and you have a image setter. And then time series problems like predicting the prices of stocks in a month or quarter or sale of products can be solved using an RNN. And this is a really good example. You have whatever your stocks were doing earlier this month will have a huge effect on what they're doing today if you're investing. So having an RNN model, a recurrent neural network, feeding into itself what was happening previously allows it to take that model and program in that whole series without having to put in the whole a month at a time of data. You can only put in one day at a time, but if you keep them in order, it will look back and say, oh, this is because of what happened yesterday. I need some information from that, and I'm going to use that to help predict today's, and so on and so on. We're going to go back to our activation functions. Remember I told you ReLU is one of the most common functions used? So let's talk a little bit more about ReLU and also softmax. Softmax is an activation function that generates the output between 0 and 1. It divides each output such that the total sum of the outputs is equal to 1. It is often used in the output layers. Softmax L of the n equals e to L of the n over the absolute value of e to the L. So what does this function mean? I mean, what is actually going on here? So we have our output nodes, and our output nodes are giving us, let's say they gave us 1.2, 0.9, and 0.4. As a human being, I look at that and I say, well, the greatest value is 1.2, so whatever category that is, if you have 3 different categories, maybe you're not just doing if it's a cat or it's a dog or, let's say it's a cow. Maybe we had cats and dogs earlier. Why the cats and dogs are hanging out with a cow, I don't know. But we have a value, and it might say 1.2 is a cat, 0.9 is the dog, and 0.4 is a cow. For some reason it thinks that there's a chance of it being any one of these 3 items, and that's how it comes out of the output layer. Well, as a human, I can look at 1.2 and say this is definitely what it is. It's definitely a cat or whatever it is. Maybe it's looking at different kinds of cars might be a better, whether it's a car, truck, or a motorcycle. Maybe that'd be a better example. Well, from a computer standpoint, that might be a little confusing because they're just numbers waving at us. And so with the softmax, we want all those numbers to always add up to 1. So when I add 3 numbers together, I want the final output to be 1 on there. And so it goes through this formula, changes each of these numbers. In this case, it changes them to 0.46, 0.34, and 0.20. They all add up to 1. And that's a lot easier to register because it's very set. It's a set output. It's never going to be more than 1. It's never going to be less than 0. And so you can see here that there's probably a pretty high chance that it's the first one. So as a human being, we have no problem knowing that. But this output can then also go into, say, another input. So it might be an automated car that's picking up images, and it says that image in front of us is probably a big truck. We should deal with it like it's a big truck. It's probably not a motorcycle, or whatever those categories are. That's the softmax part of it. But now we have the ReLU. Well, where's the ReLU coming from? Well, the ReLU is what's generating the 1.2 and the 0.9 and the 0.4. And so if you remember, our ReLU stands for Rectified Linear Unit and is the most widely used activation function. We looked at a number of different activation functions, including tangent H, the step function. I remember I said the step function is really used if that's what your actual output is, because then you know it's a 0 or 1. But the ReLU, if you have that as your output, you now have a discrepancy in there. And if that's going into another neural network or another process, having that discrepancy is really important. And it gives an output of x if x is positive and 0 otherwise. So it says my x value is going to be somewhere between 0 or 1. And then the usually, unless it's really uncertain, the output's usually a 1 or 0. And then you have that little piece of uncertainty there that you can send forward to another network, or you can look at to know that there's uncertainty involved. And is often used in the hidden layers. This is what's coming out of the hidden layers into the output layer usually. Or as we reference the convolutional neural network, the CNN, which you'd have to go to another video to review, the ReLU is the most common used for convolutional part of that network. It has a bunch of little pieces that are very simplified, looking at all the different images or different sections of the map, and the ReLU works really good for that. And like I said, there's other formulas used, but this is the most common one, and you'll see that in the hidden layers going maybe between one layer and the next layer. So just a quick recap, we have our softmax, which means that if you have numerous categories, only one of them is going to be picked, but you also want to have some value attached to it, how well it picked it. And you put that between 0 and 1, so it's very standardized. So we have our softmax. We looked at that. Let's go back one. We looked at that here, where it transforms the numbers. And then we have our ReLU function, which takes the information and the summation and puts it between a 0 and a 1, where it's either clearly a 0 or, depending on how confident our model is, it'll go between the 0 and 1 value. What are hyperparameters? Oh, this is a great interview question. Hyperparameters. When you are doing neural networks, this is what you're playing with most of the time once you've gotten the data formatted correctly. A hyperparameter is a parameter whose value is set before the learning process begins, determines how a network is trained and the structure of the network. This includes things like the number of hidden units, how many hidden layers are you going to have, and how many nodes in each layer. Learning rate. Learning rate is usually multiplied once you've figured out the error and how much you want to change the weights. We talked about, or I mentioned it early just briefly, you don't want to just make a huge change, otherwise you're going to have a biased model. So you only take some little incremental changes, and that's what the learning rate is those small incremental changes. Epochs. How many times are you going to go through all the data in your training set? So one epoch is one trip through all the data. And there's a lot of other things depending on which model you're working with and which programming script you're working with. Like the Python sklearn package will have it slightly different than, say, Google's TensorFlow package, which will be a little bit different than the Spark machine learning package. So these are just some examples of the hyperparameters. And so you see in here we have a nice image of our data coming in, and we train our model, then we do a comparison to see how good our model is, and then we go back and we say, hey, this model's pretty good, but it's biased. So then we send it back and we change our hyperparameters to see if we can get an unbiased model, or we can have a better prediction on it that matches our data closer. What will happen if learning rate is set too low or too high? We have a nice couple graphs here. We have one over here that says the learning rate set too low, and you can see that it slowly works its way down the curve. And on the right, you can see a learning rate set too high. It's just bouncing back and forth. When your learning rate is too low, that's what we studied at 2 slides ago, that's what the learning rate was, training of the model will progress very slowly as we are making very tiny updates to the weights. We'll take many updates before reaching the minimum point. So I just mentioned epoch, going through all the data. You might have to go through all the data 1,000 times instead of 500 times for it to train. Learning rate too high causes undesirable divergent behavior to the loss function due to drastic updates in weights. At times it may fail to converge or even diverge. So if you have your learning rate set too high and it's training too quickly, maybe you'll get lucky and it trains after one epoch run, but a lot of times it might never be able to train because the weights are changing too fast. They flip back and forth too easy. And you see down here we've introduced 2 new terms, converge and diverge. Converge means that our model has reached a point where it's able to give a fairly good answer for all the data we put in. All those weights have adjusted and it's minimized the error. Diverge means that the data is so chaotic that it can never manage to train to that data. The data is just too chaotic for it to train. So we have 2 new words there, converge and diverge are important to know also. What is dropout and batch normalization? Dropout is a technique of dropping out hidden and visible units of a network randomly to prevent overfitting of data. It doubles the number of iterations needed to converge the network. So here we have our standard neural network, and then after applying dropout. Now it doesn't mean we actually delete the node. The node is still there, and we're still going to use that node. What it means is that we're only going to work with a few of the nodes. A lot of times, I think the most common one right now used is 20%. So you'll drop out 20% of the nodes when you do your training. You reverse propagate your data, and then you'll randomly pick another 20 nodes the next next time you go through an epoch data training. So each time you go through one epoch, you will randomly pick 20 of those nodes not to mess with. And this allows for less overfitting of the data. So by randomly doing this, you create some, I guess it just kind of pulls some nodes off to the sides and says we're going to handle the data later on so we don't overfit. Batch normalization is a technique to improve the performance and stability of neural network. The idea is to normalize the inputs in every layer so that they have mean output and activation of 0 and standard deviation of 1. This question covers a lot of different things, which is great. It's a great interview question because it pulls in that you have to understand what the mean value is. So a mean output activation of 0, that means our average activation is 0. So when you normalize it, remember usually we're going between -1 and 1 on a lot of these. It's a very standard setup. So you have to be very aware that this is your mean output activation of 0. And then we have our standard deviation of 1. So we want to keep our error down to just a 1 value. The benefits of this doing a batch normalization is it provides regularization, it trains faster, higher learning rates, and weights are easier to initialize. What is the difference between batch gradient descent and stochastic gradient descent? Batch gradient descent. Batch gradient computes the gradient using the entire data set. It takes time to converge because the volume of data is huge and weights update slowly. So you can look at the batch as, a lot of times if you're using big data, batch the data in, but you still go through a full epoch. You still go through all the data on there. So batch gradient descent means you're going to use it to fit all the data and look for convergence there. Stochastic gradient descent. Stochastic gradient computes the gradient using a single sample. It converges much faster than batch gradient because it updates weight more frequently. Explain overfitting and underfitting and how to combat them. Overfitting happens when a model learns the details and noise in the training data to the degree that it adversely impacts the execution of the model on the new information. It is more likely to occur with nonlinear models that have more flexibility when learning a target function. An example of this would be if you're looking at, say, cars and trucks and motorcycles, it might only recognize trucks that have a certain box-like shape. It might not be able to notice a flatbed truck unless it's only a specific kind of flatbed truck or only Ford trucks because that's what it saw on the training set. This means that your model performs great on your trained data and great on maybe a small test amount of data, but when you go to use it in the real world, it leaves out a lot and is not very functional outside of your small area, your small laboratory data coming in. Underfitting, doing the opposite when you underfit your data. Underfitting alludes to a model that is neither well trained on training data nor can generalize to new information. Usually happens when there is less and improper data to train a model, has a poor performance and accuracy. So if you're using underfitted data and you generate a model and you distribute that in a commercial zone, you'll have a lot of people unhappy with you because it's not going to give them very good answers. So we've explained overfitting and underfitting, so now we want to ask how to combat them. Combating overfitting and underfitting. Resampling the data to estimate the model accuracy, k-fold cross-validation. Having a validation data set to validate the model. So when we do the resampling, we're randomly going to be picking out data, and we'll run it a few times to see how that works, depending on our random data and how we sample the data to generate our model. And then we want to go ahead and validate the data set by having our training data and then keeping some data on the side, testing data to validate it. How are weights initialized in a network? Initializing all weights to 0. All the weights are set to 0. This makes your model similar to a linear model. So if you have linear data coming in, doing a basic setup like that might work. All the neurons in every layer perform the same operation given the same output and making the deep net useless. Right there is a key word. It's going to be useless if you initialize everything to 0. At that point, be looking into some other machine learning tools. Initializing all weights randomly. Here the weights are assigned randomly by initializing them very close to 0. It gives better accuracy to the model since every neuron performs different computations. And here we have the weights are set randomly. We have our input layer, the hidden layers, and the output layer. And W equals NP random, random N. Layer size L minus 1. This is the most commonly used, is to randomly generate your weights. What are the different layers in CNN, Convolutional Neural Network? First is the convolutional layer that performs a convolutional operation. We have our other video out if you want to explore that more, so we can go into detail exactly how the convolutional layer works in the CNN as far as creating a number of smaller picture windows that go over the data. The second step is as a ReLU layer. ReLU brings nonlinearity to the network and converts all the negative pixels to 0. Output is rectified feature map. So it goes into a mapping feature there. Pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. So we have all our ReLU layer, which is pulling all these little maps out of our convolutional layer. It's taking that picture and creating little tiny neural networks to look at different parts of the picture. Then we need to pool it together, and then finally the fully connected layer. So we flatten our pooling layer out, and we have a fully connected layer recognizes and classifies the objects in the image. And that's actually your forward propagation, reverse propagation training model, usually. I mean, there's a number of different models out there, of course. What is pooling in CNN and how does it work? Pooling, used to reduce the spatial dimensions of a CNN, performs downsampling operation to reduce the dimensionality, creates a pooled feature map by sliding a filter matrix over the input matrix. I mentioned that briefly on the previous slide. It's important to know that you have, if you can see here, they have a rectified feature map. And so each one of those colors, like the yellow color, that might be one of a smaller little neural network using the ReLU. It'll just kind of go over the main picture and look at all the different areas on the main picture. So you might step 1, 2, 3, 4 spaces. And then you have another one that's also looking at features, and it has a 2, 7, 8, 5. Each one of those is a map. So it might be, the first one might be a map looking for cat ears, and the second one looking for human eyes. When it does this, you then have this rectified feature map looking at these different features. And the max pooling with a 2x2 filters and a stride of 2. Stride means instead of skipping every pixel, you're going to go every 2 pixels. You take the maximum values. And you can see over here, when we look at a pooled feature map, one of the features says, hey, I had a max value of 8, so somewhere in here we saw a human eye labeled as 8, pretty high label. And maybe 7 was a human hand, and maybe 4 was cat whiskers, or something that we thought might be cat whiskers. 4 is kind of a low number in this particular case compared to the other ones. So you have your full pooled feature map. You can see the process here as we have our stepping. We look for the max value, and then we create a pooled feature map of the maxed values. How does a LSTM network work? And that's long short-term memory. So the first thing to know is that an LSTMS are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. We did look at the RNN briefly, talked about how the hidden layer feeds back into itself. With the LSTM, it has a much more complicated feedback, and you can see here we have the hidden layer of T-1 and the hidden layer, that's what the H stands for, hidden layer of T, and the formula is going in. As we can see here, we have the hidden layers. We have T-1 and then H of T, where T stands for time. So this is a series. Remember, we're working with series, and we want to remember the past. And you can see you have your input of T, and that might be a frame in a video. As a frame comes in, they usually use in this one the tangent H activation formula, but you also see that it goes through a couple other formulas, the omega formula. And so when it combines these, that then goes into the next layer, your next hidden layer. That then goes into the data that's submitted to the next input. So you have your X of T plus 1. So when you have that coming in, then you have your H value that's coming forward from the last process. And depending on how many of these omega structures you put in there, depends on how long-term the memory gets. So it's important to remember this is more for your long-term recurrent neural networks. The 3 steps in an LSTM. Step 1 decides what to forget and what to remember. Step 2 selectively updates cell state values. So based on what we want to remember and forget, we want to update those cell values. And then decides what part of the current state make it to the output. So now we have to also have an output on there. What are vanishing and exploding gradients? This is a great question that affects all our neural networks. While training an RNN, your slope can become either too small or too large, and this makes the training difficult. When the slope is too small, the problem is known as vanishing gradient. So our slope, we have our change in x and our change in y. When the slope decreases gradually to a very small value, sometimes negative, and makes training difficult. When the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. The slope grows exponentially. You can see a nice graph of that here. Issues in gradient problem: long training time, poor performance, and low accuracy. What is the difference between epoch, batch, and iteration in deep learning? Epoch. An epoch represents one iteration over the entire data set. So that's everything you're going to go ahead and put into that training model. Batch. We cannot pass the entire data set into the neural network at once, so we divide the data set into a number of batches. And then iteration. If we have 10,000 images as data and a batch size of 200, then the epoch should run 10,000 times over 200. So that means we have our total number over the 200 equals 50 iterations. So in each epoch, we're running over all the data set, we're going to have 50 iterations. And each of those iterations includes a batch of 200 images in this case. Why TensorFlow is the most preferred library in deep learning? Well, first, TensorFlow provides both C++ and Python APIs that makes it easier to work on. Has a faster compilation time than other deep learning libraries like Keras and Torch. TensorFlow supports both CPUs and GPUs computing devices. So right now TensorFlow is at the top of the market because it's so easy to use for both programmer side and for hardware side and for the speed of getting something up and running. What do you mean by tensor in TensorFlow? Tensor is a mathematical object represented as arrays of higher dimension. These arrays of data with different dimensions and ranks that are fed as input to the neural network are called tensors. And you can see here we have a tensor of dimensions 5, 4. So it's a two-dimensional tensor coming in. You can look at an image like this, that each one of those pixels is a different value if it's a black and white. So it might be 0 and 1s, and then each one represents a black and white image. In a color photo, you might either find a different value system, or you might have a tensor value that has the XY coordinates as we see here, plus the colors. So you might have 3 more different dimensions for the 3 different images, the red, the blue, and the yellow coming in. And even as you go from one layer or one tensor to the next, these layers might change. We might flatten them, might bring in numerous, in the case of the convergence neural network, we have all those smaller different mappings of features that come in. So each one of those layers coming through is a tensor if it has multiple dimensions coming in and weights attached to it. What are the programming elements in TensorFlow? Well, we have our constants. Constants are parameters whose value does not change. To define a constant, we use tf.constant command. Example, a equals tf.constant 2.0 tf_float 32. So it's a tensor float value of 32. B equals tf constant 3.0. Print AB. If we did a print of AB, we'd have tf.constant, and then of course B is that instance of it. Variables. Variables allow us to add new trainable parameters to graph. To define a variable, we use tf.variable command and initialize them before running the graph in session. Example, w equals tf variable 0.3 dtype tf_float 32, or b equals the tf variable minus 3 comma dtype float 32. Placeholders. Placeholders allow us to feed data to a TensorFlow model from outside a model. It permits a value to be assigned later. To define a placeholder, we use tf_placeholder command. Example, a equals tf placeholder, b equals a times 2. With the tf session as SESS, result equals session run, b comma feed dictionary equals a 3.0, print result. So we have a nice example there of a placeholder. Session. A session is run to evaluate the nodes. This is called as the TensorFlow runtime. So for example, you have a equals tf constant 2.0, b equals tf constant 4.0, c equals a plus b. And at this point, you'd go ahead and create a session equals tf session, and then you could evaluate the tensor c print session run c. That would input C as an input into your session. What do you understand by a computational graph? Everything in TensorFlow is based on creating a computational graph. It has a network of nodes where each node performs an operation. Nodes represent mathematical operation and edges represent tensors. Since data flows in a form of a graph, it is also called a data flow graph. And we have a nice visual of this graph or graphic image of a computational graph. And you can see here we have our input nodes, our add, multiply nodes, and our multiply node at the end. And then we have the edges where the data flows. So we have from A going to C, A going to D. You can see we have a 2 flowing, 4 flowing. Explain generative adversarial network along with an example. Suppose there is a wine shop that purchases wine from dealers, which they will resell later. So we have our dealer going to the wine, our shop owner that then sells it for a profit. But there are some malefactor dealers who sell fake wine. In this case, the shop owner should be able to distinguish between fake and authentic wine. The forger will try different techniques to sell fake wine and make sure certain techniques go past the shop owner's check. So here's our forger fake wine shop shop owner. The shop owner would probably get some feedback from the wine experts that some of the wine is not original. The owner would have to improve how he determines whether a wine is fake or authentic. Goal of forger, to create wines that are indistinguishable from the authentic ones. Goal of shop owner, to accurately tell if the wine is real or not. There are two main components of generative adversarial network. And we'll refer to it as a noise vector coming in, where we have our forger who's going to generate fake wine, and then we have our real authentic wine, and of course our shop owner who has to figure out whether it's real or fake. The generator is a CNN that keeps producing images that are closer in appearance to the real images, while the discriminator tries to determine the difference between real and fake images. The ultimate aim is to make the discriminator learn to identify real and fake images. What is an autoencoder? The network is trained to reconstruct its inputs. It is a neural network that has 3 layers. Here the input neurons are equal to the output neuron. The network's target outside is same as the input. It uses dimensionality reduction to restructure the input. Input image comes in, we have our Latin space representation, and then it goes back out reconstructing the image. It works by compressing the input to a Latin space representation and then reconstructing the output from this representation. What is bagging and boosting? Bagging and boosting are ensemble techniques where the idea is to train multiple models using the same learning algorithm and then take a call. So we have in here where we're bagging, we take a data set and we split it. We're going to have our training data and our test data. Very standard thing to do. Then we're going to randomly select data into the bags and train your model separately. So we might have bag 1, model 1, bag 2, model 2, bag 3, model 3, and so on. In boosting, the emphasis is to select the data points which give wrong output in order to improve the accuracy. So in boosting, we have our data set. Again, we split it to test data and train data. And we'll take bag 1 and we'll train the model. Data points with wrong predictions then go into bag 2, and we then train that model and repeat.
So guys, we have come to the end of our full course. If you have any doubts or questions, ask them in the comment section below. Our team of experts will reply you as soon as possible. Thank you and keep learning with Simplilearn. Hi there, if you like this video, subscribe to Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, you can check the description box below.